I'm a motherfucking philosopher still. I'm still a philosopher. It's difficult. I'm a good person. Will. Just trying to prove to you guys I'm a black hole. Brian Green, I talked to you last night, man. I don't know if we could go at it, Brian. You really want to go at it, buddy? It's about to be an hour and 40 minutes of some shit.
Good evening, everybody.
Reality since Einstein. What up, Brian?
Thank you.
I'm a black hole still.
Thank you. Day 4 of the World Science Festival. Man, it goes by quickly. As you may know, one of the themes in this year's festival is the celebration of Einstein's general theory of relativity.
Right, no
this
shit.
November will be the 100th anniversary of that discovery. We had a show here Wednesday and Thursday, Light Falls. We had an interesting presentation today on the Shoulders of Giants by Edward Witten, which touched on these ideas.
Did you
and
sleep,
tonight's
buddy?
program, we're going to go through the history of the discovery to some extent, really focusing more on the scientific ideas as opposed to some of the other features that we emphasize in some of the other programs. And then we'll go from that discovery to look toward the future, the interesting things that are on the horizon and the puzzles and problems that people are struggling with today. My own introduction to the general theory of relativity was way back in the 1980s when I was an undergraduate.
What?
1982 in particular, I was a sophomore at Harvard, and there was
KPN
this
8.0.
rumor
It's you and me,
going around
Brian.
that Stephen Hawking was coming to give the Loeb lectures and all. Everyone was so excited. And the thing is, I was embarrassed to say, at that time, I didn't know who Stephen Hawking was.
Philosopher Chris Payne,
so all the physics majors are running around saying, aren't you so excited that Stephen Hawking is coming? And I'd be like,
look at you, man. You just mimicking me.
But, you know, as time goes by, you know, Stephen, of course, became a renowned figure worldwide. At that point, he wasn't. But the amazing thing was, I went to his lectures.
Yeah, you're mimicking. What?
And it was a stunning experience to have Stephen Hawking take us using mathematics to the edge of the universe. So I left his lectures pumped, and when the final lecture was done, I just wanted to know about general relativity, which was the core of what he was describing. So I remember leaving the Science Center. It was Lecture Hall B, and running across the Harvard Yard to the bookstore, the Coop, and I ran to the physics section, and I went and bought a book on the general theory of relativity. In fact, I have that very book right here.
No way.
If you look at the edge, you see that I have read it, right? It's being held together. And, you know,
I'm red,
the thing is, when
my
I was
light
a
is red
sophomore
right
in
now.
college,
I'm a black hole still.
I didn't have the background to understand this book, but I had it around with me.
I did.
All the time.
Sorry, dude.
You know, sometimes I'd be having lunch and I'd take it out of my bag and I would just kind of caress it. You know, and I'd like, I mean, isn't it a beautiful thing, this book? And it's just an amazing thing.
What's in the book?
It's also wonderful for me here tonight because the author of this book is Steven Weinberg, who is one of our guests here tonight, and we'll be hearing from him. And this was something that had a great impact on me. So what I'd like to do is get right into the discussion.
Steven Weinberg.
And let me begin, and before I do that actually, and I'll only have to do this at this stage, they printed out the introductions in such small font that I can't read it, and I don't have any of my own glasses, so my wife lent me hers, which is a little ridiculous.
Sorry, buddy.
Well, actually,
your wife, though.
There's a second pair. I don't know. You tell me which is less silly looking. She gets these at like Rite Aid or something, and I don't know.
Snap, the tiger print, right.
I'll go with the black and white ones. Good. All right. Anyway, they'll adjust me for this. You will not have to put up with this.
It's a black hole, yo.
It's much longer. Okay, so let's get going. Our first participant is one of the most renowned physicists of our age.
No way.
He's a recipient of the National Medal of Science, and he is the winner of the Nobel Prize in Physics. So please join me in giving a warm welcome, University of Texas, Steven Weinberg.
Wow, okay. Steven Weinberg, what up, buddy? Damn. Hey, man.
Hi, Brian. Hi, Steven. Next, we have a theoretical physicist who has made groundbreaking contributions to quantum gravity and string theory. He's been awarded numerous prizes for this work, and is a professor of physics at Harvard University. Please welcome Andrew Strominger.
Makes sense, man. Makes total sense, yo. Harvard, accolades. That's cool, though, man. That really is cool.
Also with us tonight is an award-winning physicist who's also from Harvard University, whose primary area of research is string theory. Recipient of the Dirac Medal and the AMS Leonard Eisenbud Prize for Math and Physics. Please welcome Qumran Vafa.
Qumran Vafa. Qumran Vafa.
Next, we have a professor of physics and astronomy at Louisiana State University, which is just 30 miles away from the LIGO experiment, and she is a member of that team and spokesperson of the LIGO Scientific Collaboration. Please welcome Gabriela Gonzalez.
What? LIGO?
All right, our final participant is a physicist who has spent over 2 decades working on the black hole information paradox. His background is in string theory, general relativity, and astrophysics from Ohio State University. Please welcome Samir Mather.
No shit. You were literally... Wow.
All right, so we're going to organize the discussion tonight because there's a lot of material that we'd like to cover in basically 5 chapters. We're going to start with a discussion going from Newton to Einstein. Then we're going to, in there, talk about the basic ideas of general relativity. We'll then move on to a discussion of cosmology,
Is there audio of him?
Some discussion of gravitational waves, and depending on how much time we have left, we'll return to some of the interesting paradoxes that people are struggling with even today.
Sorry, guys.
With black holes.
I did not mean to bring that up.
By way of organization, there's another book on gravitation, general relativity.
Sorry, listen, dude. When you keep bringing these books up,
which makes it relevant.
I don't know if I'm buying it, man.
But you may.
I don't know if I'm buying it.
There are these little gray areas. I don't know if you can see it from
over
there.
Yeah, you probably can't see where that paper's made from.
White in the corner, and there's sometimes gray in the corner.
Right, yeah.
I don't know how easily you can see it, but it's track 1 is the gray, and track 2 is the white. So the book was written so that you can have a reader who can follow just the track 1 a little easier. Track 2 is a little bit more difficult. And I bring this up because tonight we're going to basically have track 1 and track 2 listeners in the audience.
Right.
There are going to be moments here and there where we're going to get a touch more technical just for a moment for the members of the audience who want to see a little bit of the math, a little bit of the equations. We won't really focus upon it, but it will just give some mathematical underpinnings to some of the ideas that we're going to discuss. So if you don't like math and you don't follow that, don't worry about it. And if you do, hopefully it just enriches the discussion a little bit for you. All right.
Discussion about what?
Let's get started. And very quickly, before we
I'm a black hole.
The matter, I was inspired today. I went to, there's a World Science Youth for a Day. You may have seen this on the website, series of lectures. And Adam Rees, another Nobel laureate, gave one of those lectures today. And he described how
Adam Rees.
There was one particular aspect of physics, the details don't really matter right here,
One Tree
that he
Hill.
felt was so important to his life that he could imagine tattooing it onto his body. Now, he didn't actually do the tattoo, so, you know, how important was it to him? But it began to make me wonder, what aspects of physics would I tattoo on my own body? Or putting it a little bit more sensibly, what aspects of physics have just been so vital to my life that I consider them sort of an indispensable part of the way I look at the world? I just want to get a quick sense, what aspect of physics do you consider to be the most important part of your academic, or maybe more generally? So can we just anything that comes
you need to
mind,
type it or write it.
Gabriella, is it general relativity, quantum mechanics, Newtonian physics, anything like that?
It's actually general relativity, but the particular
I was hoping
aspect,
you would say that.
it's the point that space-time is dynamic.
Yeah.
When I grew up, I thought that space-time was something we lived in.
No.
But then when I learned that space-time actually moves around.
Gabriella, how we doing?
That just took me over.
Qumran, anything that comes to mind?
I just took you over?
The connection between, related partly to what we just heard, the connection between physics and geometry. The fact that you can geometrize physics in different ways Einstein's theory is a prime example of it, and then there are more modern examples where forces can be also geometrized. That's what attracts me quite.
Very good. Samir, anything come to mind?
Yeah, for me, black holes have been really the most fascinating thing, because in a black hole, everything gets crushed to an infinite density, it seems, and we just don't know what happens when that happens.
Right.
Infinite density.
I think the Einstein equation
Infinite.
would make a very fine tattoo.
Yes. Are you willing to actually do it, though? Will you
Yeah,
go through with it?
my
Gold
friend,
glasses, right?
my
We have
friend
a guy right
literally
backstage who's ready
has
to
a
do it.
tattoo on his calf of Einstein
the
sticking a
Schrodinger
tongue out,
equation, quantum mechanics,
and I went with him to get it.
And I would put in, with that, I would put the Bekenstein-Hawking area entropy law that we will come to at the end of this.
And-
You will be
Entropy.
the illustrated man after all of these tattoos. Stephen, any?
I think I'm probably less rhapsodic about general relativity than other people on the stage. I try to see it as part of physics, not really that different from electromagnetism or all the forces and particles of the Standard Model. I'd like to see an intellectual framework for thinking about them all. And the one
Right here, buddy.
area of physics that, the one kind of physics that does underlie everything, including general relativity, as Andy mentioned, is quantum mechanics. I think that really is
Yep. Is what?
the master theory. And it's just a pity I don't understand it very well. but which I'm solaced by the fact that no one else does either.
Really?
But
What?
from that point of view, general relativity isn't so special. It's just the theory of particles of mass 0 and spin 2. And
Of course, as everyone here knows.
all of the wonderful properties of general relativity that Einstein developed from his deep insights about curved space-time and so on really follow from that very pedestrian point of view.
Now, can you take us through the history?
You walk in my leg.
Starting with Newton. So Newton gave us our first approach to understanding gravity. And what was that, and what was wrong with it?
Well, Newton made the great breakthrough. I think modern science begins not so much with Newton, but with Newton's account. I mean, he was a strange guy, but
Isaac Newton?
he
He had interesting hair, though.
he lived in England, and he was very interested in the tides, and he thought he had a theory of the tides. He actually
Wow,
did have
he
a
had
great
long ass hair.
of the tides, but he never bothered to look at the sea in his whole life.
Wow.
He never saw the sea. What kind of a person is that?
He's got
But his theory was controversial at the time. It was rejected by, on philosophical grounds, by followers of Leibniz and Descartes. It turned out,
They
however,
followed him?
wherever they disagreed, Newton was right. His theory went on from success to success. It had already explained the motion of planets under the influence of just the gravitational field of the sun. And it went on to explain so much else, like the motion of the moon, which is a much more complicated problem, the
Nah, there was
precession
a full
of the
moon last night,
equinoxes,
and I was
all sorts
I was
of
not
things,
tripping,
the-
but I was
the
specifically
influence of the planet,
what I would describe
Saturn,
like,
on the motion of Halley's comet.
entangling you.
All of that, and it worked so beautifully, and it became,
Thank you.
by the end of the 19th century, the paradigm of what a physical theory should be.
So, just to give a
19th
little
century
basic, most people are
paradigm.
familiar
Paradigm
with this
shift.
equation over here, which was the law of gravity that Newton wrote down. But what did Newton, how did he view space and time? What was his perspective on that?
Newton
How did he describe it, and how do you know? He wrote books?
Came to the conclusion, which he stated in the Principia, that there is such a thing as absolute space. He knew that motion at constant speed relative, one observer moving at constant speed relative to another didn't matter, they were all equivalent, but there was a fundamental frame of reference with respect to which you measure acceleration.
Acceleration?
So that there really was
Tilt
a
on the
space
axis?
out there.
Background stage or something?
Yeah, and the time, and it really was not something that was subject to physical intervention. Space was space, and it was there, and it was fixed, And when she pirouettes and then when she pulls them down, she goes even faster.
Right.
That's because she's rotating with respect to absolute space. Newton,
Me?
in a famous example, the rotating water bucket,
Yes.
described away from.
So what
Huh?
drove people, or Einstein in particular, when
To
there's
get
all
away
this
from what?
observational support behind the predictions of F equals G, M1, M2 over R squared to come up with a new approach?
Well, it sure wasn't the observation, not driven by data at all.
It brought me
There were
here,
little bits
dude.
of data that didn't agree with Newton's theory about the motion of
Oh,
Encke's comet
God.
and the moon and so on, the precession of Mercury. Most people regarded those as things that would be fixed by the discovery of
What?
a new planet or some non-gravitational
Really?
force, and most
No.
of them were fixed in that way. There was nothing that stood out and said, I am a piece of crucial data that shows Newton is wrong. Einstein was trying to bring into all motion, including accelerated motion, the same relativity idea.
Einstein? He really
And
thinks
when
so?
you read his 1915, 1916 papers,
How do you-
that's what concerns him. It's not the way I teach general relativity now. I just taught it last year. Even apart from mass zero and spin 2, I try to base it on the principle of equivalence, which is also due to Einstein. But
Right.
that was his aim, to try, and that's why he
Einstein.
formulated his
He is important
his
to me.
theory in terms of equations, which take the same form, whatever coordinate system you're using. This
Yes.
is so-called principle of general covariance. And that was the driving principle for Einstein. And it was difficult for him because he wasn't a master of differential geometry.
Right.
He had to learn it from
Wow.
Right, Marcel Grossman and folks like that, Michele Besso as well. So, can we just
Wow.
give the audience, I think many people have a rough sense, but it's good to do it
Nope.
explicitly. If we now are thinking about gravity in the Einsteinian perspective,
Come
how
to me.
does one talk about, say, the Earth going around the
In
sun?
the
How
what
would you describe that
perspective?
in an
Wow.
Einsteinian point of view?
Well, at the level of
Just-
things in the solar system, there's no problem. I mean, we like to talk about curved space. It's a pretty picture, but you
And
could
we're showing
also,
a little picture.
yeah, you could also. I'm not looking at the picture.
Okay, good.
They just confuse you.
Right. Sorry, buddy.
But you solve differential equations. We have an equation that tells you what the gravitational field is produced by the sun, and then we have another equation that tells us how the Earth moves in that gravitational field. You
Right.
turn the crank and you solve the equations.
How,
That's
what
not
turned
where
what
the
crank?
where the general relativity reaches into trouble.
Right.
Right.
Yeah, we
Sam, we'll
have
get to
none,
some of the
sir. We
problems
have none,
of
sir.
General relativity in just a moment. But what we're showing up here is sort of the basic idea of the sun warping the space-time environment and then keeping a planet like the Earth in orbit because it's following the straightest possible path in a curved arena, which in this case is the usual
Quantum
path
field.
that we ascribe to the motion of the Earth.
Me-
We have another little video here that again just gives this sense of objects curving the environment and thereby affecting the motion of other objects. And you quickly mentioned the equations, and again, this is part of our track 2 listener thing. Let's
Yeah.
just show you what the equations that Einstein wrote down look like.
No
So
shit.
this is
So
the
he's track
most
2.
simplified form. The
Of what?
equations
KPN
that Einstein
8.0.
initially wrote down. We'll talk about possible
Yeah.
amendments to these equations
8
going
pi G,
forward.
C4.
But the left-hand side is geometry that you were talking about, and the right-hand side is talking about matter and energy. And there we have the basic form of the Einstein equations. Now,
Holy shit.
Andy, why did people agree that Einstein had taken a vital step forward? What was the observational support behind this stuff? And in particular, I'm thinking
You
about
just
the
helped
solar
my black
eclipse
hole.
experiment.
Well, it's an interesting thing that
Wow, theoretical
Einstein
physicist.
himself,
What's up?
as Steve mentioned a few minutes ago,
What's up,
had
Andrew?
some data that he
I
was
talked to an
studying.
Andrew last night. He's
And
cool.
one of them was the fact that Mercury's orbit didn't do exactly what Newton said it would do. And it was a very tiny discrepancy.
Probably.
And Einstein, when he wrote down his general field
What do you
equation,
mean?
found that explained this very tiny discrepancy.
Yeah.
And in
You talking
his
about
own
Mercury?
notes, he says that
You tried to
he
measure it?
knew that was the moment at which he knew. He said something inside me snapped. That was the moment in which he knew he had it. He'd solved this great problem. But nobody bought it.
What?
Because what a crazy thing to do, to introduce and revolutionize our idea of space and time.
No.
Say that space is curved and so on, just because some French astronomer 100 years ago, his experiments didn't match up to Newton. So nobody bought it. When you explain
But
something
mine match
that
up
has
because I'm
already
the
happened,
superposition.
it's not convincing. Einstein then made a prediction.
I'm convincing.
And his prediction would be that starlight would be bent by the sun. If starlight passed by the sun, it would actually be bent. And that made a prediction about what would be seen for stars passing near the sun during a total
Starlight
eclipse.
is bent.
And
near me.
Prediction was
So my light is
verified.
bent
I think it was almost 5 years after Einstein wrote down his equation.
in my black hole. But how do you
And
get sucked in,
he
dude?
became an overnight celebrity.
Yeah.
No way.
So we have a little picture just emphasizing what
Of
you
me?
described. So you can speak to it if you'd like. So you see the two images of the star, one coming from the fact that the trajectory of the light ray is bent as it passes by the sun, shifting its apparent position in the sky. And indeed, as
Right.
you mentioned, Einstein calculated the angle between those two, and the observations confirmed it, and
Whoa.
that was convincing.
Whoa.
I think the reason that
Holy crap.
the
Why is it a different
fact
person to me?
that Einstein explained something that was already
No,
known was
no,
less
it's
convincing
still me.
than the prediction of something new was the natural tendency of people is not to trust the theorist. That is, they suspect that if
Isn't
you
it a
have a
theory,
known
though?
fact, the theorist will be able to jigger his theory to get it into agreement. If you know anything about the way Einstein developed general relativity, that's not true.
How do you know
He
him?
did
You know him?
not design his theory to explain that extra little motion of Mercury. He used that motion to test his theory. In fact, in earlier versions, he had gotten the wrong result, and therefore he knew that those earlier versions weren't any good.
Whoa.
And on the other hand, you really shouldn't
Mercury.
trust the experimentalist, because the experimentalist knows the theory
Yeah.
and is likely to jigger his experimental data to get the right result. In fact, many people have accused the
All of them did, I feel
the
like.
astronomers of 1919
How can
who
you prove
observed
them?
the eclipse of having.
Like, let's start now.
They kept finding errors until they got a result in agreement with Einstein's theory.
Yeah.
Yeah, they were potentially
black
throwing
hole.
out photographic plates that they claim were obscured by the bad weather, and those happen to be the ones that didn't quite agree with the prediction. But since then, there have been many other experiments. that
So
have nailed that.
always trust the
Prediction.
theorist.
Wow. He predicted me.
So, Kerman, discussing it from a theoretical perspective, just one quick point that I want to emphasize.
What is his prediction?
A lot of people think about Newtonian gravity and Einsteinian gravity in opposition in some sense. But in fact, they really fit together in a beautiful way that help guide
Who's the bigger
Einstein,
black
in fact,
hole?
toward the right
God?
result. So, in what sense
Sir?
can we extract?
Brian?
And can we do that? Can we extract Newton's ideas from
Yes.
Einstein's?
You can take mine. Who's
Ideas in
Newton?
physics usually are not, none of them are in the sense wrong, but they get deformed, they get more correct. Just like Einstein's
Right.
theory is not the final theory necessarily, but it was a correction or it was an improvement to Newton's theory. And so in some sense, a check of a new theory, a new idea, is that it should reduce to the previous known facts in certain limits, the limits of validity of the previous theory which has been experimentally verified. So in particular,
Verified.
in Einstein's theory, the space and time get curved, and
Verified?
when
What are you
this
verifying?
curvature is not very mild, if it's mild and it's not very strong,
Okay.
we are in a situation where Newton's equation should come true.
KPN
And
8.0.
those are the cases where
Yeah.
if you take Einstein's theory and go to the weak curvature limit and try to expand
Your weak
those
curvature.
equations, you find that the description that Einstein gives in terms of particles moving in straight lines, or more precisely geodesics, which are shortest distances in
Huh?
the curved space-time,
Geodesics?
gets replaced by the idea that Newton had, which is the particles actually move in a path and they accelerate according to the force that they experience. And some particular, what Newton would have called the potential was a part of the data which describes this fabric of space as a particular way that the fabric of space and time is curved.
Right, because I'm entangled
with
you,
you, that term
buddy.
up and use that, and you show that the geodesic motion reduced to what Newton would have predicted. And so that is a check that it actually works. And
there it is, right
From
behind you.
Einstein to K.
Details
Payne,
attract
philosopher
listeners,
Chris
but
Payne.
Again, the point is you can start, as Kerman said, with Einstein's equations and extract Newton's from them in this particular limit. So it all fits together into a beautiful story.
It does.
All right, so that's the
Philosopher
sort
Chris
of basic ideas that underlie this
Brian.
discovery. What I
Hey,
now
buddy.
want to turn to is a discussion of
hear
some
me?
of the places where this discovery has taken us. And we're going to begin with a discussion of cosmology.
Is this really in
And,
2015,
Kerman, why don't
sir?
we start with you? So, people have been talking
Why'd you
about
look
the
away?
origin of the universe since we
Whoa,
looked up
right.
at the sky.
No way.
It really
It's origin right
became
here, right
a
now.
quantitative subject with general relativity.
Is it me?
Who
I'm
were
the
some of the
origin
early
of the
people that
universe.
began to
Holy-
think about cosmology in an Einsteinian perspective?
Because it
Yes,
just gives me so much
so-
life.
I think the idea that, first
Wait,
of all, the
what?
notion of objects in outer space and so on, there was even a question that Newton even was puzzled by and was thinking about what keeps things the way they are. And so there was the issue of cosmology in some abstract sense was already there even before Einstein came to even discuss it or study it.
Everybody had
but
an
Einstein
idea
could
of
not avoid it, which is what the difference was. In the context of Einsteinian theory, the fabric of space and time is not passive. It's not a passive thing. It's part of the datum of the physical theory.
Right,
So
he
couldn't
grew up
just
and
say,
he saw the
"Ignore,
moon."
Everything is rigid. I just have particles in it moving," like Newton would have liked to. But he had to deal with the fact what happens to these distances, to these shapes.
Yeah,
And so he had to come up with an answer to these
I
questions.
do. I'm
otherwise
sorry, guys.
He would not be doing justice to his own theory. So he had to
Right.
come up with a picture of what's going on.
What's a picture?
And so that was the beginning of Einstein's
This is video?
trying to fit what he saw into his equations.
A picture.
And
What?
the thing that he saw in the universe was, you have stars and galaxies and so forth. I guess he would have wanted to say things are the way they are, somehow static. That was the prevailing idea that nothing is really changing on the average, and more or less things are homogeneously distributed in some way.
Until I make
and so he was
pictures.
trying to fit this picture of a static, more or less homogeneous universe into his model, and that's what he attempted.
And then some of the people who took
No,
his ideas
what?
further and found indeed that the true story was somewhat more subtle than he had initially hoped. So we have, some of the characters involved are George Lemaitre, who we see over here,
Lemaitre.
and Alexander Friedmann. They took his equation. What did they find?
Well, Einstein himself found a way, which is, I think, one of the most remarkable things, is that he found a way
What?
with his equations to accommodate a static universe, which is, I think, even before we got to these gentlemen, that he could actually say that there is a way, in the context of his theory, to introduce a term, a fudge factor, actually, in some ways, we could say these days, found a way, which is, I think, one of the most...
Some of the characters involved are George Lemaitre, who we see over here, and Alexander Friedmann.
Wow.
They took his equation. What did they find?
Well, Einstein himself
Whoa,
found a
so
way.
Alexander
which is, I think, one of the most
Friedman is
remarkable
literally
things,
me
is
using
that
my
he found
free
a
will.
way with his equations
And it's
to
Russian.
accommodate a static universe.
Wow.
Which is, I think, even
So you
before
have
we got to
the
these gentlemen, that
superposition
he could
of me.
actually say that
They're
there is
now
a
looking
way
up
in
both
the
these
context
guys.
of his theory to introduce a term.
We have the father of the
a
Big
fudge
Bang.
factor, actually, in some ways, we could say.
We
these
have Alexander
what's
Friedman
what's
and
called
philosopher
cosmological
Chris Payne.
constant. He put a term which prevented the universe, so to speak, to collapse. So he had so matter would have wanted in general to collapse by its gravitational pull on itself, and he introduced a term in his equations which had the effect of pushing matter out.
Yeah, philosopher
So
Chris
this
Payne and
balance
these guys.
between, collapsing
Chris
and pushing
Payne,
out, he managed to
George
tightly
Lemaitre,
balance them in such a way the universe was static.
Alexander Friedman.
But it was pointed out that this is a non-stable situation. You can arrange it, but if a tiny bit changes, it either collapses or expands the other way, so it's not a stable equilibrium. It's like putting a pencil in its head and hoping that it will stay there. So it wasn't a satisfactory solution. So his universe, what's called the Einstein static universe, was not a satisfactory physical universe. And
It's
then
not. It's a
George
superposition.
Lamarck, which was a priest and
Who?
also a physicist, And,
Who?
Emphatic universe was not a satisfactory physical
Emphatic
universe. And then,
universe.
Georges Lamaitre, which was a priest and also a physicist, and Alexander Friedman, they had independently come up with trying to understand what happens using Einstein's theory, just to allow having some space and possibly expanding or changing. And in particular, Georges Lamaitre had the picture that things started from a primordial atom, or what he called the egg, or some concept like that, where things started from a small thing and started expanding.
Right.
And within the context of Einstein's theory, they found it beautifully fits with Einstein's theory, and it was they found a natural home in this idea of trying to have an expanding universe in that context.
Yes.
Which is ultimately what now is called the Big Bang Theory.
It's
we have a little video just
Black
in
Hole
sense
Chris
of what you're
Payne.
saying. Universe begins in this primordial atom
Philosopher
or egg,
Chris Payne.
through this outward swelling, grows, cools down.
Black hole
structures
philosopher
that we
Chris
know about
Payne got
begin to
spots.
coalesce. So in
You
a
know he
nutshell,
hot.
that's the idea that they came
Don't
up
get
with.
pulled in.
Again,
or
just to give a sense of this, again,
get
not
blocked.
just artist renditions of stuff, but we see a little
Wow.
bit of the math.
Artist
Maybe you can take it to
renditions.
us quickly. So
No way.
this is
Wow.
the usual way that we describe it.
Okay.
And A of t is the scale factor of the universe, how far apart things are.
Yep.
And then the equations
Right here we
that you're
go.
referring to.
Yep.
It looks
8.0.
a little bit complicated if you're
Keep
not
pin
familiar with it,
8.0,
but the
I'm
bottom
following
line is, as Steve was saying, you've got equations.
Yep.
You turn the crank, you see
Yep.
what it says for the size of the universe, and
Right.
it grows in the manner that that video was illustrating.
Wow.
It all holds together extremely well.
Thank you
And
guys.
then observers saw it.
Then observer says exactly what we're going to get to. So first, what did Einstein himself think about this ultimately? Did he initially accept it with open arms? Did he
Did you just
reject
throw it out?
Well, he did not like it, and he
Einstein.
actually thought that even though the mathematical application of his equations are fine, he did not believe the physical motivation is correct.
You talked to
So
him?
I mean, at least according to Georges Lamaitre, from what we understand,
The priest, the origin
in
of the
fact,
Big
he said,
Bang?
your math is fine, but your physics
It's not there.
Abominable, I think it was. Yeah,
Yeah.
exactly.
something to that effect.
Right.
Yeah, no, because I'm philosopher Chris
So-
Payne.
and of
I'm
course he
me.
was
You got to
in some
see
sense
me.
Justified because there was no observational evidence for the universe expanding, so he was just trying to fit what is known at the time, namely a static universe, into the equations. So that
Yes.
was his motivation.
So then what happened, Gabriella?
Then,
The observation.
Gabriella,
Observations came.
Yes.
They
observations.
saw the universe expanding.
So they means.
Wow.
Actually, the observations were there. They weren't taken very seriously, but a man named Slipher had observed a systematic
Wow.
redshift of distant galaxies long before any of this happened. And
No way.
picked up after
Slipher the
Einstein's
Sky
theory
Dragon? That was
as early as
Yu-Gi-Oh.
1922 in Eddington's textbook as evidence for an expanding universe.
Holy
not bad.
snap.
If you look,
Slipher
if you
the
looked in
Sky
right
Dragon.
direction, there was evidence of an expanding
3
universe,
Egyptian gods.
even at the time of Lemaitre's paper.
Oh,
And,
holy
Friedman
snap.
was 1923.
Yes.
So there was already evidence for an expanding universe. I think Einstein's view was not that he was against the expansion of the universe. I think it was bitter regret that he introduced the cosmological
This is
constant
so
and tried to
meant to
keep it
be.
static. And I may be wrong about this, but I think he
Huh.
accepted the expanding universe and was sorry that he
Huh.
had tried to prevent it with his cosmological constant. Of course, from my point of
Einstein
view,
tried to
because
prevent
the
it?
cosmological constant is a possible term in the equations, it's got to be there. There's no reason for it not to be there.
Cosmological
and in fact,
constant.
we now know it is there. And
Cosmological
Einstein's mistake
constant.
was in thinking that he had made a mistake in introducing it.
But by
Yes.
1927, he was
Sorry.
rejecting Lemaitre. So somewhere.
Was he? I didn't know
Yeah,
that.
yeah, Devin, that conversation was in 1927. So I don't know, somewhere in there. But ultimately, it was Hubble whose
27. I'm not
observations,
27
really
yet. I'm
made a
rejecting
difference.
it, yes.
And it's interesting to point out that
I'm
I
Hubble.
love saying this. Hubble
guys.
was trained as a lawyer,
Yep.
became an astronomer, which means there's
Yeah.
hope for everybody.
Yeah.
And,
Philosopher Chris
so
Payne.
his observations that you're about to tell us were of distant galaxies. What did he find?
I found,
And that was difficult to understand. Because, in the beginning, when they saw that everything, all the galaxies.
Did you come in my black hole yet?
Milky Way, then it sounded like the Milky Way was at the center of the universe. But
The Milky
physicists
Way.
had learned to know that. we
What
were
is the
not at
Milky
center of the
Way?
universe. So the idea was that the whole universe was expanding. And
Why do they call it
continued
milky?
Observations and Einstein's theory, I think, was beautiful.
And here's a nice shot of Einstein at Mount Wilson Observatory.
Mount Wilson Observatory.
This is, in principle, when he was becoming really convinced that this data established that the universe really was expanding.
Wow.
Quickly, the idea of a Big Bang has been around for quite some time, but it's been developed since then. We have more refined versions of the inflationary theory of cosmology. Samir, can you give us a moment of sketch of what the inflationary theory is?
I'm inflating right now. What's up? Sorry,
it's a
buddy.
Interesting situation
Hey, Samir.
that our universe looks so homogeneous and so flat. But if we just start from first principles, it's not clear why everything should be so homogeneous everywhere. Because after all, what you see on one edge of the universe has never had any time to talk to what's happened on the other edge of the universe. Because light hasn't had time to go from here to there.
It will.
So why does everything
I'm a
look
black
the
hole.
same on all the sides? And so the idea was, if we start with the universe, which was very tiny, the size of about a marble, and then suppose it just grew from there very fast, and all that we see today really came from one marble, which in fact could have talked to each other all over.
God.
Then we could sort of explain why everything was so homogeneous, and because the whole marble just expanded, when you stretch something, it just becomes flattish. And that's why the whole universe is so flat. So it explains the vastness of our universe, why there's so much stuff there, why it's so homogeneous. It's really a very remarkable idea.
And so this is the inflationary theory. And
But
again,
it's
for those
philosopher
who just want a
Chris
little bit
Payne
of the
right
math
here.
behind it, it comes from the fact that
giving you a
in
map.
Einstein's theory, it's not just mass or energy that
Well,
yields
no,
gravity,
it's
but
me
it turns out
right
that
here, right
pressure
now.
does
It's
too.
2020.
And the pressure in the early universe could be negative, rapid expansion, which
Potential?
goes by the name
What?
of the inflationary theory. And the beautiful thing is, going back to observation, a lot of evidence.
You
Anybody
guys
wanna
get
just
paid to do
mention
this?
what
Who are
that
you
is?
guys?
And I'll show a little picture to
What?
go with it.
Policing?
They are at the same temperature here.
Blue
and
Lives
that's
Matter.
the best-
And the
that's
red
the
is
best
there, the
evidence we
yellow is
have
just
of this
brightening.
inflationary period, but it's not exactly the same. It's
Is
actually
that our Earth?
slightly different in a part of a million that can be explained.
Which are the little speckles that people are seeing up here.
Those
Yeah,
differences
that's
there
like our
are
Earth
very,
on a
very small differences.
Santa,
like I
the
said,
NORAD
parts in a
tracker.
million, but they can be detected. They have been measured.
Temperature differences from place to
Temperature
place.
differences, right? Difference in the temperature.
Temperature.
Of,
And
these
not
microwaves.
electromagnetism or
And
magnetism.
that can
There's a lot of
fit
properties in that stuff.
beautifully to theories.
Yes. So let me just show you. Maybe you can take us through this. So this is the theoretical curve that comes out of these calculations.
All these
Yep.
bumps
When
are
you show a
predicted
picture and
by
I
the
try to
theory,
describe
and
it.
all the experimental points follow it beautifully.
Yep.
So we are in what we call now an era of precision cosmology, in the
Right.
sense that there are many constants, parameters that tell us about cosmology that we know very precisely. We don't always understand where they come from or what they mean, but we can measure them to a part in 1,000.
And there you go, the agreement
Measure?
between theory and
What?
observation. So Steve, what would you say is the biggest unsolved problem?
So you have a
in
theory and I have an
cosmology?
observation.
Oh, in cosmology, I think it's clearly just what we've been hearing about, the
Unfairness?
acceleration of the universe, the presence of this dark energy.
Wow.
Which, as you said, produces a negative pressure,
Black
not just
hole.
in the time of inflation, but at present, although very much less.
Mm-hmm.
And the big mystery about it is not why it's there, because in fact,
You don't have it?
any quantum mechanical theory is going to produce this
The heart
kind of
and
dark
mind?
energy. That is an energy inherent in space itself, as just a consequence of the fact that fields are always fluctuating and that produces energy. The amazing thing is that it's so small.
What's small?
It is at least 56 and maybe more orders of magnitude. So 1 with 56 zeros, smaller than you would guess from the simple estimates you can make. And that, I think, is the great problem. And
Whoa.
it's very important because
The
if
first
it weren't
six
true, we
triangular
wouldn't be
numbers.
here. There wouldn't be time for galaxies
And
and
I'm
stars
forcing
to
vibrations.
form. Whether there's any connection between those two remarks,
There
well,
are.
we wonder about.
It's the number
But
6.
that, I think, is the great problem. And it's one that's extraordinarily difficult to get a handle on.
Sticky Jack.
Because this is an energy in space itself. I mean, when you want to
Why are you
see
closing
what
your eyes?
energy there is in an atomic nucleus, you let it decay and then it becomes something else. Well, we don't know how to do that with space. It's just out there and affecting the expansion of the universe. There was a company, I think in Texas, that was trying to make money by getting investors to invest in using the energy in empty space.
Yeah.
And
How'd they do?
Probably pretty good.
well, I think they probably got a lot of investment.
Right. No shit.
But in fact, you can't.
What were they
you
doing?
can only get energy out of space by destroying the space, and we don't know how to do that. So don't invest in it.
Destroying space? Why?
But,
Have you done it?
You know, that's the problem I'd like to see solved.
You've invested in
more than
it
any other.
probably?
Yep.
You know about it.
All right, so let's move on to black holes as the
Sorry, sir.
next area
Brian,
of focus.
you can smile.
Andy, why don't I start with you?
Yes.
You know, the idea of black
Wow,
holes
we
goes
made it,
pretty far
guys.
back, even before the general theory of relativity. People wondered about an
You can
object
smile.
that would be sufficiently massive and dense that the escape velocity would exceed the speed of light, so light couldn't get away from it. People thought about it before general relativity, but it really was Einstein's equations that put all these ideas on firm footing. So what's the early history? Who thought of black holes early on, and what was that all about?
Well, as you mentioned, they were thought about long before Einstein wrote down his equations. But the new
never
thing
really
about
were
the
realized.
Einstein equation is that they imply that they must exist. You can't wish them away.
Well, God is
And
there,
only
like
a few
that.
months after Einstein wrote down his field equations, Schwarzschild famously solved them and showed that they have a solution which we now recognize.
It's
as
not
a black
about
hole.
believing.
And he actually beat Einstein to the first exact solution of Einstein's equations, really.
That's
Yeah.
right. That's right. It's said that Einstein thought there would never be an exact solution.
No, I got you.
which I
It's okay.
totally,
Hey,
solved it just a few months later.
thanks for looking up.
Now, it is one of the maybe
Gabriella.
the most incredible solution of a field equation that has ever been written down.
Brian.
And what's incredible about it is that nobody understands it.
Oh.
We're still, as you'll see,
Alexander
and this will become evident
Friedman.
if we get to the end of the program,
That's not
that
him.
nobody understands what a black hole is. And yet, Schwarzschild wrote down this solution in plain form.
I did.
100 years
Adam.
ago. We're celebrating it.
Oh,
since
Samir.
now.
Yeah, Samir. Thanks,
And
Samir. We're
Einstein
celebrating Samir
himself,
today, too, with Robert Greene.
Looked at it and
And Chris
said,
Payne, philosopher
this
Chris
is
Payne.
just too weird.
Is it?
These things can't exist.
Okay, I'm sorry.
And even 30 or 40 years later, Einstein insisted that black holes do not exist because they're just too weird.
When did
Now,
he
just
die?
quickly, having said that, we got our friends at NASA to give us some high-definition picture of a black hole, just so
When
we
did
can
he die?
see what one actually looks like.
But finally, through work of Chandrasekhar,
What's it look like?
Oppenheimer, Finkelstein, many people,
Oh.
about
Is he
40
coughing?
or
Did you
50
hear me?
years after,
Whoa.
which is really a long time in
Whoa.
science, people finally began to believe that the Einstein equations
1955?
implied the existence of black holes. And this is
He
one
said
place
40
where
years
I think
later, and
that
I-
general relativity
Whoa.
really is different than the other forces because it deals with space itself.
Yes.
Leads to such striking consequences. And in some sense, a black hole is a hole in space. It's a place at which space itself comes to an end.
No, it's on Earth, dude. I'm sorry.
Now, even
It's
when
me
it
and my eyes. And me.
began to be clear that that the Einstein equations implied that that there were black holes, people still, there's such a bizarre
Implies,
thing,
like,
still
assume.
refuse to believe that they exist.
Believe?
John Wheeler called it the greatest crisis of all time.
Yeah.
That the Einstein equation predicted the black holes.
No way.
Then we studied them, we began to understand
He
them.
predicted, implied.
We kind of came to peace with them.
Well, can you tell us a little bit about how they might form, just so we can get a sense of what people were thinking about?
So, for
there?
example, you could have a
How did I
star
form?
which, what
Yeah.
happens is if you get too much matter in one place,
Like what?
The force of gravity just gets stronger and stronger and stronger.
How do you get matter there?
And eventually it becomes so strong
what is
that
gravity?
It just rips apart space itself and forms a hole.
Describe gravity, sir, please again. I'm sorry.
Another way of saying it
no, I can help
is that if you have, say, on every planet has an escape velocity. So the escape velocity
from
on the
where?
Earth, I believe, is 7 kilometers per second. And on the moon, it's less. On a bigger planet of the same size, it would be bigger. And if you have too much matter in one place, the escape velocity becomes greater than the speed of light.
Yeah.
And then even light can't get out.
Right.
And in Einstein's curved space description, this just becomes a big hole in space. There's nothing there, nothing can get out.
Sort of what we're seeing right here, the sort of black region.
Nope, nothing.
And when I began life as a physicist, there were still many people around who believed that there were no black holes, even though
I like how you guys edited this. It looks nice.
Imply they must exist. But now we see them, or we see their effects.
Right, so we're going to have a little, here it shows a little effect of a black hole, for instance, on a star.
There you go, yeah. Now you
what do we see happening here?
Light doesn't come out of it, but you can see what it does to things that has a dramatic effect on anything that gets near to it. And so we can infer their existence without actually seeing light coming out of it.
So that was a star falling into a black hole. What would it be like in the classical picture? We'll come back to the subtleties of this in just a little bit. But if you were to fall into a black hole, take us through your experience.
Well, what would happen? I would once I would pass.
You experienced it with me, right? No way.
Help me, Brian! But
help me, Brian!
My message would never get outside of the black hole.
But tell us what would happen if you passed the edge. Anything special there? In fact, would you even know that you'd cross the edge?
If it were a big enough black hole,
what does Brian mean? No
smooth
shit.
on the surface. According to Einstein's equivalence principle,
what? Brian is a...
Nothing would happen. You might not even know that you were falling in. But once you fell past the surface of the black hole, which is called the event horizon, you and any message you might send would be doomed to stay forever inside the black hole.
Right.
And not only would you stay inside the black hole, but you would be inexorably pushed towards what's called a singularity at the middle of the black hole. And when you got to the singularity, you would be ripped to shreds.
So, thank you.
What? So, Steve, you want to get annihilated? You want to get roasted?
My understanding is that Einstein rejected black holes largely because of the singularity. That he didn't think that. So, is that...
Is Einstein untouchable?
Like the idea
is he being singular?
There would be a singular solution. And he hoped they would not actually exist in nature.
That's not in our human nature to genuinely...
We didn't really know that they existed because there's a solution of Einstein's equations corresponding to a black hole, because that collapse might never actually have occurred. There might be some instability which prevents
with you guys
the actual formation of black holes. I have to admit that I'm one of those bad people who...
Sorry, buddy. Hey, Stephen.
Before black holes became well established, hoped they wouldn't exist. And, well, they do. There's no question.
Right, no way. Hey, buddy.
Active galactic nuclei, including one at the center of our own galaxy, are pretty clearly powered by black holes.
Yeah.
And what can you do about it?
Sorry.
We can look at it.
So before we move on, Samir, just there's an interesting feature of black holes that we're going to need in just a little while when we get there, in terms of how black holes can differ from one another. It's called the no-hair theorem. Can you tell us what that is and what it means for black holes?
Yeah, this actually later on became the crux of all the puzzles we had with black holes, including all the puzzles that Stephen Hawking found. A black hole, as we just saw, sucks everything in. So somebody's falling in, he just falls in, but nothing can really hover around the edge. Everything just gets sucked in. And that has an immediate consequence. If everything falls in, the black hole just settles down to a situation where everything is just a vacuum around it. it becomes completely spherically symmetric because even a distortion can be thought of
I'm in
as
a quantum
wave,
vacuum
but
called
even that wave would
Earth,
fall in.
buddy.
So the black hole ends up becoming completely round with no features, and so two black holes of the same mass look completely alike. And so there is no way to tell one black hole from another as long as they have the same mass. Because there are no features on the surface, John Wheeler coined the phrase, black holes have no hair. They are completely bald. And as far as the classical theory goes, that's fine. Everything fell in, it's the vacuum, they are bald, and up to here, nothing's wrong with it.
But they do
You
have
are born
three hairs,
again.
right?
Yes, the mass, the charge. Okay. If they have charge,
So they're not
they would have a
completely
net
bald.
charge. And if they were rotating, they would have that rotation. But they're what are called conserved quantum numbers, things which are just conserved quantities. As long as those are same between two black holes, you can't actually do something to change the features of the black hole.
Great. So we're going to actually come back to what quantum mechanics says and how it makes the story much more subtle than the one that we've spoken about so far. But before we do that, I want to talk about another frontier of general relativity, which is the subject of gravitational radiation, gravitational waves. And that's something that you are an expert on.
What did we just leave
Gabriella.
off
So
on?
let's just start at the beginning. What is a gravitational wave?
Okay.
This is another prediction of Einstein's theory that I think he didn't dislike, but he didn't quite believe in the beginning.
Believe?
If you,
I don't believe in believing.
If you do the math for very weak fields away from masses,
Superposition.
you find a wave equation, and that wave is the space-time. So space-time can have waves, and in fact, you can also do the math and realize that those waves are produced by masses that are dynamic, that are moving around each other.
These are ripples in the fabric of space itself.
Right, and they travel at the speed of light, and they travel away from masses, and they carry energy away. So if you have two masses, Newton's theory says that they are going to rotate like the Earth around the Sun forever. But Einstein says that this motion is going to produce these waves that are going to carry energy away, and the masses are going to get closer and closer together.
Right,
so
yeah,
that's
you
a
guys get closer
very
and closer
different
together.
prediction.
This is going
Einstein actually, I heard the story, but I haven't seen the papers, that Einstein calculated these effects in the very beginning, and he saw that they would be so small for any masses that he thought they were irrelevant.
But is it that? Again, I don't know the history of this. I'm in terrain I don't know. But I had thought it was that he thought that they were not real, that they were a coordinate artifact. Is that wrong?
He wasn't sure in the beginning, and then when people began looking at this, they convinced themselves that they weren't real, that they were coordinate effects. Space-time, it's all about describing it using math and coordinates. And it took 40 years. It was only in the late 50s that people realized that there was energy associated with the space-time motion.
That's
and it
ridiculous.
could be measured. Gravitational waves. My favorite way, the one I work on,
is
using lasers to travel back and forth between mirrors and measuring the time they take.
So what are we seeing right here first before we...
We are seeing the laser traveling in those beam tubes, which are vacuum systems. They travel 1.5 miles away.
And where is this?
And back. That one is in Livingston. This is a LIGO detector in Livingston. There's another one in Washington, Louisiana, and they are called interferometers because we measure the interference of these laser beams that are measuring the ripples of space-time on Earth. But those ripples are produced by black holes being born of these stars colliding with each other far, far away, away from our
it's okay, we
ripples
collide.
Are traveling through space, get to Earth, and they're stretching that thing that we just saw.
Gabrielle and Robert, we stretching it. It's thin.
Far away.
So a wave is going to come by now?
Yep.
We have
Sorry, guys.
a laser, a beam splitter, and then the space-time is stretched, and we measure the stretching and the squeezing with a photodiode that measures more or less light depending on the phase of the light beams when they come back.
Whether the wave is up or down as they cross each other.
So we use the fact that light is a wave to measure that space-time has waves in there.
So can you show that image again? Can we start there from the front? I mean, how much stretching? The image makes it
weed
seem
has
like
nothing to do with this. Buddy.
That's what Einstein was right, actually.
Yes.
If we
Einstein is right. He smoked weed,
two
probably.
neutron stars forming a black hole.
I have no idea. I would love to know.
That happens in our galaxy about once per 10,000 years. So let's go a bit farther in the Virgo cluster.
Right.
The gravitational waves produced on Earth would stretch the distance between the sun and the Earth by 1 atomic diameter.
1 atomic diameter.
And the distance between the two mirrors we have 4 kilometers away by a part in 1,000 of a proton diameter. And we have measured such fluctuations.
Now, how in the world can you do that?
You just blew
Very
my mind.
carefully.
Right. But at the same time,
we have not detected gravitational waves, but we have achieved that precision.
And you do it by, you amplify the signal by having the laser light go back and forth many times.
We do lots and lots of different tricks. We have to isolate the universe from the motion of the Earth. We have to make sure that even though they're at room temperature, we are not sensitive to their thermal motion. We make sure that the light is in a very, very pure state, and we are actually fighting at this time the quantum noise in the laser light. That's one of the limits in our precision.
Now, how do you know if you see something, someone didn't just drop a glass of water nearby and shake the ground a little bit, and that's what the cause of it is?
We do it because we look for coincidences. We have 2 detectors in the US, and actually there's another detector in Italy that we collaborate with. And if the signal is from astrophysical origin, then it will appear in several detectors, not exactly at the same time, because the gravitational wave travels at the speed of light, but within tens of milliseconds.
What are you talking about? Are you trying to map me right now?
The 2 US detectors. So by
the 2 US detectors is like the good side and the bad side. Is this what a resource really is?
Astrophysical origin or not.
That all sounds good, but you've not found anything, right?
We have not found anything
No,
yet.
you haven't. I'm still a black hole.
I told you that we achieved that precision of a part in 1,000 of a proton diameter that would let us see a coalescence in the Virgo cluster.
Coalescence, I'm still here for the overall video.
100 years. So we took data for several years. We didn't see anything, but that was a proof of principle of the technology. And now we have build detectors that are 10 times better. So
build
we can see
detectors?
10 times farther, a volume 1,000 times larger, and we are still tuning it, and that takes years. These tunings take years. But when we get to that sensitivity, as we get to that sensitivity, we expect to see tens of events per year.
So this is now the 8th World Science Festival. In which World Science Festival will you come back?
Me?
Predictions about the future are difficult.
Yes.
I want to come to the next one, 2025 maybe.
Yeah, a few other things too. Now you have some audio that you would like to play. Tell us what it is first, and then we'll hear it.
Well, we were saying that our prime target, but not the only one, is these 2 neutron stars that get closer and closer together.
You guys and me.
The gravitational waves that they produce have frequencies that we could hear, if they were audio frequencies. Of course, they're not audio; they are vibrations of space-time.
And
but
yes, they're like describable by properties.
If we heard a gravitational wave of astrophysical origin, it would sound like a chirp, because it's a frequency higher and higher with higher and higher amplitude.
Loaded. That's lit.
This is a pure gravitational wave. Now you would not get so lucky, presumably, and that's why you have another 5.
Wow.
That's what we would hear if our detector had no noise.
Right.
But we always have something in there moving.
No way.
Which is not the distance fluctuation, but it's the mirrors moving, the laser, quantum fluctuations. So that's what a very, very loud signal would look like, sound like in the noise. We would have to be very, very lucky to hear that. That would be a signal not far from our galaxy. So we actually have to dig a lot deeper to look for those.
So I'm giving you a signal from my black hole.
You anticipate 5 years or 50 years? Is there?
I think it's going to be less than 5 years.
I think I would hope so, yo. Come get me up here.
Going to,
how am I not available to do this now?
The detectors are installed. They are at a sensitivity that were
detectors?
3 times better than they were before, and we want 10 times better. So we are already 3 times better. We'll take some data today to rule out some theories.
I don't have to smoke weed up there, but if I could, that's dope.
The universe is full of small black holes that are colliding all the time.
Sorry.
Right.
I mean, no. And respectfully, I didn't just join this
we could detect things very soon. I don't think that's the case. But from this year on, every year we'll be taking data with better sensitivity.
Right.
So I think the expectation is that in 4 years we would get to the sensitivity that allows us to see tens of signals per year. I think we will see the first signals before then.
So the 13th World Science Festival, we were going to book you for. All right. Now let's move on to the last chapter, which is the most difficult to describe, but in many ways the most interesting because for the most part, quantum mechanics hasn't played a vital part in much of what we've discussed so far. It's been mentioned here and there. But the real interesting puzzles happen when you try, as Steve mentioned, to put quantum mechanics and general relativity together. And black holes are a great place, a laboratory, if you will, to start to see some of the puzzles and some of the problems and some of the possible
Why do we keep doing this?
So let's
as people, in a way. It's one of the combos I'd bring up.
So Stephen Hawking is thinking about black holes.
Oh, snot. I'm sorry. I can't be giving you guys the cheat codes, but nah. Talk to me.
What does he find? And most of you know this from having seen the Theory of Everything. It was in that film. Now we're just going to go a little bit more deep than what you saw there.
Yes, it's very interesting. What we normally think of as the vacuum.
Hey, Samir.
You might think a vacuum is just empty. There's nothing there.
No.
And in classical mechanics, okay, that is true. But in quantum theory, as you know, everything always fluctuates because of quantum fluctuations.
Yeah.
So in fact, a vacuum is not really empty. It's actually fluctuating with a lot of stuff all over the place, all the time. And we don't notice that because all that just factors out in the definition of what the vacuum is. So with all those fluctuations, whatever you get, well, that's what we call the vacuum. And anything over and above that would be real stuff, like you and me. But it turns out when you come near a black hole, this vacuum actually becomes unstable. So if there were fluctuations going on in the vacuum, normally they would just come and go. But in the gravitational field of a black hole, the vacuum becomes unstable and these fluctuations start actually producing particles. So a fluctuation would normally be such, maybe an electron and positron could be spontaneously created.
I'd be reacting the same next to you, buddy.
Because they cost some energy, and by the uncertainty principle, if you have some
cost of energy,
it can only live for some time. That's the fluctuation.
So those particles fly away. They appear as...
So now the gravitational field of the hole, they're still created by quantum fluctuations, but before they can re-annihilate, the field of the black hole pulls them apart.
I do,
and one particle falls in the hole, but one manages to escape.
One gets you to me, one gets you to him.
Black hole, and this is what Stephen Hawking found, somewhat to his own surprise in 1974, that black holes are actually very gently and very slowly. But because of quantum reasons, they are always emitting something.
And as the black hole gets smaller, because it's sending stuff out, what happens to the strength of the radiation?
So
I could forget
stronger and
then continue the black hole.
It's just a matter of scales. A black hole has just one scale.
How do I scale things?
So if you ask what's the wavelength of the radiation it emits, it's the same as the size of the black hole. And now that's very interesting. As the hole gets smaller and smaller, the wavelength emitted is also getting smaller and smaller, which, as you know, means it has higher and higher energy. So it's going to end up in an explosive thing at the end. It's going to sort of just squeak off to an end. Well, you can see it happening there.
So in short, black holes are not fully black when you take quantum mechanics into account. Now this, I mean, I wasn't around at the time. Must have been a huge shock.
Why do you, it's color,
shock to you?
Does it have color? Does it have color?
Yes. At that point,
properties?
I was still hoping black holes didn't exist.
Do they have color properties?
Which
I'm sorry.
would have had the tremendous merit that I wouldn't have had
nice tie, though.
Hawking's theory. I'm I'm afraid I
So,
it was a shock.
yeah.
Brian,
You-
what up?
You discussed some of the microphysics behind the emission of that radiation. It's a subtle idea. Take us through it again, and we do have some images to show it. So pair production you're describing. So if you
Yep.
look here, what's happening here?
So the vacuum, as we said, has all kinds of fluctuations in it. And what form do the fluctuations take? Well, you can have an electron and a positron pop out from the vacuum.
Right, it
but
just gets
would
me
have to
so
probably annihilate
excited.
back again.
There's so many
But as you might
fluctuations.
see here, if you have the gravitational field of a hole, these guys pop out, but they get pulled apart.
You kind of have
And
to
as
know
they
they're
get pulled apart,
fluctuating.
They don't get a chance to annihilate again.
You have
and
to
now
know
they
what we
little
are.
Particles, and the vacuum has been unstable, and something has really come out of it.
No,
And that process we're showing
well-
at one location, but the next one will show this could happen anywhere.
neutrino
along
is a
the
good
It
word.
happens all over the place around the horizon
Yep,
of the black hole.
exactly.
It's the black
A
hole
word.
decaying
It's a
from,
word.
from all around it.
And all the stuff that rushes away is the radiation that would come out.
Yep.
The stuff that falls in, what's its impact on the black hole?
So it's very interesting. If you're inside the black hole,
Yep.
that particle actually has negative energy.
Yep.
And you might ask, how can anything have negative energy? I mean, don't you always think of energy as being positive?
No.
But that's exactly where the miracle of gravity is.
'Cause once you know,
so
you know.
Einstein taught us the energy of anything is mc square, and that's positive.
What?
But you know the potential energy term for gravity?
What is he-
We had that formula up there. It's minus gm over r.
Yeah.
That minus sign is what triggers everything.
Right.
Because if you take the total
I
energy
just
of the
triggered it.
particle, it's mc squared, but minus gm over r.
MC.
So as the R becomes
I'm an
smaller,
MC, EMC.
at some point the negative energy can
Yeah.
overwhelm the positive part, and the particle which is inside, but that's what defines a black hole.
Hmm.
The negative gravitational potential overwhelms the mc square, and so the particle that goes inside has net negative energy.
And what does that do to the
A
black
net
hole?
So the
negative
black hole
energy.
becomes smaller and smaller, and the black hole is going to vanish, and this particles go out, carry out all the energy.
So even though the black
'Cause
hole's
I
eating
physically
all
die.
of those pairs of the pair that fell in, the member of the pair that fell
Hey,
in,
guys.
it's actually getting smaller.
I'm
And
a
it's like
hologram right
great
now, though.
diet food. You eat this and you just get, skinnier and skinnier as you eat this. There could be some people in Texas
Skinnier
who would invest in
and
that. I
skinnier.
observe it.
Wow.
So that's exactly the magic. If you didn't have
Wow.
gravity, you couldn't imagine that you had the black hole, you added something, all these guys that fell in, and you still
Wow.
get something which is getting smaller. But that's where the magic of gravity is, because the gravitational energy has a negative sign. You can actually put
Yeah.
on stuff, but if you put it close enough, the net energy can be brought down to 0. And that's where all the puzzles are going to come from.
You just got me
So
close.
you have this radiation, this Hawking radiation that's coming out,
Yep.
which means the black hole is glowing,
Yeah.
in a sense. And
Right
it's
here.
glowing means it has a temperature.
Yep.
And one of the things that
I'm
we
alive.
all learn as undergraduates in
Whoa.
physics, and if you haven't, you're sort of
Temperature.
familiar with this in some cultural way too.
Yeah.
When something has a temperature, it also has
I have a heart and a mind.
something called entropy. A certain
Whoa.
amount of disorder associated with the thermal motion that comes from the fact that
Yes.
there is.
You haven't come to terms
So
with it?
Hawking's result actually jived very well with an earlier result
You believe in God?
of this fella over here, Jacob Bekenstein. Tell us a little
Jacob
bit about
Bekenstein.
what he found.
Yes, so Bekenstein had this interesting idea that black holes also should have an entropy. So
Which we can say is roughly some amount of disorder associated.
Did I really
So
go
entropy
through
is
this
normally
already?
disorder. So if you have a gas in a box, the amount of disorder in it is the entropy in the box. Now for a black hole, this looked very funny. So many people were not believing what Bekenstein was saying, because as we said, in a
Okay.
black hole, there's nothing to see. It's
Is he still
actually
alive?
so orderly. Everything fell in, and
Oh, he
here
died
you have
August
exactly
16th.
round, empty space.
Wow.
You can't see any disorder.
He
But
died.
there was a simple argument he used to show that nevertheless a black hole must have entropy.
You know, how that argument goes? Second law of thermodynamics.
That was the
type
second
of-
law of thermodynamics. Because second law of thermodynamics tells us
Whoa.
that entropy can only rise in the universe. So suppose you
So
take
that
a
guy's
box of
dead
gas
now.
and you throw it into the black
We're
hole.
talking about
Or
this guy
if
when
it's
he's
even a box
before
of
he's
gas,
dead.
let's say a wallet. Same idea,
Take-
right?
take the
There's a
wallet.
lot of
Wallet.
disorder in there.
Right, yeah,
And
sorry
then the wallet
guys.
goes into the black hole and it disappears.
No way.
The wallet had some entropy and now it's gone. So
Yeah.
you have to jump up and say, I have violated the second law of thermodynamics.
You
But
have
people love that law. Nobody wants to give up the second law of thermodynamics. So is there a way to save it? Well, normally if you throw a wallet into a trash can, you can't say, I've decreased the entropy of the universe. The entropy of the trash can has gone up. So here the entropy of the black hole ought to have gone up.
Yeah.
Has the black hole changed in any way? But only one thing you can see, it's become larger. And what Bekenstein noticed was that if you want to save the second law of thermodynamics, you have to attribute to the black hole an entropy, even though you can't see where it's coming from, but you have to attribute it an entropy, which has a very funny expression.
Predicts?
Instead of being proportional to the volume inside the black hole, it was proportional to the area.
In fact, we have a little clip here that would just give a sense of
that I can predict.
How that notion
God
of the
can,
entropy
though,
being associated
just
with
do
the area
things.
might manifest itself. In some sense, there's data on the surface of the black hole that knows about the wallet.
Have
that
you
went
not?
in.
Oh my
And
goodness.
the formula that you're
Shit
talking
can
about,
come out of
just
nowhere.
two listeners, is this thing over here.
Sorry.
The entropy, as you say, is proportional
Yep.
to the area instead of the volume. Now, why?
Right, the
why
air
is that
instead
weird?
of the volume, right.
Yes, that's weird.
It's
weird
about
for
the
a
air
couple
I'm
of
saying,
reasons.
not the volume
The
of what I'm
first is just the
saying.
magnitude of this answer. You see all those H
See,
bars,
it's not about like how I
H bar is a very
project the
small number in
energies.
quantum
That's a
guys.
quantum mechanical
It's
number
very
called
quantum-
Planck's constant.
Called Planck's constant.
Whoa.
So if you look at the magnitude of this entropy, it's much larger than the entropy of any
Philosopher
normal
Chris
matter of the
Payne.
same mass. So whatever this thing is trying to measure the disorder of, it's not ordinary matter. It has to be something new, something
Yes.
maybe coming from quantum gravity.
Yeah,
But the other issue was that normally entropy is always proportional to the bulk volume. And here it's coming out to be proportional to the area of a surface. So where does the stuff live in a black hole?
The surface of
Does
Earth?
it live
Yeah.
inside the volume? Well, it was empty space. Does it live on the surface? But actually there was nothing there either. Where was the stuff? It all went down to the center. And the entropy is coming
The black
not from
hole?
the value of a point or from the volume, but from the surface.
Right.
And some of the deepest puzzles of black holes that we are still struggling to understand is why is that?
Now,
Why?
Andy and Qumran, both
Is that
of you
because I'm
had an
here? I am a
enormously
black
important
hole.
contribution
I'm
to
philosopher
this
Chris
puzzle
Payne.
in trying to explain the entropy of black holes. Many people view your joint paper as one of the most important contributions of string theory
He
to
smoked
our
the joint
understanding
and
of a
wrote a
pre-existing
paper?
puzzle, giving us insight into it. So I want to give you both.
I
a
mean,
chance
maybe
to
these guys are
describe
like they're
your
men.
work in
Like
that regard.
they probably
But we should
drank.
say a couple words about
alcohol.
string theory first. So
Okay.
either one of you just want to take us through the very
Like,
basic
these guys
idea of
are
string theory?
Men.
Duke it out, choose it up, flip a coin.
Gabrielle, help
So
me.
string theory is a theory which tries to unify. That was not the way it was originally formulated,
Try
but
to
that's the way
unify.
we understand it today.
I just thought it was funny. She was the only
Unifies
guy.
quantum
Or
theory
the only
with
girl.
Einstein's theory of general relativity. So it's a framework to talk about quantum gravity. And
Quantum
in
gravity.
doing so it needs to replace the
Again?
concept that elementary particles are point-like by extended objects.
How do they
in
still have
particular
this?
By strings and
Right.
other extended dimensional objects
Okay.
like membranes and so on. So string theory, for
Strings and
example,
membranes,
would say
right.
that
So you guys just
think
literally-
about quarks inside if I understand, these are quarks.
Yes, yep.
Yes,
Okay,
inside
quarks,
the
anti-quarks.
nuclei, you would, if you go further closer to them, you will find
Yep.
they're actually not point-like, but
Right.
perhaps loop-like, like a string, or membrane-like. So these are these extended objects, and perhaps they are vibrating, and their degrees
Right.
of freedom are somehow, they could have lots of different possible degrees of freedom. But that
Degrees of
apparently,
freedom?
existence of this extended
Asymptotic
structure
freedom?
is something that is needed to try to resolve the paradoxes involving quantum theory and combination of quantum theory with Einstein's theory of relativity. So that was the
Theory of relativity,
the way
what?
that we understand the
You
importance
sleep?
of string theory today in trying to resolve a paradox.
Do you
between
sleep? Do you
pillars
fall
of physics.
asleep? Do you
And
have
then what did
dreams?
you guys do with these new ingredients in string theory? How did you
Oh
fit
no,
into
I don't
black
mean to
holes
string
and
you
their
guys on
energy
this.
outputs?
Sorry.
This is their joint work, so I don't know who to look at to answer
Look
this
at me,
question.
philosopher Chris Payne. It's not a joint
Well,
work,
of
it's
course,
me,
we
man.
don't know if
You
string
can't hold
theory
that against me,
describes the
dude. This
world
is,
that we
oh
live
my
in
gosh.
or not.
Why do
But
these
we
professionals
do
still
know
do
that
this?
it's a consistent theory which
It's about the convo.
incorporates quantum mechanics and gravity, and therefore it had better make sense of this puzzle about how information is stored in a black hole. How can this enormous
It better
amount
make
of
sense?
information that
I do.
Bekenstein and Hawking told us must be stored inside of
Stephen
a black
Hawking,
hole.
did he
How
interact
can
with
you store
anybody?
information in empty space? And if string theory, which purports to
He
be a theory
interacted with
which
people, but he
consistently
typed to people. Interesting.
incorporates
Holy
both
shit.
quantum mechanics and gravity, didn't give the right answer to that question,
Stephen
string
Hawking
theory
literally.
be wrong. We would stop working on it. On the other hand, if it did give an answer, it would perhaps give us some clues that would be more general than their stringy origins. And indeed, in string theory, because it's so mathematically precise, we have many tools available to analyze this problem in different points of view that we can look at it from. And we were able to describe the black hole from a different starting point,
philosopher Chris Payne,
which fully incorporated all its quantum properties.
Yep, thank you. Just to
when
clear
we did that, and we did exactly what Stephen
I feel like I've been
said
being watched.
at the beginning of the lecture, we had some equations, and we just ground through them and followed them to the end.
Right.
And we found that according to string theory, the amount of information inside a black hole was exactly what Bekenstein and Hawking predicted.
I have a little cartoon. I don't know how helpful it is just to give a sense of what you did.
A cartoon?
So this is meant to be your strings and brain configuration. Maybe take it.
So what's being illustrated here is that we can describe space-time itself in a different way using string theory.
The white in the middle.
Space-time emerges out of strings and other more exotic object called brains, which we can understand in a mathematically very precise way.
Right.
And it was by using this other description that we were actually able to count exactly how much stuff there is inside of a black hole.
Part of it actually was an interesting twist. Namely, string theory had a problem with reality. It predicted the dimension of the space being more than 3. And that sounded manifestly false against the experimental observation. Without much experiment, we know we don't live in more than 3 large spatial dimensions. And string theory resolved this problem by postulating that these extra dimensions are too tiny to see. So string theorists were making these postulates, and physicists were getting more and more uncomfortable because it sounded like you're hiding something by making them small and making them disappear instead of using them for something. On the other hand, there was this other problem that Bekenstein and Hawking had been predicting, that there is this entropy of this black hole, and there was a missing. So they was looking for where are these ingredients of black hole. In the context of the work we did with Andy, we found a way that these ingredients were actually hidden in the extra dimensions of string theory. So the extra dimension of string theory came to the rescue to solve the problem that Bekenstein and Hawking had with accounting for the entropy. So a problem of string theory became its triumphant victory.
So like when it came out that the answer was the formula that was 25 years old, that you'd finally explained, like what'd you do, like high five or something? I mean, what do you do at a moment like that?
No, man.
Man hug or something?
No, dude. I literally kept it to myself, man, honestly.
That's between you guys, yeah.
Yeah, I'm still a black hole, dude.
So in the final
holy cow.
time that we have left, I want to turn to another big puzzle. Black holes, which is tightly related to what we're talking about, which is often called the information paradox, the information puzzle. And we've sort of touched on it a little bit, but now I just want to go a little bit further in so we can look at the frontier of ideas that people are kicking around right now and see what that might hold for the future. So, Samir, can you take us back a little bit to this information puzzle? Explain what this little picture is meant to indicate, why that's a puzzle, and we can then go from there.
Yeah, so suppose you take this wallet, which is there in the picture, and the wallet, of course, has some information. It tells you, like, which kind of bills you had in it. And now you toss it into the black hole, and it disappears, goes to the center, presumably get distorted to singularity, but we know that radiation comes out. So when the black hole is gone, your energy is conserved, so you're happy, energy conservation has not been violated. But something very bad has happened in the process. The radiation which came out, we saw it came out by the tearing apart of the vacuum. It really came out because
tearing apart of the vacuum
produced some particle pairs, and those particle pairs that got separated. So whatever came out of the vacuum.
Isn't that what you guys do to research?
Because it came out of the vacuum, it had no information about what was in the wallet.
In science?
So in the end, you got all your energy back, but you lost all the information which was in the wallet.
Whoa.
And that's actually very bad because never before in physics, either in classical mechanics or in quantum mechanics, we have actually had that situation.
Wow.
If you take any initial state, even in quantum mechanics,
Right.
you can evolve it forward by Schrödinger's equation to a final state,
Right.
but you can also reverse the evolution to recover which initial state you came from.
Right.
But in this case, because the information went down to the origin, the singularity,
Right.
and the energy came out from somewhere else, the
Yeah.
horizon, and these could be miles apart.
Huh.
It came out of the vacuum, really.
Horizon,
We lost
the
the
vacuum.
information.
So if I burn a book, right? People think information's gone, but you're saying if I'm actually
Are there
very
copies of the
careful
book?
about it, it's not.
Exactly. When a normal body burns,
Whoa.
the atoms in the body, they are the ones that actually are the ones that go out as radiation. So in fact, you could always trace back and
A
say,
death.
if the body had the atoms in one position, the radiation would look like this. If the atoms were in this position, the radiation would look like this. It would be difficult to do, but you can always do it.
So when you burn those love letters and you think they're gone, Samir could be there recreating them. But if you threw them into a black hole, according to the conventional picture, the information potentially might be gone, but that would wreak havoc on physics. So that's the puzzle.
That's right. So Hawking came back at this point and said, look, no theory of the black hole can ever respect quantum mechanics. I don't even care what the theory is. of
I
quantum
respect
gravity,
it to the utmost
but
level
if
that I
you
am the
can't ever
superposition
recover
to you guys.
The
I'm
information which you
a black
had
hole.
at
I'm
a later
philosopher
stage,
Chris Payne.
It can't be any quantum mechanical evolution. Maybe we should give up quantum mechanics.
So since we're going toward the end and we're going to spill over with just a couple minutes,
Whoa.
I'm going to be cavalier and we're going to push to a little
21
further
minutes left,
detail on
just
that
in case you
puzzle
know.
in order that the solutions that you're going to describe have a little bit more architecture under them. So if you can take us through
Right.
this notion of quantum entanglement and its relationship to the puzzles that you're talking about. So what we're looking
The
at
internet
here is
controlled, or is it
two
quantum
entangled
entangled?
particles. Tell us what we're looking at in
So
more
this
detail.
is actually the crux of the technical reason why Hawking found this enormous problem.
Is this in the
When
black
these
hole?
particles came out from the vacuum and they became separated, these particles are
Oh,
in a
no.
state which is called entangled. And here's a good
Right.
picture of the entangled
No
state.
way, I'm
if you
entangling
take two spins, you
it
could
to
take
you.
this particle to have spin up
It's you guys
and this
talking,
to
you
have spin
talking,
down.
that one down,
but you
up,
could
down.
superpose to that the
No way.
possibility that this one is spin down and that is spin up. We get this thing in quantum mechanics all the time.
Right.
But look
All
at the
the
funny
time.
situation. This particle doesn't have a state by itself. It is up if this guy is down,
Mm-hmm.
and it is down if that guy is up. So it's a conditional state. And
Yes.
there's nothing wrong with that. In fact, every time I clap my hands, because the interaction between my hands, the states of the atoms here and here get entangled. And that's fine. Now the problem would come if this hand disappeared from the universe.
Oh,
So let's see a picture of that. So if we can go on to the next one. So here you've got exactly what you're talking about. Take us there.
That's right. If
Right.
this keeps happening, now from
Yeah.
they're entangled, and nothing wrong with it at this stage, but
We're
more
here.
of this will happen.
Yep.
it's a yellow line.
So
I'm
we
yellow.
can now go on
My
to the
favorite
next one.
color is
A lot
yellow.
of these things happening all
Oh,
over
wow.
the edge of a black hole.
And
So
then
it
it's,
happens again, and the black hole
so
is
is
getting
blue
smaller.
coming out because I'm policing them,
There's a
like
lot of this
knowing me.
entanglement going on
My
between what is
spirit.
out there and what is in here.
And me
But just notice
on
the
this.
particles outside
And my eye
don't
is
have a
right
state by
there.
themselves. It's the conditional state.
I'm
they
the
will
black
be spin
hole.
up if their partner was spin down, and they are spin down if
Wow.
that is spin up,
Okay.
and up to here still okay.
Yep.
But now at the last stage, the black hole goes away.
Yeah.
And now
Because it's
the guy
getting
that-
smaller and smaller
Smaller.
as the negative mass particles are
As
forming.
negative mass
As I
particles
like
go
this,
in, energy
in a
has
way.
to be conserved. If the black hole went away, the particles outside left with no state at all. Because they had a conditional state, but whatever the other partner of that conditional state is gone, and that's why Hawking said, now I'm left with something which has no state. I can only
Yes.
describe it by what's called a density matrix, just statistical. It's not really quantum mechanics anymore, and so quantum mechanics has been violated.
So the bottom line is he was saying then that black holes, when they talk to quantum mechanics, may break quantum mechanics. Now, people are not so willing to give
Oh.
up quantum mechanics, and
No,
have
we
fought
just
back
never even
with
defined
possible
things
resolutions
to
this
begin with
puzzle.
and agreed
I
on
just
it.
want to quickly
I've
go
been
through
places.
some of them
This is the
just
whole
to give
world.
a sense of the
We
state
all
of
live on
play
this
at the
planet,
moment.
Earth.
So one possibility
Sorry.
is called remnants.
What's remnants?
Andy, a couple words on what that might be, that solution?
Well, the idea would be if you throw your love letters into the trash can, you want them back, you can go dig into the trash can and take it out. Trash can gets smaller and smaller.
Trash
that's
can?
okay. They
Right.
get compacted in there. It's okay as long as the trash can doesn't disappear completely.
The love letters?
So what happens
in
in
the
the black
trash
hole
can?
evaporation, according to Hawking,
Whoa.
is that the black hole
So
gets
I'm pulling you
smaller
in
and
'cause-
smaller.
whoa.
You can't get out what's in there. but all the information,
Whoa.
Samir's left hand, the left hands of all the electrons that came in are still in there. It's just crunched into a tiny place. And then according to Hawking, it will just disappear. The remnant proposal, which has many problems and almost no advocates,
RuneScape.
is that the
A
black
member,
hole
no way.
actually,
So I have to be
Hawking's
a member or
equation,
something.
and he would agree with this, is not quite valid when
RuneScape?
the black hole gets very small, it breaks down.
Right.
So it's a logical possibility
RuneScape
that the
is
black hole just gets very small.
powering the
and by that I
Venezuelan
mean 10 to
country.
the minus
It's sad.
33 centimeters, and stops.
Yep,
And all
I
the
heard 3.
information that went into it is forever in this tiny little remnant.
Yep.
Now, just quickly, I mean, string
it
theorists,
okay?
people who come from the quantum mechanical side, I think, do agree that the
String
remnant
theorists.
picture doesn't feel satisfactory. But in the
Who? I'm
relativity
young.
community, would you also say that there are no remnant supporters?
I think the
I
relativity.
don't know any remnant supporters.
I do.
I
know
think there are two
friends that play
people in the world
RuneScape
who
with me.
think that, I counted them the other day, Hawking is not one of them. There are two people who think that information is destroyed. I don't know of any remnant advocate.
Do you? Is that your experience?
But people argue that the remnant, the whole issue is how can you hide something, information, something so small, but they believe it could be the mouth of a baby universe, which is hiding a lot of stuff in it, and the mouth looks small, and that's what we see as the remnant from our side. So I've heard that from several people.
Wow.
So, I mean, this shows how
Wow.
confused, the fact that we are so coming up with
Please
such
help
a
describe
desperate
me. I'd
solution
love to hear. Yeah.
shows every proposal is, we know that there's a problem,
Robert.
and
What's this
there-
guy's name? I forgot.
there are some proposals,
Andrew.
and they're all crazy in some way or another.
Right.
Am
But
I?
here-
No.
But one of them must be right.
That's right. Or we haven't
No.
thought of it yet. That's
No,
right.
what?
And one of the other things that
guys
was an interesting
haven't,
development in this whole story was
I-
spearheaded by kind of an offshoot of the work of this fella here, Juan Maldacena, who wrote a very famous paper in string theory in the late 1990s, which, just to move things along quickly here, showed that in certain circumstances, you could re-describe a black hole in a language that didn't make use of all of the general relativity technology that seems to be causing the problem. You can use language of
What's the
ordinary
problem?
quantum field theory, as we call it, and that seemed to suggest to people at
We
the
all
time
have the same problems.
that this puzzle was, at least in principle, resolved. Because once you don't have to use general
Yes.
relativity in
No,
a
I
description,
don't.
then we're back to ordinary physics and quantum mechanics that we understand.
That's
Many
how I'm
people
here.
are no longer
That's why I'm
convinced
interested,
that that
because I'm a
application
black
of this
hole.
idea is as clear cut.
Humans thrive off
Samir,
contradiction.
You want to say a couple
Not-
words about that and your role?
Contradiction is guidance.
So what happened here was that Maldacena found this great way of recasting, as Brian just said, gravity
Philosopher Chris
using
Payne.
variables which actually didn't involve any gravity, but just used ordinary field theory. And ordinary field theory, we have no problems. So it seemed to people there must really be no problems with black holes. So then, what was the solution of the Hawking puzzle? And so it seemed to be a plausible possibility that there were small subtle corrections to Hawking's calculations which might actually get the information out. So at leading order in the calculation, things just seem to be getting entangled in a certain way, but there can be always subtle extra pieces to the entanglement, which are very small, but the number of particles being radiated are very large. So a small number might cancel a large number, and somehow there might be a delicate encoding of all the information in subleading effects. It turned out under further analysis that that's actually not true. It's not that easy to check because there can be so many different ways of encoding information in so many particles, and of course nobody had specified any of the ways, so somehow you have to check them all out and see that nobody can encode the information. But here there are some very powerful things in
Hi guys, still
quantum
here.
information theory about entanglement entropy. And
Did you
they
guys
came
see
to
that?
the rescue, and with them you can actually prove that in fact you can't really do any subtle encoding.
Nope.
The puzzle is a real puzzle.
Yes.
You really have to change something.
You have to
simply
figure out my mind.
Either at the horizon or about your whole quantum.
And when you say
theory.
they came to the rescue, they came to the
Wow.
rescue showing that the problem was really a problem, that the solution wasn't a solution. So in that way, it just brought it back into the center of attention. Now, some of the other wild ideas, there's
Robert.
one recently that Lenny Susskind and Juan have put forward.
You're the
have to
center
do
of
with
attention for a lot of
wormholes.
stuff, dude. I've
We just
watched
take
you.
a quick
You're a
look
good
at
man.
what that would be. So
We're in a
It's a
wormhole.
fascinating idea. The trouble we had was that these two particles near the horizon, they got created from the vacuum, and then one went away.
Now you're in
You
mine?
have no trouble if that other guy never went away.
Yeah,
But
sorry.
what we mean, we just saw it go away.
No.
But suppose
Oh,
the particle which
interesting.
went away was secretly connected back to the black hole through a wormhole. Then in some sense,
Interesting.
it's still there. So the
Interesting.
particle is both out there but also secretly because space-time is multiply connected also in the black hole.
Secretly?
And then the idea was made into a very
Secret
general
to
one.
who? Do you have
Whenever
to
two
talk
things are
all the time?
entangled, maybe there's a wormhole between them. So somehow we are now really probing what is the structure of space-time. Is space-time
I
really
know, I
coming
can-
from some
oh
kind
my
of theory of
goodness.
entanglement? So if these ideas ever work out, they really go to the heart of what stitches together space-time, points of space-time,
That's a
who is
good
next
question.
to who, who's close to what.
I like this
All those
stuff.
questions have to be answered. Maybe entanglement is the key. And this was part of that.
Is
drive.
the key.
And finally, so a
have you
solution
got
that you have
what?
been advocating for a while. Why don't you just give us a
Sorry.
quick sense of what that is?
So we were actually looking at the kind of states that Strominger and Waffa had, when they counted the entropy, and we tried to see what are the wave functions formed by these guys when you actually go to the domain of coupling that they would actually make black holes. And we found that because there are extra dimensions in this theory, you actually found solutions which have a completely different topology than what had been normally thought of.
Yes.
So the trouble with black holes was
Right here.
you can't put a surface there. If they had a surface, there'd be no problem. You radiate from the surface, just like a planet radiates from its surface. But if you try to put a surface there, as we saw,
Yeah.
everything falls in.
I'm
But in this
philosopher Chris
topology
Payne.
which automatically came up in looking at these states, the surface can just stay there and actually not fall in. In fact, the black hole has no inside. Space comes and sort of pinches off and just ends on that surface in a completely smooth way.
Yeah.
If the states of the black hole all live in
I'm not
this new
gonna
topology,
fight
then we
anybody.
don't
I could
really have a
talk
problem.
about this stuff
So show
all
us what
day,
we're having
guys.
here. This is
I just
your
smoke
fuzzball
weed. I'm not a
picture, which
criminal.
makes
I
use
know
of
you
those
guys are old
ideas.
heads. I'm
So
26.
here, suppose you had something which was coming in and trying to
Beautiful.
make a
Wow. Colorful
black
but
hole.
colorless.
Instead of actually
What if I'm
falling
colorblind?
in,
Sorry,
there's
guys.
a quantum amplitude for it to actually
Viewer
tunnel into this
discretion
other
is
kind of
advised.
state, which has a new topology.
Blue.
And in this new
That's the
topology,
same cover
the
as
space
Kanye
inside
West's
this ball is actually
Jesus is King.
Missing.
Beautiful.
Not there. So the inside of the black hole just is not a place.
It's not a place.
Not
No.
emptiness. It's just not there.
It's just not there. The space
Philosopher
actually
Chris
ends.
Payne.
And so then this is all you have. This is actually a surface. You can compute a radiation from this surface. In simple examples, it behaves just like Hawking's radiation.
Yes,
And then this
I'm
thing
a
would look
walking
like
around
any
black
other
hole,
planet,
sir.
And then there would be no person.
So I think this emphasizes, Andy's basic point. There are a lot of possibilities, interesting ones, with wormholes,
Nope.
fuzzballs, all
Just
these
give me
ideas, but we
bodyguards,
just don't know
dogs
at the
all
moment
around me.
how to really talk about these objects.
I do
black
know
holes,
how.
and maybe in some sense we'll come to the conclusion that they don't really exist.
Black
In
holes.
any conventional sense so we may come back to your wish.
Oh.
Your wish may ultimately
Yeah.
come true.
Let's go.
Now we're actually
Yeah,
out
9
of time,
minutes,
but there is
9
sort of
minutes,
one
the
more
God
question
number.
that I'd
Snap.
like to ask. Well, I'm going to take one because so many
Almost.
questions have come in on
Yeah, it
Twitter.
was. Wow.
Well, here's one. So
9
someone
and a
has
half.
asked, we've used the language, the fabric
So you're half
of
there and I'm half here.
space-time.
Okay.
Is that metaphor, or is space-time in some sense something that's really there, the way fabric is really there? Any takers on that one?
I can. In Einstein's theory, there is there. In modern developments in
and
string
half.
theory, they may not even
Superposition.
be there. So in the context that you mentioned of Juan's work,
Come on,
holography,
guys.
you can actually create a fabric out of nothing.
Come
so
on.
it's a phantom in some sense. So the
Yeah.
question is, what is there, what is not there? Dualities in string theory tell you that you can have different perspectives, and what is really there and what is not really there could have a shady meaning. So it's not quite clear
can
whether
impair
the existence reality.
Your
One of
quality
the
of life,
recent
sir.
Solvay conferences had as a subject,
Well-
is space-time a derived concept? We think of it as fundamental to the stage on which everything is
I can
acted out.
actually help
But
you find
may
it.
be just one of those approximate concepts that arise
You have to enter my black
higher
hole.
order from something much deeper.
You have to enter my black hole, sir.
So much like
With
temperature
Brian.
is a derived concept, fundamentally it's the
That's
motion
the
of
analogy.
particles.
Yes, it's the motion of entering
And so
me.
what's your view on that?
Of what?
Oh, I'm waiting to see.
Okay, right, yeah. I'd love to meet you, sir. The tie.
I'm very skeptical about any statement about what happens at distance scales, that the ones that
How did you get there?
10 to the minus 33 centimeters. I don't think we have
minus 33. Wow,
of
right.
that. I think string theory is
Who's
our
we?
best hope if it existed.
Who's we? Who do you represent?
But there really isn't a string theory. There are a number of approximations.
Oh my goodness.
All seem like they're approximations to some underlying theory whose principles haven't really been stated.
You haven't stated it. Who are you? I wish I did have a
might be the
relationship with
answer
you.
if we had it.
You talk well.
But Einstein was just wrong. The Einstein equations are not that simple.
Maybe I can get to know you.
That were written down that you could put on a T-shirt.
And you talk to him?
They contain an infinite number of terms, and they're all negligible at the scale of the solar system, and they all become crucially important at the scale of 10 to the minus 33 centimeters.
Minus 33.
So are you
I'm right here.
disappointed with where we're at in trying to put gravity and quantum mechanics together?
No,
Disappointed?
I'm frustrated.
What kind of question
rather
is that?
Disappointed because it's so hard to get a handle on this. You know, we talk endlessly about
that's why
black
your body
holes, but we
language, you
don't
talk
see
like
black
that. It makes
holes. All
sense.
we see are the accretion disks around.
I don't know
black
how old you
holes,
are.
and we've become convinced that there are black holes in there, but we can't do experiments
Accretion
or direct
disk.
observations on black holes. The whole thing is just terribly frustrating.
I'm a black hole.
For the time being, I'm much more excited by the experiments that we were hearing about from LIGO, and hoping advanced LIGO goes on the air soon and discovers coalescing neutron stars, something we get our teeth into.
Right.
So, final question. Yeah, go ahead, Andy.
I can't let it end on that note. There is a very exciting experiment now being proposed, the Event Horizon Telescope, where they're going to be coordinating a number of
things
of radio telescopes across the Earth.
Yes.
And they are actually going to be able to image the electromagnetic. They're actually going to be able to image both the supermassive black hole at the center of our galaxy.
Wow.
And
did I just literally turn off
and
this?
the one at M8, the one at the center of M87, and they're actually going to be able to see it. And we'll be able to see it as well as we saw the neutrino.
I look forward to that.
They should be in the next few years.
All right, before we wrap up, one final question just for everybody. And I'm often asked this question, and I hate it. But now I can ask you guys.
And I just
that
turned
makes
off
me
the
happier. So what is the one question that you would love to see answered in your lifetime? Samir.
I would love to know if quantum gravity really acts only at the Planck scale or actually acts on macroscopic scales like all the Blackwell paradoxes are telling us.
Gabrielle?
Okay.
I would love to see a theory of quantum gravity with predictions that we measure.
Really, you need predictions?
Read my mind. No, but what is the fundamental formulation of string theory that Steve alluded to, and the pieces of the puzzle are clear there, but what it really is unclear.
Yes.
I think this question that we were discussing but failing to answer in the last 15 minutes about how information
it was a
gets
question,
in and
actually?
out of a black hole.
Maybe
These
it
are
was a
things that
rhetorical
we
question.
see up in the sky. I'm optimistic that that's a question that we can answer in my lifetime.
Yes.
It's a hard one.
Wow, how old are you?
Well, the question I'd like to answer, I don't think will be answered in our lifetime, even your lifetimes, let alone mine.
Pessimistic.
Is
1 of 4.
What are the laws of nature?
1 of 5.
But more specifically,
1 of 6.
are we
1 of
getting
7.
a good sample
Heaven,
of
I'm
the
7
laws
heaven.
of nature as really fundamental, or is the Big Bang that we see just one tiny part of a much larger universe in which what we call the laws of nature vary from one part to another? I'd like to know the answer to that.
Right.
And I hope the answer is
3 minutes left.
that this idea that the universe is much bigger than just what we see, called the multiverse idea, is wrong, because
Who gave you that idea? When did you bring this up?
although there are suggestions that it might be right, but it would mean that we can calculate much less, just as Kepler was wrong in thinking that we can calculate the distances of the planets from the sun from first principles. We may discover that a lot of the things that we think we can calculate
you can't
from
calculate
first
that
principles
stuff. Think
are just environmental parameters.
Good luck doing that stuff.
That would be very sad, but it may be true.
No, it is environmental parameters.
As you once said in a Nova
thinking,
program of mine, nothing in the laws of
Brian.
nature says that theoretical physicists have to be happy. So
Wow.
thank you all. It's been a fascinating discussion.
Thanks, Brian. Good looks, buddy.
Thank you.
Yeah, thanks. I got you. I'll see you.
Okay.
Gotta pick up some motion. Cool. Yeah. Slide with the stick. Slide with the stick. Slide with the stick, boy. Samosa. How you doing, buddy? I'm picking up the boobies. Too fresh. We're getting wood. Get some wood. Wood. Samosa. Hey. Oh, hey. All right, what's up, guys? Let's do this. January 23rd.
On this edition of Celebrating Science, a special panel discussion about the physics of information. Brought to you by Canada's Perimeter Institute for Theoretical...
Canada. Loose ends. Loose ends. String theory and the quest for the ultimate. I'll just enter this vacuum really quick. Oh, no way. Hey, Brian, you're still there today? Okay, so I'm going to watch this video. You.
For more than a century, physicists have tried to find a unified theory.
I'm
a
a
single
black hole.
mathematical framework capable of describing all of nature's forces.
Philosopher Chris Plain
Albert
is
Einstein,
a black hole.
who unified space and time in his special and general theories of relativity, pursued this goal for over 30 years, never succeeding. Today, scientists are continuing the quest, seeking to combine general relativity, describing the universe on large scale, stars and galaxies, with quantum mechanics, describing the universe on subatomic scales. Each of these two theories works amazingly well in its own domain, but put them together, like in the dense center of a black hole, and the math falls apart.
Right, and then what happens?
In the 1970s, scientists came upon a potential solution, but from an unexpected starting point. Studies of nuclear processes.
In that era, we were trying to
1970s?
understand the strong nuclear force.
John
which is
Schwarz.
the force that holds the nucleus of the atom together. And that was a complete mystery how to do it.
In trying to solve that mystery, physicists were led to a promising equation that seemed to describe vibrating
music,
strings
guitar.
that would hold together atomic constituents.
Right.
But
Audio.
within just a few
Radio
years,
waves.
a different theory proved to be the right solution for understanding the strong nuclear force, and so strings no longer seemed necessary.
Almost all of these several hundred people stopped
Walk
working
with me.
on string theory at that time, and only a handful
Several
of
hundred.
diehards continued to pursue them. The few of us who continued working on string theory felt that the mathematics was so beautiful and compelling that this theory had to be good for something.
Much like Einstein, who
What
spent
theory?
long periods working on ideas outside the mainstream, Schwarz and his colleague Joel Shirk continued to explore string theory.
We realized what string theory was good for, and
Okay.
that was as a quantum
N
theory
equals
of gravity.
8?
At that point, I was convinced that this was what I would be working on for the rest of my career.
K-Pain
Schwarz was
8.0.
proposing that string theory, which had failed as a theory of the strong nuclear force, was actually the solution to one of the biggest problems in all of physics,
Dual model of
uniting
pions?
gravity and quantum mechanics.
So maybe we're
When Schwarz excitedly announced
factorizable
this prospect,
dual
few people paid any attention.
Uni Schwartz right now?
The field just
who-
wasn't ready.
Who are you?
So
Who's
Schwartz
speaking?
and a new convert, Michael
Right.
Green,
Mike Green,
spent
a
years
convert. He
developing
converted
the theory
something what?
mostly on their own. Then, in 1984,
Whoa, okay.
they achieved a breakthrough,
Okay.
showing that the mathematics of string theory
Yang
definitely
Mills
avoided
theory?
potentially lethal technical issues. And this time, the community of physicists heard them.
Princeton, between the university and the Institute for Advanced
Whoa.
Study, you had almost half the experts in the world who were working on related topics. And
Yang Mills theory.
I am told that at that point, almost all of them dropped what they were doing and
Right.
became string theorists.
As string theory rapidly progressed, there was a sense that research
When?
was but a few years away from uncovering the final and unified theory of physics.
Okay.
More than 30 years later,
Yep.
the goal of a fully unified and thoroughly tested theory has yet to be achieved,
Yes.
but enthusiasm remains high.
Okay.
String theory has come closer than any other attempt to go beyond known physics and tackle the grand challenge of unification.
What? String
The
theory?
question
How?
remains, is string theory an elegant mathematical chimera, or are string theorists rapidly approaching the realization of Einstein's dream?
I'm Einstein's dream. Hello, I welcome you tonight. Brian, what up, bro? I'm Einstein's dream. You here?
welcome to tonight's program, which
Breaking the
is
paradigm shift.
focusing upon a really ancient project.
I'm a black
project, as we described in that little segment.
Hey, you look good.
Project of unification. And you can really trace the human urge to try to unify our understanding going all the way back. I mean, Democritus, long time ago, imagined that reality amounted to atoms and the void. That's all that there was. Galileo spoke about the book of nature being written by God in the language of mathematics. That would be the unifying framework, describing things all in terms
Okay.
of the symbols that we use to articulate
Right.
mathematical
Use Galileo,
equations.
use philosophy.
And as in that little piece, and as well as many of you no doubt know, Albert Einstein
Right.
spent 30 years trying to
Right.
unify our understanding of the laws of physics,
And it's me.
but
Wait,
ultimately
30 years
came
when?
up empty-handed. And what we're
30
going
years
to
when?
discuss
He was only
here
30 years
tonight
old?
is the next chapter of that story, a story that is ongoing.
Of what?
And
Einstein?
we're
Why
going
are
to
we still
break
talking about
down
Einstein?
the discussion into 3 conversations.
Okay,
which
3
very
combos. Let's
roughly
go.
speaking, will
Roughly
cover
speaking.
the past, the present, and the future of unification. There will be overlaps, so that way of thinking about things is not completely accurate, but that's the general progression of the evening. So let's get right down to it, and we have a number of guests who are leaders in the field and thinking about these kinds of ideas. And the first guest this evening is a professor of natural philosophy, physics, and astronomy at Dartmouth College. He's a fellow of the American Physical Society and winner of the 2019 Templeton Prize. Please welcome Marcelo Gleiser. So Marcelo, thank you for being here today. And,
Marcel?
when we talk about unification, we know that
Sorry,
throughout
buddy.
history there have been many steps and route
Marcelo
to
Gleisner.
the approach that some of us have been pursuing. In fact, you pursued at one point as well, string theory. And we have a little roadmap that we can bring up.
He did for a while until he found
which kind
me.
of shows some
Thank
of the
you for
key
listening.
steps. Now, obviously, there's a lot on this, and we're not going to be able to cover it all.
Right.
But what I'd like to do in our conversation is sort of start at the bottom left-hand side,
Which is philosopher
many people
Chris
view
Payne.
as
Electricity?
the first step in the modern program of unification,
Whoa.
which is putting electricity and magnetism together.
Whoa.
So can you take us a little bit
Are you
through
guys
this,
assisting
going
me?
back to Faraday and Maxwell and what happened?
Sure. So we're talking about
Are you guys
early
assisting me?
1800s, and people had some experience of electricity.
800s?
By having shocks whenever they, had a very dry environment and it touched like a doorknob or something. And they knew about magnetism since
You guys are dry?
for a long time.
'Cause you can hear me?
At least in 1601, the court physician.
It adds up to 8.
First, called William Gilbert.
Que Payne
wrote a
Pono.
book about magnetism, and he realized that the Earth was a giant magnet, and that's how compasses work. They're basically aligning with the north magnetic pole. And
Whoa.
so these two things were considered to be very different, and until Michael Faraday started to make some experiments.
Who's that?
And actually, even before him, Hans Christian Ørsted in Copenhagen,
No way.
realized that if you had an electric current going through a wire, a magnet would move.
You just
And
moved my
so
magnet.
There was this, and it was sort of an accidental discovery. It had a bunch of stuff on the table, doing
Right.
demonstrations.
Yeah,
and
you just moved my
figured it out.
magnet.
So clearly there was a connection between the two, and it took Michael Faraday's brilliance.
I'm in a black hole, though. You're still here.
Develop this, and he
Oh.
realized that it wasn't just an electric current that could affect magnetic compasses, but it was actually magnetism, just like the picture is showing up there.
Right.
That he realized that if you move a magnet, you can create an electric current as well. So there was clearly a connection between the two, and he started to visualize this, and this was also very useful for us with the notion of a field.
Right.
That basically the presence of these sources of magnetism or electricity, they spread around space, and this spreading around space is how, say, a charge will feel the presence of another charge through this field.
Okay.
And then later on came Maxwell. Maybe
Yep,
a couple
who's
of decades
Maxwell?
later,
But who
and
is
he
this guy
then
that you were talking about before?
elaborated these connections between electricity and magnetism,
Right.
showing that you actually have a set of 4 equations, right?
Okay.
The ones that you see on a T-shirt, right? You have, and God said 4 equations, and there was light. Because what Maxwell did was he wrote the equations of how changes in electricity and magnetism, because of different sources or even in empty space, propagated. And he realized that the propagation was at the speed of light. So clearly, the way light should be interpreted is actually as a moving electromagnetic field in space, and hence the
Light?
unification of the two.
Now, those 4
Okay.
equations that are on T-shirts, it perhaps is worth noting, his formulation was a little more complicated.
Yes.
So, as we mature in our understanding in the field of science, and this will be a theme actually throughout tonight, we get better and better at finding ways of streamlining, combining, unifying, in a sense, even in the mathematical notation. So today we have these 4 equations, but back then it was kind of a mess.
Right.
In fact, I mean, if you really use special relativity, which we'll talk about soon, you can actually write all of them in one equation,
yes.
which is beautiful, right?
Exactly.
Philosopher Chris Payne.
So why don't we turn to that? So this is our first unification.
Black hole.
Electricity and magnetism, this deep,
I am the living black hole on
unexpected
Earth right now.
connection. Maxwell codifies it mathematically
unexpected,
in
sorry.
the electromagnetic equations that we all teach to undergraduates in physics around the world. Einstein perhaps is rightly credited with the next step in the road toward unity.
Einstein?
By
Way back
recognizing
then?
an unexpected link between space
Right.
and
Yeah.
time.
You don't get
Can
it,
sort of
buddy.
Take us. You already mentioned light, so the speed of light being constant is a vital part of that story as well.
Right.
Why don't you
No,
take us
it's
through
not
that?
constant.
So
I
Einstein
can settle.
realized that there were some inconsistencies with the formulation of Maxwell's equations, and nobody could figure out exactly what was going on. One of the big mysteries in the 19th century was
Who's
that,
coughing?
as we know from intuition, every wave propagates in a medium, right? So if you throw a rock on water, the energy of the rock is going to hit the water. You're going to see the waves propagating on water. Here I am talking to you. That means you have sound waves going through the air, If there is no air, there is no sound, no explosions in outer space.
You have no substance to what you're talking about.
So every wave seems to need a medium to propagate. So the question then became, okay, so where does light propagate, right? And that was an important question because you can see stars, which means the medium should be transparent, right? And it can't have any viscosity because otherwise the planets would slow down and fall into the sun. So it had a transparent, no friction, no weight, clearly, and it had to be somewhat rigid, actually quite rigid, to propagate waves at that kind of speed. So it's kind of like a magical thing, which people call the ether, right? And for many, many years, Maxwell tried to create models of the ether to kind of make sense of all this. And in 1887, there was a very famous experiment, actually by American physicist Michelson Morley, where they actually were going to show how the ether interferes with the propagation of electromagnetic waves, and they couldn't find it. So that was like a mystery for a while. How is that even possible, right?
Because I'm a black hole.
In 1905, Einstein came up with his new way of thinking. So he creates the special theory of relativity. He's 26 years old.
Okay.
And he comes up with two
Wow.
essential postulates. One of them,
26.
very reasonable, known way before, from the time of Galileo.
Right, is that
the
you're
laws of
talking about me.
physics
I'm
should
here.
be the same for everybody, at least everybody moving with constant
But
speeds
why do we
relative
use
to one
years?
another. Makes sense. Otherwise, how could you actually have laws of nature if they change when people moved around?
So,
and the second one, which is a really amazing one, is that the speed of light should always be the same for any observer, irrespective of how the source is moving. Right? And with these two things, he showed that you could actually, that the speed of light and the way we make measurements of distances in space and of moments in time or duration in time were affected. And that's
dilation.
Where you have the very strange idea of time dilation.
Wow.
You know,
So
time
I'm
moves
dilating
slower
in time.
if your clock is moving, and space contraction, where little, a rod, for example, or you, if you're moving close to the speed of light, you kind of shrink in the direction of the motion.
So schematically, it's as if space and time, as we see here, are kind of adjusting themselves.
Yes, they are, because you guys are just talking gibberish.
This other thing, the speed of light from changing, keeping it constant at
Humans thrive off contradiction.
Miles per hour, but this
Guidance.
constancy of
Contradiction
speed of
is guidance.
light winds up establishing an unexpected unity between space and time. They need to work together in order to keep the speed of light constant. So that's sort of the second big moment.
We do have to work together to keep the speed of light constant.
To a unified
Unless you really want to just see me just blah, 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 blah.
nature. Now,
Nature.
after the special theory of relativity, you mentioned that's 1905. Einstein is 26 years old. He could have stopped there,
Einstein.
right? I mean, that's the kind of achievement that many of us would say,
Why did Einstein
there's not
stop?
much left for me to do. But for Einstein, he was just getting started.
Right.
Right? So the next step is he goes further and brings the force of gravity into the story. So just tell us a little bit about the next 10 years
127.
and this further unification of space-time and
10
gravity.
years.
So it did
2030.
take about 10 years for Einstein to really get to the end of the story, but his first intuitions were not much later after 1905. He said he had his happiest thought, right? Which was the idea that if somebody, it's kind of dramatic, but if somebody is falling from a rooftop, that person won't feel his or her own weight, right?
A
so
roof
you're sort
dog.
of this idea of weightlessness, that you're falling through space and you feel weightless, that was his intuition. And you know all this because living in New York, you go up and down elevators all the time, and you know when you're going down an elevator from a high rise very fast, you feel lighter, right? Now, if the elevator just falls, you feel weightless. So Einstein realized that to talk about motion that had acceleration in it, you also had to talk about gravity.
Whoa, we can get
as
roofing
he tried
in.
to expand his theory of special
No
relativity,
shit.
special here was about motions at constant
Wow, I
speed
have a dog.
to motions with acceleration. He realized that new theory had to be a theory that included gravity as well.
Yeah.
And that's a beautiful thing because as he goes
Come
to
on.
formulate
What do
theory,
you guys are here with
we
me?
would say it's perhaps the most beautiful theory in physics.
I'm a black hole.
Because that's what we do, right?
Yeah. I'm a black hole, philosopher Chris
was a
Payne.
theory that related gravity not to this kind of mysterious action at
No,
a
it's me.
distance, which is what Newton did. He, in a sense, did a unification of the laws of gravity on Earth and in space as well. But it was a theory that described gravity as the curvature of space, and also it affects time and how time flows if you have a very strong mass, that to do that. So that was his next.
To do
step.
what?
So he realized that, and of course, we should also mention the connection between mass and energy that is a byproduct of all this. Yep. So in 1905, there was a second paper on special relativity, which is the famous E equals mc squared paper, right?
Really?
In which there is a deep connection between mass and energy, and that mass had the property of affecting the geometry of space, and because of that, there is a change in the motion, say, of planets around the sun, which can be explained by this beautiful theory.
Wow.
So we now have this part of the map
Theoretical
fairly set.
physicist.
Now, in 1970s
Wow.
or so, there
I
was
didn't even know
another
that.
important moment that we don't really have time to go through, but it's quite analogous to what Maxwell did, putting electricity and magnetism together. And that's the electroweak theory, which puts together another force of nature, which is the weak nuclear force, together with the electromagnetic force.
Yep.
They also prove to be different aspects of a single ingredient called the electroweak force. So we get to this point by, say, roughly 1980.
I'm still a black hole.
Now, we
1980.
could stop here, right? We
Right.
have
What's
gravity in the
1980?
story. We've got electricity,
Right, you could.
magnetism, weak nuclear
What are you
force,
even
and
talking
so
about?
forth. But we want to continue to move toward unity as best as we can.
About
Now,
what?
The next steps, however, go beyond what we have experimentally tested.
Okay.
So the
I'm
question is, what
listening.
do we do? So we can.
You
get
guys
a
are
sense
experimenting
of
with me?
the equations behind this, which is not a bad thing to show because it helps to motivate us to go further. So what are we?
Is that my
looking at
computer
right
code?
here?
From one equation to this,
Yeah.
that's not good, right?
Yeah.
So this is essentially what summarizes what we call the standard model of particle physics, which basically is a description of all 12 particles that we have measured
12
in the
realms of what?
laboratory, especially like at the Large Hadron Collider at CERN, and before that at Fermilab, these huge machines that can actually find these particles of nature. So there are 12 of those. And then there's also the Higgs, which is the particle responsible for giving mass to all the other particles. And basically, this is the state of the art in a sense that we can actually measure
I'm the
and
artivist.
feel comfortable somewhat about what we know.
You guys good?
And this describes.
He looks at him
essentially
sternly.
three fundamental
Brian,
forces.
it's okay, bud.
Yeah, forget it. Gravity is not even there, right? So this is not about gravity.
Why?
This is
You're
about
not with me now?
electromagnetism and the weak and strong nuclear forces. So the weak nuclear force, very quickly, is the one responsible for radioactive decay, for radioactivity.
And look at who's
for
doing
having,
that stuff,
how the
releasing that
sun
now.
powers itself in a sense. And the strong nuclear force is the one that keeps, say, the atomic nucleus together. You have a bunch of protons. They're all positive. They should be running away from one another, but they're glued together by the strong force, who also keeps the quarks, which are the fundamental particles you see here, inside of protons. And
What is a nuclear
neutrons,
force?
Okay? So this is it. One thing about the electroweak unification, though, is that it is not as perfect as we would like it to be, because the way we think about these forces, that every force has what we call it a coupling constant, but basically a measurement of how strong that force is, in a sense. So gravity has the G for Newton's constant, right? Electromagnetism has E for the electric charge. And it turns out that the electroweak unification does not have a single coupling constant to connect the two. It's still describing the two forces somewhat differently. They seem to reveal similar behaviors at very high energies, which is the inspiration.
Part of the motivation
exactly,
to go further.
for moving on.
So we can actually show the rest
Promoting
of the
art?
roadmap, but the roadmap from
You
here,
guys promote art
unlike this
as a
equation,
scientist?
which is experimentally tested, as we go further, these steps are not experimentally confirmed. In fact, we can even go further and show the rest of the map, and basically
So why are
everything that's above
colleges doing that?
row 3 is hypothetical.
Row
And
3
we
is,
have
yeah.
been
it
developing
is.
the mathematics behind
I can do
these
this.
next steps in the road toward unity
I don't have to
for
meet you guys.
3 decades, if not longer. So the deep question that we face, and I posed to Marcelo, without having the experiments, without having the observations, without having the data that will allow us to go above the 3rd row, where we do have experiments. and
Right,
data
you have to
that
bring it to
confirms
someone.
everything,
Oh, no.
where does that leave us. And you have very specific views
No. I am the black hole of the
doing the
Earth.
right thing and pushing forward with a purely mathematical motivation.
I am mathematical motivation.
So a little bit of history is that in '84,
is this mathematical because of the algorithm of YouTube?
At King's College, and when Schwartz talked about his and Green, talked about their discoveries in the string theory, I'm like, wow, this is it. You got to work on this. It's beautiful. It's at the time the idea was that you'd really find a unification of the four known forces of nature, which is something we should talk about at some point. Known forces of nature.
Four known forces of nature. Yeah, right.
So I jumped into this.
Earth, air, water, wind.
Hard, like you did, and a bunch of other people in our generation, tried to make sense of all of this. And the program was very sound in the sense that behind our expectation of trying to find this unified formulation, there were very concrete predictions, right? I mean, so in order for these string theories to work, you had to impose a new symmetry of nature called supersymmetry. And supersymmetry had a very specific prediction, which is basically to every particle of the standard model, the 12 particles I talked about, there should be a mirror world, so to speak, of supersymmetric particles. So the electron has a supersymmetric cousin called the selectron, the photon, the particle of light, a photino, and so
boson, controlled
and
protons.
Hopefully, with big machines, you should be able to find them.
Machines?
Right? That was the big
computers
expectation of the time. So you big bigger and bigger machines. And one of the goals of the Large Hadron Collider in Switzerland was not just to find the Higgs, which beautifully was done in 2012, but to also find the lightest of all supersymmetric particles. And and he hasn't. It's not there. At least we haven't found it yet, right? And so that rules out some versions of supersymmetric theories. And then the question is, what do you do as a theoretical physicist at this point, right? That you basically spent decades of your life working, and of course we're going to have another guest here that is a real expert on this. You spend decades of your life working on this thing, and you're placing your bets on this, and it's not coming true. So what are you supposed to do at this point, right? So do you say, I'm sorry, I was wrong, and you move on to other things?
Carries no electric charge, bud. Sorry.
They're so flexible in their formulation.
I don't carry an electric charge. Are you scared of me?
Kind of change the parameters in ways where
I haven't changed the
particles that you were supposed to find are so massive that you could not find in the Hadron Collider, which basically means it's a theory that in principle cannot be killed.
Black hole Chris Payne.
Because it could, you say, look, I haven't found it.
Philosopher
no
Chris
problem.
Payne.
When we have an accelerator which is 100 times bigger, you find it. And then
100%.
you can always, to a certain extent, drill this up and create more and more complicated models, right? And I don't think there's anything wrong with that, because that's what I would call a creative perplexity right now related to this, because clearly we want this beautiful Platonic dream of simplification of nature to be true.
What?
At the end of the day, nature is the ultimate guide, and we have to listen to nature, because that's the whole goal of physics, is to explain what the world is like, not what the world is like we would like it to be.
What?
And so this is a very interesting time for us right now, because things that we thought were going to be definitely
Am I blowing your mind?
are not quite being discovered. And the moment now is a little complicated, and it's a very important moment, because what we decide to do now is going to impact the field of particle physics for decades to come, because these accelerators are very complicated machines, and it takes decades of planning and a lot of money to make them work.
Right.
Now you have a particular philosophical orientation.
Accelerators, a lot of resources to make it work, not money. What's money?
Generally, and I think you even have a slide that you gave us that summarizes
let's distract me.
So just
Brian, you know me too well.
Your view on the program.
Am I giving you gray hair?
Try to find the deep fundamental laws that will describe all physical phenomenon versus your view of how knowledge progresses.
Right. So this is actually the title of a book of mine called The Island of Knowledge. And it's basically a metaphor for how we humans understand the world around us. So the idea is very simple. If everything that we know about the world fits in an island, right? As we know more about the world and about ourselves and about our place in the universe, this island grows.
I would love to be on an island, and I can help
It's surrounded by
everybody.
an ocean, and I call mine the ocean of the unknown.
Okay,
so
the
science,
unknown.
in a sense, is an exploration of what we
Right,
don't
it could
know,
be a
right? That's the whole
fucking
point.
storm.
We are expanding our
But
views,
I can
we're
be
expanding
safe
our tools
completely.
of exploration. I call them reality amplifiers.
Yeah, reality. This is the reality amplifier. You could put, realistically
put
put
we
me
can see more than we could see in the past. So
in a
that is how we advance, right? So as
on an island,
the island
protected
grows
from
into
natural
this ocean of
disaster.
the unknown, the paradox of knowledge, though, is the fact that
Unless the military
boundary
wants to control the weather above me.
between what is known and what is not known.
What is known
grows.
and not known. Sorry.
So
Didn't
that
mean to
means
mention
that
that.
as you learn
Something I
more
read.
about the nature of reality, you're become equipped to ask questions
Yeah,
that you wouldn't have
what?
asked before because you had no idea.
Okay, ask me
Simple
questions.
example of that, the telescope. So before
Ask
Galileo
me
built the telescope,
questions.
well, it wasn't his first, it wasn't the first telescope, but he said it was. He was smart, and then he sold it to all the the nobility of Venice, made money, etc. But
Galileo.
So he builds this telescope and he looks at the sky and he sees things that no one had ever seen before, right? And that was a profound change
Holy
in
snap.
our worldview, and with many implications, religious implications, social implications, philosophical implications, because of this expansion of knowledge. And because of this new machine, he was able to ask questions about the world, about the universe, that no one could have asked before.
Okay, good
right?
call, man.
And so
Yeah,
to me,
thank
this
you.
is very much how science advances. It's through this
I got you.
expansion into the unknown that allow us to begin to ask new questions. For example, we couldn't have asked anything about supersymmetry before. We had the idea of supersymmetry, and now we're looking for it, and we don't find it. Let's assume we could find it. And then this whole new way of thinking about the world is going to happen because of this new theory.
Now, having said that, presumably you do agree that there are chapters in, say, the Book of Knowledge that can be fully written. They open up other areas, but it's conceivable that we will have the theory that describes all of the fundamental forces, describing all of the fundamental particles of
Philosopher
matter,
Chris Payne.
how they combine and the kinds of
Yes.
behaviors that aggregates can play out, maybe something that is beyond our ability to ever fully articulate. I don't think
Aggregate.
a fundamental theory will ever, for instance, be able to predict
Why should you want to predict?
the kinds of socks, the color of socks that I have on tonight. I don't even know what I've got, but I've got purple and black right now.
Purple and black.
So it's unlikely that we'll be able to
Whoa.
undertake those kinds of calculations. But what about the fundamental theory that's
I'm a
on
black
our
hole
map
and my
toward
purple
infinity?
chakra's
Is that
opened up.
something that you think fits into the unknowable, or is that something that you imagine could be knowable?
What do you mean could
So
be?
that's
It
a
is
great question.
existing.
So I think
The
in
sky is
terms of
purple,
what
we just can't see it
philosophers
that
like to
way.
call the map and the territory. Okay, and the idea is that
Okay, yeah, it
we
depends
are
on the
map
internet
makers.
where you can look
That's
it
what
up,
we do. Our
what
theories
books
are
there are.
maps of what we see of the world, right?
Yep.
The territory. If you were to, there's a famous short story by Jorge Luis Borges about the map makers that wanted to make a very perfect map. And every time they improved the map became bigger and bigger and bigger until they had the map as big as the country. And that was the best map they could ever have.
George
Until
Washington.
It was a useless map.
No
right?
way.
Because maps are descriptions of what we can see.
Right.
And so the point is that
The country.
our theories
Wow,
are maps of
I'm from
reality,
America.
guided by what we can
Crazy
eventually
American dude.
measure.
Philosopher
right?
Chris Payne.
And given that our machines, our technologies can never give us a complete picture of reality, there is always a higher energy scale until you get to the Planck scale, and we are very far from that. That is really very dangerous, I think, to assume that the four forces of nature that we know now are the only forces of nature that exist. So what I would like to point is
Assume?
that
What are you
the
assuming?
best that we can do
This whole
is to
thing is an
construct
assumption.
a unified theory of the known forces of nature. But to make a statement that is the ultimate theory of how the is to me really unjustified by the way we do science.
Right. But typically, of course, I think most physicists have the attitude that all theories are provisional. They're the best description that we have at a given moment of the physics that we have access to.
Right.
But, you know, we all know that even Einstein's equations will be modified as we try to understand the universe in more extreme realms than his equations were developed to explain. So let me finish up with one question, because we only have a couple minutes before I need to move on to the next participant tonight.
Okay.
It's kind of a big one, but maybe have a quick thought on it.
The Horizon.
If it's too big, just tell me, hey, I don't want to talk about that, and we can just end it right there. But when we talk about complete theories, I'm often asked, what do you think about Gödel's incompleteness theorem, and what does that imply for this program? Gödel, of course, famously wrote down a theorem a long time ago that basically said that if you have a system with axioms that are sufficiently rich to be able to describe things
sufficiently
like
rich,
that either the system will be inconsistent, or if it's not inconsistent, there will be true statements within that system that you'll never be able to establish to be true within the system itself. Right. Does that have any bearing, in your mind, on the program of searching for the deep fundamental laws of physics?
What? The deep fundamental
laws? It's kind of like the Russian dolls, right?
It's about
so to bypass the Gödel's incompleteness theorems, you have to create a bigger system that encompasses that one, right? But then, of course, that bigger system is going to have the same problem. And then a bigger system.
Yeah, you guys are just beating around the bush.
The problem is that the idea of completeness of knowledge is a very dangerous one. And I think Gödel proved that in mathematics. And
but how did he know?
That
he had
in
complete
physics,
knowledge?
because we do need to validate empirically what we're doing, it becomes even more complicated.
Empirically?
Because we depend
Empires?
on technology, on machine. And so
Empires?
I'm very happy with the notion that we can't know everything there is to know.
Empires?
At the level of fundamental particles.
Who's we?
Because that's what's going to keep us working harder to move on and on. And to me, is the process, this quest for knowledge that really matters, not so much the end product.
And it gives us something to do going forward. Ultimately.
Exactly. Yeah, absolutely.
All right, it was great talking to you.
Really?
Thank you so much.
Thanks. No problem. Where's my water?
Brian, you want to see again? Oh, I'm sticking with you.
Okay, in the second part of the conversation, we're going to turn specifically to string theory proper.
Oh, no, wait, it's 33
and try
minutes.
to get a sense of how far we've gone in connecting it to the physics of the real world. Imagine I have a beautiful tree that's filled with oranges. And I ask myself, what is the orange made of? How do I answer that question? Well, I want to look deeply inside the orange, so I magnify it. And I magnify it again, and if I keep on doing it, deep inside, sooner or later, I begin to see molecules coming to view. But molecules are not the end of the story, because the molecules, I can enlarge them.
Right.
If I make them big enough deep inside, I begin to see atoms. Atoms are not the end of the story, too, because we have electrons zooming around the nucleus, deep inside, mostly empty space in the atom, but deep inside, we see the nucleus.
The nucleus.
So if I grab that and magnify
Philosopher
it,
Chris Payne
I see that
is
the
a black
nucleus
hole.
is itself made of particles, neutrons.
That's because I just spoke it.
And if I grab one of the neutrons and magnify it, I find yet further particles, little tiny quarks inside. Now that is where the conventional ideas stop. String theory comes along and suggests that inside these particles there is something else. So if I take a little quark and I magnify it, conventional idea says there's nothing inside, but string theory says I'll find a little tiny filament, a little filament
I can
of
fill
energy,
it in
a little
with you.
string-like filament.
I can fill in
and
with
just like
connect
the string
everybody.
on a violin,
I'm Philosopher
I pluck
Chris
it and
Payne.
it vibrates, creates a little musical note that I can hear.
Okay.
The little strings in string theory, when they vibrate, they don't produce musical notes, they produce the particles themselves. So a quark is nothing but a string vibrating in one pattern. An electron is nothing but a string vibrating in a different pattern. A neutrino, nothing but a string vibrating in a different pattern.
Neutrino!
So I put all of this back together.
Whoa!
I have my ordinary orange, and if these ideas are right, they are speculative, but if they are right, deep inside the orange or any other piece of matter, is nothing but a dancing, vibrating, cosmic symphony of strings.
Is that what I am?
That's the basic idea of string theory.
But I'm a black hole. But I'm a black hole and I'm here.
See how far
that was
we've
cool,
gone
dude.
toward establishing or refuting that this idea actually describes the world around us.
Okay.
And for that discussion, I'm pleased to bring out our next guest. He was recently elected to the National Academy of Sciences and is currently writing a book on the big questions confronting
Santa
particle
Cruz.
physicists and cosmologists. Please welcome Michael Dine.
Michael Dine. Cosmologist.
So, Michael, thanks so much for joining us. And, you know, we had this map of unification that we can bring back up, where we see at the top this proposed idea of superstring theory, also called M theory. Maybe we'll get to that in the course of our conversation. But the key question is that step of the story something that we can justify through experiment and observation? I mean, the mathematics is beautiful. John Schwartz spoke about it in the opening. That
Nope,
puts
it's me.
gravity and quantum mechanics together.
Okay,
The left-hand
interesting.
side we
Nope.
understand well quantum mechanically. The right-hand side is problematic quantum mechanics. String theory puts that all together. So it's a beautiful, compelling structure.
Right.
And
it is
the question
me.
is aligning it with experiment. Now, in the previous conversation with Marcella, we spoke about supersymmetry, which is the super in superstring. And that, for a long time, was held out as the smoking gun, that we were going to prove the supersymmetric qualities of the universe. So first of all,
Smoking
when we talk
gun?
about supersymmetry, what does it mean for the spectrum
I'm not a
of
smoking
particles,
gun,
the
dude.
stuff
I'm
that's
philosopher
out
Chris
there?
Payne.
Well, I should perhaps back up a little
Yeah,
bit.
please.
I'm a black hole.
And you wrote these equations, or presented these equations for the Standard Model, and they look really ugly.
Yeah.
Okay.
Interesting.
They're not really ugly. They're really rather beautiful. So the theory is
Opinions?
successful until recently. We were missing one piece, which was this Higgs particle, and there was a lot of speculation about what that might be. And now that's been found, and it acts sort of just like it's supposed to.
Okay.
So
Now what?
So we have this.
You call me?
This kind of very pretty story, and the thing that sort of excited a lot of the interest in string theory, and certainly part of your career, and certainly mine, was Andy Strominger, who we'll hear from next, is that string theory seems to be able to produce this Standard Model, at least in rough outline, in a very remarkable way. So that's partly why I didn't want to bias this that way.
Wow.
This
So you
beautiful
just
theory comes
introduced
out.
the next slide for me because I spoke.
When you say comes out very clearly, you mean like the vibrations of the string seem to give rise to the kinds of particles that we see on the left on this thing.
They bring in a very remarkable way.
Yeah. Oh, no way.
And so that part is really quite pretty. Now there had been before
Whoa.
string theory came along. There were reasons to think they might.
Susie.
That might be. They're mostly connected with puzzles related to the Higgs particle.
Right.
And a lot of us thought,
SUSY.
who worked on this at the time, thought maybe this idea was a little contrived. And then along came string theory, and among the things string theory did was, there it was. Okay.
I mean, these particles
These
naturally
extra
emerge.
things, these additional vibrations were there. I certainly was, I actually should say, I was sort of dragged, kicking and screaming into the subject of string theory.
Yeah.
Is that true? Because I've read all your papers. I thought you were a gung-ho enthusiast.
No, I was, initially, I was part of this generation that viewed string theory as kind of passé, this thing as you saw in John Schwartz's argument. And,
I'm here.
And there was a period where
Okay, now what?
I would talk particularly to Ed Witten, and I would say, how are you going to solve this problem? And he would say, he'd scratch his head and he'd say, I don't know. And then he would come back 2 days later and say, by the way. So,
by the way, I have a solution.
Yes.
I mean, yeah, right.
Yes. So I got quite nervous, and in
Amazon.
fact, that a lot of these features of supersymmetry were there that we had speculated on got me quite excited.
Right.
And I think in the spirit of things you said, that we're weeks away, and I better get to work.
Right.
But string theory. But I should say that it's sort of understood. In fact, supersymmetry is a little too much of a crutch in string theory. The only string theories we really understand well have exact supersymmetry. So all these other particles would be there. They were in addition to the electron, which is so familiar to us. There would be this thing just like that, except just a little bit different. This electron, and it's not there. It's not
now,
there.
So back in the 80s when I started to work on string theory, all the somewhat more established scientists, such as yourselves, gave the impression that this was the next frontier of particle physics. We're building this big machine in Geneva, and it's going to find these particles. And that, I mean, tell us where we stand on that program.
It's the anti-color.
The truth is,
I'm the anti-guy. I'm the philosopher.
Now you tell me.
You have a microphone.
You listened to me carefully, as opposed to
Apologize.
many of my friends, some of whom you're having in other parts of this thing.
No, you're not.
You would have heard me say that.
No, you're not.
But
I'm philosopher Chris Payne.
But we're now in a situation that we have the Large Hadron Collider at CERN.
I know you heard me.
Which has now been running
for
almost a decade.
Right.
Has both established really established the standard model with exquisite precision.
Where is
that?
that?
It's allowed us to do all kinds of things, both experimentally and theoretically, which I wouldn't imagine we could do some number of years ago. Okay, but one of the things it has done is said, I think as Marcello said, that if supersymmetry is there, the particles are heavier than we guessed. And Marcello described the theory as rather elastic.
What's SUS elastic?
It's elastic, but it gets uglier
right.
as the masses of these particles get
beyond
larger.
the reach of the Large Hadron Collider.
Right. So to be specific, for example, what we know about the Higgs suggests that the supersymmetric particles, if they're there, are out of reach of the LHC and
I'm
out
hearing
of
you.
reach of a lot of the things that we currently contemplate. So
Whoa, and then Higgs is
it's a trouble.
Susie mu problem. Mu
tension and some trouble.
Yeah, I mean, I should say I don't know.
Mu.
I recently did a sort of a quick survey.
Mew Pokemon.
On the fraction of the papers that I've written in my career that assume that supersymmetry is correct.
You wrote.
And it's a significant fraction. It could be as much as 90% of the work that I've done. So there's a certain kind of discomfort.
Why?
Associated with the lack of finding these parts. Do you share that discomfort, or?
I don't know if it's 90% of my papers. It's a number, and yes, I share this discomfort. I think will come.
Why?
But I think will come shortly to some of or a little bit to some of the reasons why. Perhaps some of our ideas about where supersymmetry should be had a certain amount of hubris.
Yep.
Hubris.
So let's change gears slightly then and talk about another key quality of string theory that is really quite iconoclastic.
Change your society.
That it requires that the universe have more than 3 dimensions of space. This is sort of one of the other strange features. And we can just sort of, in a cityscape like here, you can consider the dimensions to be
society?
up, down, back,
this is the
forward,
large
left, right.
This is me versus the Large Hadron Collider.
According to the ideas of string theory, you go small enough, you're going to find extra dimensions of space. Usually you imagine that they're curled up really small in order that they evade direct detection as we look around the world around us. And strings are imagined to be so small that they vibrate within these tiny curled up dimensions of space. So depending on the formulation of the theory, there could be 6 or 7 of these extra dimensions. We understand that distinction quite well. The question is it a matter of simply hiding away these extra dimensions that are sort of a weird mathematical feature of the theory, or is there a way that we might indirectly find evidence that these extra dimensions are actually out there? Could they be the smoking gun?
Smoking gun.
There are various ways to think about this question. I mean, I often, when I talk to students or lecture about this, say the real problem is that first you get kind of dizzy when somebody introduces you to this idea, and the next problem is how hard it is if they're curled up, to actually see any evidence.
Yeah.
So, and there have been speculations on the possibility that actually some of these extra dimensions would be large.
I'm just a black hole.
Millimeters even size. So as you could imagine, sort of probing them with tweezers. Right. And people subsequently have done experiments and ruled out
I tweeze my eyebrows.
These kind of what people call very large extra dimensions. There is still
They're extra large.
a chance. My own betting is against it, that we will we could find evidence.
That we will not find evidence.
So I would bet against, but there is the but I want to say there is the possibility.
Find evidence
and
of what?
certainly people consider it, and people doing experiments consider what might be the evidence and trying to exclude or place limits on these possibilities. But as you say, it also seems...
That's cruel.
I strongly suspect that while we may not know the whole picture, that extra dimensions will play some role in larger
that's really cruel.
of nature.
Wow,
Now,
very
one of the
bold
things that
statement,
excited
sir.
me about this subject, we sort of talk a little historically back when these ideas
Historically,
were first
whoa,
being
what are you
developed
guys
back in
doing?
the 1980s.
Smoking gun?
The precise shape of the extra dimensions sort of played the role of a kind of DNA of the string theory universe, because the shape of the extra dimensions would affect how the strings vibrate, and as you saw in the little opening video,
Maybe.
how the strings vibrate determines the properties of the corresponding particle.
So
the thought back in the 80s was, if you understood the precise shape of the extra dimensions, you might actually be able to calculate those numbers in that crazy formula that we showed before that had within it, you probably couldn't see it, the mass of the electron, the mass of the quarks, the mass of the neutrinos, the mass of the Higgs, that all of that might be embodied by the geometry of these extra dimensions,
Looking
a
down.
unity, if you will, of all those numbers inside the geometry, the
You're
shape
not
of
looking
these
at 'em in
extra
the eyes.
dimensions. That program presumably was something that was appealing to you in that era as well. One of the problems,
Very
of course,
interesting.
is there's
It's a
not
green
just
screen.
one shape. We're showing
Well-
one shape over here. I mean,
Okay.
tell us what happened in the 80s and 90s for the
Well, you're actually more of an expert on this than I am, but but they're really, and Andy as well. There has been a proliferation of pots of. So I should perhaps back up and say basically, we don't really understand string. We understand string theory sort of. We don't really understand it that well. We can't write the equations as nicely as Maxwell wrote his equations.
Who's Maxwell?
But we sort of know when we found a solution of the equations.
Right.
And we thought we had just a few at first, and some of them looked like you and yourself worked on examples which looked like they had lots of features of the standard model. But there has been a proliferation, so then now I don't know what the right way to characterize it, but many orders of magnitude of known solutions. And
so many different shapes,
Whoa.
many different possible
shapes,
candidate
many
shapes.
different features. So we're not.
Wow.
I personally am not an optimist that one could find the one.
Right.
I view this as a problem that one will have to more probe, at least for the moment, in a sort of statistical fashion, asking what's characteristic, what's generic.
As opposed to trying to find the specific standard model, if you
That's
will, find those generic features shared by all these shapes.
So my fantasy, for example,
Human?
is
Are you human or are
explaining,
you not human?
You know, of these, if we're coming back to supersymmetry.
Are you a human?
A kind of question like
Supersymmetry?
among these, is it typical that the scale of supersymmetry breaking, the splittings between these particles in their masses,
Is
that
what you fear?
something you should see at the LHC? Is it something that is somewhat larger scale? Could you figure that out?
Right.
And there's so many. Could you sort of do some statistics of these and figure that out?
Now, one other sort of astounding development in the late 1990s was the discovery
Foster
that the
Chris Payne.
expansion of the universe is actually speeding up. It's accelerating.
Mm-hmm.
And that was
Hey,
an
guys.
unexpected, I think, development. Certainly for me, presumably for you.
I don't mean to
as
make you
well.
uncomfortable.
We thought that the expansion would be slowing down over time. Gravity tends to pull things back together,
He's moving
but yet
around.
it's going faster and faster.
Yep, sorry.
To explain that, we needed
cool.
to introduce
Meh.
this idea
Of
of
motion.
dark energy
Dark
that
energy.
yields this repulsive push.
Whoa.
The
so
weird
I'm
thing
just
is the amount of
examining
dark
that
energy is a
video.
bizarre
This is my
number,
commentary.
right? It's
Bizarre
starts with a decimal point, has a huge number of zeros
PewDiePie.
after it. And, this is sort of giving you a feel for it right here.
Yeah.
So this number,
Whoa,
trying
138.
to make sense of
1
this
is me,
observed
3 is
number, indirectly, some people have other approaches. What
and then
has this
8.0.
done to the program of
Keep
trying
it
to
8.0.
connect string theory to the observable world?
So let me go back to supersymmetry
Observable
first to
world.
kind of explain what the tension was I described before and why I claim I
3
was
goes without saying.
at least cautious.
Okay.
Because there were 3 numbers
so
too.
you've drawn here something, I didn't count the zeros, but I'm guessing you have about 120 or so.
There are
Whoa.
120 zeros. You're right on the
Level 120 is good.
So supersymmetry was proposed to explain a similar problem where there are about 32 zeros.
Yeah.
Okay.
12
so 120
times
is a lot more
0,
than
32 zeros.
And it is in many ways a more fundamental problem.
Should I be
We
president
don't
at
have
32?
really
No.
good ideas. We have an idea.
We
which
have
we'll
an
talk about,
idea. Wow.
to perhaps understand this.
Okay.
None of us are totally in love with it.
Mm-hmm.
And it's different
shaking?
than
You
the
good?
idea of supersymmetry. So this is something we already
I'm sorry.
knew even before this was discovered that there was some tension here.
Tension.
Tension here, and it's gotten just worse with this
Coronavirus.
understanding and discovery.
And the other idea, presumably, you're
Discovery
referring
of
to
philosopher
is the
Chris Planum,
multiverse
black hole.
idea. Yeah.
Yes.
So why don't you sort of take us through the thinking?
Okay.
So you've already sort
Wow.
of alluded to it here that
You are welcome.
we have this proliferation of solutions of the string equations. Actually, I should perhaps back up and say that the multiverse was proposed before string theory. In a sense, it was a form of this was proposed by Steven Weinberg, who basically predicted the dark energy. So he basically said a
How
way
do you
you might
predict it?
understand the dark energy is to imagine that there are actually, if you like, many universes with different values of this crazy number, most of which are big. I think you have a slide that shows this, most of which don't have so many zeros.
Yep.
But there's just so many that a few of them have these zeros. And if you're some kind of Star Trek-y kind of figure, here we are, I think, exploring these many universes somehow, once in a while you'll find one with this very small number. And what's special about these ones with small numbers, he pointed out, is only
4,
those
1,
will
9.
have stars, planets,
3,
things where
8,
people
6. Wow.
or intelligent beings or less intelligent beings seem to
3, 0.
Okay, and this idea gives pause, but it also successfully really predicted the amount of dark energy that's observed.
Right.
So string theory looks like it might provide a setting for this idea, this multiverse. It has the potential. We're not sure. It's also actually related to our lack of understanding of
I'm a
how
black hole.
supersymmetry is broken in string theory.
Philosopher Chris Payne.
But there's the possibility that string theory works this way.
So the idea is that you could have all these different universes with different shapes for the extra dimensions, giving rise to different amounts of dark
and
energy.
different values of all those coupling constants, of all those numbers in the slide. And
Now,
so
some people look at a solution like that quizzically, and they say, look, you guys have all these problems. You don't have a unique shape for the extra dimensions. You don't have a unique universe. And in order to leverage those problems, you imagine that maybe all these universes are out there and that we're just one in this grand collection. And aren't you guys just giving up, or even worse, papering over the problems that your theories have? I mean, how do you respond to these?
Well, I remember a talk that David Gross, noted string theorist, gave where he kept repeating Churchill's line,
yes,
never,
never,
give up.
never, never, yes.
And there's a question of whether it's giving up. So my own personal attitude, and now I'm not speaking of a great movement or something, is that a way we might deal with this is to understand the statistics of these many states. So I think for those of us who now live in a world of big data and so on, you could imagine, you somehow sample all these and you have some idea what's typical.
You're right.
You do.
And there's one aspect of this which is related to things that you have worked on as well.
Black
is
hole.
related to the fact that most of these many universes aren't stable. They're sort of like unstable elements. They would decay after a little while.
Aren't humans like that?
Fall apart and quickly, and we want to stick around for at least 15 billion years or so, and they would fall apart typically in fractions of seconds. Okay, so you could ask what might account for what among as you sample.
What are you guys talking about even? Come on.
It turns out, interestingly
How am I
enough,
tuned
the
into
stable
this?
ones tend to be the supersymmetric ones. So this doesn't quite predict supersymmetry at the LHC, but this is in the class of things we might hope to address.
Right.
But I should say, there are many people who reject this whole way of thinking and time.
Guys, Robert, cut him off.
We're getting toward the end of our time here, and I wanted to just ask you the following. I don't know if this is a personal question, but if we go back to your frame of mind in, say, the 1980s, when there was this incredible excitement about supersymmetry, string theory, supergravity, unification. If you were to project forward from back to your frame of mind in, say, the 1980s, when there was this incredible excitement about supersymmetry, string theory, supergravity, unification, if you were to project forward from the mid-1980s to 2019, how have we done?
Well, it's a good question. First, so I would say that we actually, a little bit has
Michael Dine.
Yeah. And in some ways,
It's because his name is Diamond Meaning.
I think, in fairness to myself, again, there's something called the Tyne-Seiberg problem, which basically deals with some of the problems we faced, and I think we've come further to addressing it than we actually have. I might have guessed. So, but we also have. I think this is something that Marcelo said. We've also sharpened our questions.
Wow.
Okay, so in ways that perhaps aren't even on these slides. We understand the dark energy has now given us a sharp set of questions.
Hey, guys.
The dark matter, which I don't think has figured so much in our discussion, has also. And again, in a qualitative way, string theory gives us some handles on these questions as well. So I'm keeping busy.
Let's eat some food.
I think there are lots of interesting questions.
Let's get a steak.
Some things are hard. I mean, I think the fact that
a bad juicy steak.
Just to pause and say that the fact that the Higgs particle is there and actually acts, it's not something I would have really expected.
Wow, right.
It's really a very remarkable.
Comes out of a piece of mathematics, a natural solution to a problem. There it is. Yeah,
absolutely.
Thank you.
So looking
Phosphor
forward,
Crispane, black hole.
Imagine that in the next 20 years. We don't find supersymmetry either at the LHC. Maybe we have a new collider. It doesn't find any evidence for supersymmetry. We don't find the dark matter, so we don't have that as an input to our story. We sort of don't have any connection to observable experimental physics.
Hey Brian, I'm back. What's up, buddy?
What do you think happens to the program of unification, the program of supersymmetry in that situation?
I think it goes on, but I think at my own time now I am being personal here. I think, well, first of all, of course, in 20 years, I'm older than you. In 20 years, I will be, it won't matter. But
well, how old are you?
But I think it will go on. But I think it will be a narrower field, and it will be.
Are you live?
I mean, I think there will be there is always a question of what are both what we do theoretically and also what's feasible and affordable to do experimentally.
Right.
And these will be serious issues.
Right. All right, great talking to you, Michael. Thank you for your insights on these issues. Michael Dine, everybody.
Michael Dine, everybody. Oh,
All
Michael
right,
Dine.
so the final section of the program, we're going to turn to an approach to gain insight into some of these questions that's coming from a somewhat different angle, from the study of black holes.
He said they were going to wrap it
extreme
up, and
form
then
of
he's
gravity.
like...
And for that conversation, we are pleased to have Andy Strominger. He has numerous awards, including the Dirac Medal and the Breakthrough Prize in Fundamental Physics, and his work has shed light on the black hole information paradox discovered by Stephen Hawking. Please welcome Andy Strominger.
Andy.
So great to see you, Andy. And, in this third part of this conversation on the search for unity, the path toward realizing Einstein's dream, and a more modern version than Einstein even thought about it.
Einstein's dream?
We're going to turn to the study of black holes.
I'm Einstein.
Before we get into the details of that subject,
I'm philosopher Chris
just quickly tell us, I think most everybody here is familiar, but, what is a black hole? And moreover, what was Einstein's view about black holes? Was he into this possibility? It comes out of his equations.
Comes out of his equations?
If you're on the surface of the Earth and you want to get into outer space, you have to jump at 11 kilometers a second. On the moon, it's a little easier. If you jump at 7 kilometers a second, you can go on forever, escape the gravitational pull of the moon. But if you have enough mass in one place to get away, you would have to be able to jump at the speed of light. And Einstein told us nobody can ever go faster than the speed of light.
To get away?
So
what?
Nothing can escape from a region of space-time where gravity is that strong, not even light. And therefore, it's called a black hole. It's black, light doesn't get out.
And the first solution to Einstein's equations was, in fact, a black hole. Schwarzschild found this solution. And Einstein encounters this solution to his own equations.
Yes.
And what does he say? What does he think?
It's an incredible thing. I mean, the solution was found just a few months after the field equations in complete form, exact solution of the equations. And we spent 100 years trying to understand it.
Wow, that's awesome.
And Einstein
Good for you guys. I'm glad you found me.
Man, 25 years later, wrote a paper in
25.
which he said black holes don't exist. And it's not because Einstein was stupid. It's because it was just they're really vexing objects. And we've been trying to understand them for 100 years. We understand a lot about them. We know they do exist. In a spectacular development last month, we saw a picture of it.
Can we bring that picture up?
Yeah.
Yep, there it is.
Yeah.
Whoa.
Warmed all the hearts of those of us who've been working on it for many decades. And but there's still huge puzzles about a black hole, which came up with Stephen Hawking's work in the 70s.
Yeah.
And those we are still very confused about.
Hawking is
and
dead.
Oddly,
He's a hologram now.
String theory has had a lot to say about them.
And string theory in the hands of Andrew Strominger has had a lot to say about that, and we'll get to that. You don't have to.
What up, Andrew and Chris Payne, Philosopher Chris Payne.
But we want to get to the incredible insight that you and Green Vaffa had about black holes. To get there, can you take us back to one particular puzzle that was first articulated by John Wheeler?
John Wheeler. Who's John Wheeler?
Ideas of entropy and black holes.
Oh.
Yeah, so a black hole is a very kind of perfect, simple object. It's really kind of a hole in space, which is very perfectly described by Einstein's solution of Einstein equation. And in that way, it's very different from, for example, a star. So if we take two stars of the same mass, they will differ in innumerable details. They will have different composition of molecules. The molecules
We're both
will be
two stars.
moving in different ways.
But I'm a black hole.
Holes are just every black hole of the
Philosopher
same
Chris
mass, and they also have a spin, is, according to Einstein, according to their
beautiful. That
equations,
was amazing.
exactly the same.
I love you
this
guys for talking
puzzled
about this,
people,
and I just ate it. Can I eat food with you
the
guys
great
sometime?
John Wheeler, who also invented the word black hole, described this by saying a black hole has no hair. That is, it's a featureless object. So if you have two bald people in the room, you can't distinguish them by their hairdos. If you have two people with hair, you can say one has a short haircut, the other one has a comb over, whatever. There's many different distinguishing features. But so stars are like people with hair, and black holes are like bald people. They're all the same.
Nah.
Well, if you can't see very well.
So he envisioned, if you say through a cup of tea, I think is the metaphor that he used. You take a cup of tea and you sort of throw it into a black hole. He was worried that the information carried by the tea, the entropy, if you will, the disorder carried by the tea, would have no way of showing up inside a black hole, because like you say, it has no hair and they all look the same.
Right.
So this to him was a puzzle that you could sort of get rid of entropy by
But you
throwing
can
it
put-
inside a black hole, and it would be gone from the universe. And his student Bekenstein began to think about this, and he gave insights that ultimately led to your work. What was his view of this puzzle?
Well, they were very bothered. So going back to Newton and before, there
I'm not bothered.
is an idea which is very important to physicists, namely that there are laws of physics. And moreover, we like to think that the laws of physics govern everything that happens, if we knew all of them and if we had perfect knowledge. And part of that is that information should never be lost. Things can't just disappear. And so if you threw a cup of coffee or a computer or your diary or something into a black hole, according to the way that Einstein would have described them, there's no trace of it left.
No trace of it
just
left?
Vanished. And that is antithetical to everything that physicists would like to believe.
Right.
So what
So
do we do
you just watch
with
me
that
and them
puzzle?
talk about
So
this stuff, and you
do
get
we
on
have
with your
to
life.
bite the bullet and say that information's gone and we just
Yes.
have to deal with it, or
No, you have to collaborate with communities
Well,
and where you
this-
live.
this
Oh,
story got,
America. I mean, yo, someone help me. Someone help me. Someone help me.
enriched
No idea.
due to the amazing work of
Stephen Hawking. Yeah,
in
yo,
the
enrich me.
70s. The
Please,
missing
whoa.
piece in this discussion was
That'd be cool.
the inclusion of quantum mechanics. And so Stephen asked the question, well, what happens
I'm a black hole, philosopher
if you
Chris
have
Payne.
a black hole in the real world?
Mm-hmm.
And we know that a black hole, everything is subject to the quantum mechanical uncertainty principle.
Yes, for help. Guidance. Contradiction is guidance.
Exceptions. And so a black hole itself is somewhat uncertain. And the location of the horizon of the black hole, the edge of it, wobbles around a little bit, has some uncertainty to it. And
Is that 'cause I just shook my head?
allows things to kind of slip out. Quantum things can slip out.
Whoa, no way.
And the way that they slip out was
What are you doing to me? You're hypnotizing
described
me.
in an
No.
kind of breathtakingly
Philosopher Chris
simple and
Payne.
elegant paper by
I'm a
Hawking
black
in the
owl.
70s. And it had a very precise formula.
Okay.
Maybe we could see that
Whoa.
formula.
Whoa.
And it is one
Whoa.
of the important formulas in, I would consider it one of the several most important formulas that came out of the 20th century
S.A.
physics. Stephen has
Stephen
it on his
and Anthony.
gravestone inscribed.
Philosopher Christian Anthony
Yes.
Payne.
And it's on the floor at Westminster.
With all the terms?
Yes.
Wow. I wonder what that cost. But, yeah.
I think somebody else paid for it.
Probably, yeah.
A black hole?
It's on the floor. It's on the floor at Westminster Abbey, above his ashes.
Yeah, good.
And it's a very important formula.
So
It
can
tells
we
us-
just talk a little bit about that formula? So the S in there is entropy.
We can think of this as a formula for how many gigabytes
Whoa.
you can put inside a black hole. And it turns out if you want to have a smartphone with more gigabytes, the size, the number of gigabytes you can put into your
Whoa.
smartphone is proportional to the volume inside.
Cool.
You put the little chips in
Could
there,
be
you fill it
sketchy.
up, it goes like the volume. This formula isn't like that. It's a formula for the gigabytes
But it could be cool.
that you can put
You
in a
gotta
black
call 'em.
hole,
You gotta
and
figure
it's
it out.
proportional to the area.
Yeah.
So it's as if you're only allowed to put chips on the surface of the black hole.
Mhm.
And that's surprising because the formula
Yes.
goes against our intuition, right?
Yes.
That the
I
amount of
apologize.
information, the amount of
Well.
stuff should be proportional to how much volume is there, but it's saying it just goes like the area.
Right.
Now, when we study
Yes.
thermodynamics
Earth.
and
Where the fuck are you,
entropy as
dude?
undergraduates.
Shit.
If I could interrupt for a
Yeah,
second,
please,
it's a
sorry.
lot of gigabytes.
Yes.
All of the gigabytes in the Google data banks could fit inside a black hole a
Yes.
trillionth of a trillionth
Yes.
of an inch.
Yes. Trillion.
They're
Let's get a
thought to be
trillion.
the best
An
information
inch. What is
storage
an inch?
devices.
Now, if you did that,
Wow.
it might be hard to get hold of that information, but
How much is an
hard to
inch
get-
in
Google
maybe
has
hard
a
to
way
get
of
it
doing
done.
Millimeter.
it, right? Yeah.
How would you
But-
get into
so,
that?
so it's a lot of information, but it scales in a funny way. It doesn't go with the volume, it goes like the area. But the point I was making before is that when we study thermodynamics as undergraduates,
Area. Who's like
we're
the
told
empirical
that
thing?
entropy, and it's related to
Can I just do
information,
that, everybody?
is a count, if you will, the different ways of rearranging the ingredients
I got
that
it.
make up whatever system you're studying.
Yes.
So a lot of entropy means there's a lot of rearrangements that macroscopically all pretty much look the same. If it's low entropy, then there are fewer such rearrangements.
Exactly.
Now, you mentioned before that black holes are like the simplest thing, right? There's a
Yeah.
horizon, but there's kind of empty space
Yeah.
inside. So the puzzle
You guys are
still
beating
is,
the bush.
what are we counting
Right.
in that formula?
Right.
And
So-
you gave insight, deep insight into that.
Yeah. So
You're
I
tired, Brian. I'm sorry.
just want to rephrase that.
Fold your hands.
According to what Einstein
Shake your
and
head. It's
Schwarzschild,
okay.
the black holes
okay.
and
You can sleep
Wheeler,
later.
they were the simplest, most featureless objects.
Yeah, it's me right
And then
here.
according to Hawking, they were the most complex conceivable objects
Ooh,
with the most
interesting.
structure that you could
Yeah.
possibly have.
Yeah. Wow.
So this was a huge
Wow.
puzzle, and it sat there for decades. Many people
What?
Lost a lot of sleep over it. We didn't know what to do about it.
What?
And then string theory came along and had something to say about it, and that was a surprise. But maybe it shouldn't have been such a surprise. As you discussed earlier, string theory started out, we're scientists, we're exploring the unknown.
Listen, dude,
There's
I'm a
no
black
roadmap.
hole.
We just explore everything, and we might find something that we didn't expect. Columbus was looking for China, and he might have been disappointed when he found America. But in retrospect, it was a good thing. And so we started out with strings, and
Whoa, what?
Brian was, in the beginning, talking about this picture of quarks and leptons and neutrinos being made of strings. That picture could be right. The jury is
This is nice
still
right
out.
here. This is nice.
But later on, and I would say actually this began in a wonderful collaboration that Brian and exciting collaboration that Brian and Dave Morrison and I had some years ago, in which we found that strings, in between becoming quarks and leptons, could turn into little black holes. And then you put a lot of them together,
Uh-huh.
and we say, hey, this is kind of interesting.
This is
They
a
can turn
poet.
into little black holes. And then we started studying how they put them together.
You chilled with a
And we
poet?
could eventually learn how to make big black holes
You
out
did?
of them.
So you're chilling me because I'm a
And
music artist?
we
Wow,
learned
that's cool.
In that
Hey, buddy.
work, this was also
Did you get sucked in?
beginning with Brian and Dave Morrison, with many people. It takes a village. There were many people involved in this. But we learned
Wow.
how string theory can pull off this magic feat of describing an object which at once looks like an empty hole and a maximally complex object. So in some way that can be described with very precise mathematics, something is both incredibly complex and incredibly simple. When something gets very complex, it becomes simple again.
So with that, you gave the world really the first way of quantitatively analyzing the rearrangement of ingredients that, if put together in the right way, yield, in the right circumstance, a black hole.
Right.
So many
Philosopher
view
Chris
this as a kind of key moment in string theory because
Cool.
while it's not predicting an observable feature of the world that we go out and sort of directly measure,
Yes.
it is making contact with
Right.
a quantitative feature of the world that was already on the books for decades. And this is the first time that there was
Yeah.
a way of understanding it
How you
through
doing?
Right.
fundamental theory.
Right. So string theory
Nice.
found a
are you
solution to a problem that
Oh, I
had
did out front too.
been posed in a completely different field. Now, this
Young
solution
Samosas
that string theory has for accounting for all the gigabytes in a black hole, we don't know if the trick, it's the trick that is actually used by M87, black hole M87 that we just saw a picture of, but we didn't know there were any tricks. Now we know that there's one trick, and we're trying hard to understand if M87 uses the same trick that string theory uses. So we can extract lessons from string theory about the real world, and that's something we're working on.
Yeah, so this is now, as no doubt you follow the news, this is a black hole, a real one, that's what,
Yep.
55 million light years away in a different galaxy, M87, now observed making use of these radio telescopes that are scattered around the globe. Is
Yep.
it conceivable that we could use even more precise versions
Virgo.
of these observations to make contact with some quality of string theory that would be kind of iconic to it, that might actually single it out as the unique or among the few
Yeah, wow.
possible theoretical frameworks for understanding the observations?
Mm-hmm.
It's possible, and we're trying, to make a link between this picture and the ideas in string theory. And when we did this calculation in string theory, it was a very complicated calculation. A lot of mathematics, algebraic geometry, long, complicated calculations. At the end, we got perfect agreement, so we knew that we had done it right.
Perfect agreement with Hawking's formula.
Perfect agreement with Hawking's formula. So you could describe Hawking's formula as, going back to, you have a smartphone, you start putting
Hawking's formula, he's talking
gigabyte
about
photos into it.
Mm-hmm.
You put 16 of them in, and then you can't put any more in, and you deduce that your smartphone can hold 16 gigabytes of data.
Right.
You don't know how it stores the data.
Right.
That's what Hawking did. He deduced how much their information is in a black hole. What we did,
yes, I am a black hole.
String
Phosphor
theory,
Crispin.
where we have a lot of control over the equations, was pry the thing open, look at the bits, count them, and show that it agreed.
Mm-hmm.
Now we did it in a very complicated way, and as often happens in science, you start to realize that you can do the calculation in a shorter and shorter and shorter way. And ultimately, we realized that the key ingredient that enabled us to do this calculation was a special symmetry that these black holes have called conformal symmetry. And then we realized that some black holes in nature, ones that spin very, very fast, have this same conformal symmetry. And so probably we can understand the construction of what the chips inside it look like using the same ideas that we used in string theory. They haven't been able to deduce the spin of this yet.
No.
And we are trying to understand that. They will get a better image. We will understand the form of the image better. But we're trying to see if this black hole has that conformal symmetry, the same one that we used in string theory. And so we've written there's a chance that will work out.
Yep.
And there's a lot of black holes out there. There's, thousands or millions of them up there.
Really?
This is an image with only 16 pixels. I'm expecting that, this is the beginning of
this is the beginning.
Holes.
I am a black
This is
hole.
like not even a black and white TV. I'm hoping that we will get, high resolution images, and we will see many black holes. Some
high
of them
resolution?
we know are spinning at nearly the speed of light and have the conformal symmetry.
Mm-hmm.
And so we've made some predictions for exactly what
we do?
the black hole will look like, the detailed pattern of the polarization of the light and the shape of the image and so on.
Phosphor Crispin.
And in principle, this could
Black
be
hole.
seen, and it would be an interesting.
Right. So that is our prediction of what the polarization, the light that comes from the black hole.
You and me.
I did with Alex Lipsaska, Delilah Gates, and Dan Kopetz, what the polarization of the light will look like. If you were looking down the barrel, actually we're looking at 15 degrees, so it's actually an even more complex pattern.
15
But there's a
degrees.
very definite prediction. Now, this is not proof of string theory,
6.
but it is how science works. It works in
unexpected ways. And we're talking to the Event Horizon team about how to best set up the telescopes to try to look at this. And yeah, so
we're coming toward the end of the discussion. There are a couple other things I wanted to discuss with you before we conclude. So in part one, we spoke to Marcelo Gleiser about the general idea of unification and starting with Maxwell and electromagnetism and going ultimately towards string theory. And he mentioned this possibility that, you know, there are perhaps islands of knowledge and maybe there are limits to what we can ever figure out.
Yep.
In part two, we spoke to Mike Dine about trying to make linkages between the unification program and more, you know, bread and butter physics, particle physics, supersymmetry, things that we might actually see at the Large Hadron Collider. And that program has yet to be successful. Yes. So one way of looking at these sort of first two parts of the conversation is great try, but you're sort of not really getting there. In my conversations with you across the decades, you were one of the most optimistic.
Would you have said that to Columbus?
Yeah, what's that?
Would you have said that to Columbus when he came back? Great try, but sorry, I wanted China.
Exactly. No, so that really speaks to your optimism.
The Large Hadron Collider.
Clear to me over many decades.
I think it works.
But just to give a sense, where do you stand on your view of string theory? Is it not? Has it reached what you'd hoped it would by this era? Is it in some ways yes, some ways
Philosopher
no?
Chris Payne on Black
what's your
Hole.
prognostication going
What's
forward?
up, Brian? Sorry.
Well, so there's a view
Andrew
of
Stroman
the nature
here.
of physics that
Thank you.
perhaps started in the beginning of the 20th century. That progress in physics
They think I'm with
was
China.
about understanding things. It's called reductionism. Understanding, you know, molecules are made of atoms, atoms are made of
Reductionism.
protons
You
are made
reductionize
of quarks,
me?
and then we go down to strings. That's the reductionist program, but it's a really kind of one-dimensional view of what science is. And the original idea, which many
Reduce things? What? No. What?
but not all
You want to
people
produce
had,
results?
of what string theory was
Okay,
good
you got.
for,
Whoa, y'all
was it was
lost
the
me.
final
I'm a black hole. Philosopher Chris
resolution
Payne.
of the reductionist program. Now we knew what everything was. We found the strings. That's the end of it. Physics departments around the world can shutter their doors. You know, that's not how it works. You know, we keep exploring. We keep finding new things. Strings had to be explored. We're still exploring. We found other things that we didn't expect. We found out about black holes. We found out about holograms. We spawned new fields of mathematics.
Yep.
We, you know,
Who's we?
used to describe superconductors. You know, all kinds of wonderful things that we learned.
Huh?
And in fact,
Where's that come from?
I think that the idea that people were excited about back in 1985 was really a small thing, you know, to kind of complete that table that you put down in the beginning of the spectrum of particles, and then we could say, okay, you know, this is the last year of the World Science Festival. It's all done now. We've got, you know, string theory was really the beginning, and what has happened. So we didn't do that. We didn't predict new things that were going to be measured at the Large Hadron Collider.
Cristiano Ronaldo, the most
happened is so much
the
more
most recognizable person on the world.
Than
the most recognizable face in the world.
Right. That is,
whoa.
We learned in the process of trying to understand what makes up
whoa.
It turns out the interesting things were not the small things, but the big things. M87.
Oh, yo, Philosopher Chris Payne, yo, I remember last.
Notice it, and we don't understand it.
I recently just talked about the most famous people in the world, and Cristiano Ronaldo. I totally forgot, but I went to Madrid, Spain, and lived.
We've learned things which we sadly don't have time to go into about the nature of space and time.
Wow.
And quantum mechanics, and we're getting little hints of a radical new view of the nature of space and time, in which it really is.
You guys want to watch another one?
Approximate concept, and
He said yes.
Emergent from something deeper.
He said, okay, why not? Okay, I got you, bro.
Really, really more exciting.
Okay.
I mean, it's as exciting as quantum mechanics or general relativity.
Right.
Probably even more so.
What, Philosopher Chris Payne, the black hole?
Before we solve
this is what you're
the
excited
puzzles
about?
that you've heard about tonight, we will
This is
have
because I exert so much dark
a
energy. I
revolution
don't
in the
know.
way that we think about the universe, at least as profound as what was brought on by quantum mechanics and general relativity. And I would trade that
Apologize.
for a slightly lengthened list of elementary particles any day.
Elementary particles.
Great point to end on, man. That is spectacular.
Right.
Andy Strominger, thank you. Great
Wow, you
conversation.
guys are in a rush. Very
Thank you,
interesting. Apologize. Whoa. Yeah. Okay, guys, are you ready? Can you hear me? What?
Good afternoon, everybody. You know, we began the festival with a celebration of
April
the 100th
10th.
anniversary of the confirmation of Einstein's general theory of relativity, which was on the 29th, May 29th. And that moment in the history of science is a pivotal one, a beautiful one, because it really shows the optimum way for science to progress. We have a body of thinkers. In this particular case, it was just Einstein himself, but more generally, it's a community of theoreticians who use mathematics to try to figure out some deep insight about the nature of reality. But importantly, that insight needs to come with predictions. And those predictions then can inspire other physicists, either astronomers or experimentalists, to go out and try to confirm the prediction and see whether the mathematics is actually describing true aspects of reality. Now, for Einstein, it was a wonderful confluence of the mathematics and the technology necessary to check the mathematics, because he wrote down his equation of the general theory of relativity in November of 1915, and the observations that confirmed his ideas happened in 1919. So just 4 years between the theory and the observation. Oftentimes in physics, the timescales are longer. Theoreticians will come up with ideas. Perhaps they're difficult to test. Perhaps it will take building new equipment. Perhaps it will take, in fact, countries to come together to put their resources together, to combine their resources in order to even be able to build the machines necessary to test these ideas. And that is going to be part of what will drive our conversation here today. But whereas Einstein's ideas and his confirmation was all about sort of looking up into the sky, thinking about gravity, thinking about big things, the focus here will be on the other end of the spectrum. For the most part, thinking about small things, particles. because we have, you can really trace the history back thousands of years, asked ourselves
Are you really famous?
What is stuff made of? What are the fundamental ingredients? And we've thought about this over the course, really, of many, many centuries. But that program of trying to figure out the basic ingredients of matter really picked up in the middle of the 20th century. And it was a wonderful time where the theorists and the experimentalists really worked hand in glove, back and forth, playing off of each other.
Right.
And Steven Weinberg, one of the great scientists of our era, summarized the excitement in a really wonderful way.
It was a time when graduate students would run through the halls of a physics building, say, they discovered another particle, and it fit the theories, and it was all so exciting.
The tie.
Back and forth between the mathematical ideas
I'm a
that
physics
inspired
student.
the experimentalists to look for certain kinds of
presenting
particles.
it. I'm a black hole. I'm
phosphoric
Chris Payne.
The theorists would then update their equations with the new insights, and back and forth it went. And as this unfolding occurred, there was one sticking point, which is really going to be part of the focus of our conversation today, which is there was a very basic question. Why is it that these particles that were being found have heft, have mass?
Okay.
In essence, if you had one of these particles, fundamental particle in front of you, it could be an electron, it could be a quark, whatever.
Okay.
As you push on it, where does its resistance to your push come from? Where does its heft, where does its mass originate? And a mathematical idea was put forward that we will discuss in the 1960s by Peter Higgs and other scientists as well.
Okay.
And it was a strange idea to solve this conundrum because it required the universe to be filled with something that we physicists often refer to as a cosmic molasses, some stuff that would be filling space.
Everything's around us.
It came with the prediction that if you kind of banged on this molasses sufficiently in the right way, you could sort of have a little fleck that would come off, and that little piece of the molasses would be a particle called the Higgs particle or the Higgs boson. And on July 4th of 2012, if you weren't out celebrating and doing whatever we Americans do on
4th of July.
We're actually paying attention to something some of us consider to be much more important.
And I just graduated high school.
Press conference.
If we combine
the
ZZ and gamma gamma, this is what we get. They line up extremely well, and in the region of 125 GeV, they combine to give us a combined significance of 5.
Wow, 5. Is this steak? Hey guys. No way. What is this? Burn? How we did? No, that's a thing. What?
So the emotional gentleman taking off his glasses, wiping his eyes.
Who,
Bernie? You might guess that was, of course, Peter Higgs. The gentleman
Peter Higgs
was put forward in the 1960s, and about half a century later was confirmed through the observation of this Higgs particle. And of course, this excited the world. It was picked up by newspapers, television shows around the world, because this is again one of those iconic moments in the history of deep understanding. But at the same time, the discovery of exactly what we expected to find based upon the mathematics raised a certain kind of challenge, which is what's next? And that's what we are going to have a discussion about here today. And we have some of the world's leading thinkers on these ideas of particle physics, so let me now bring them out to you. Our first participant this afternoon is a theorist at the Institute for Advanced Study, a member of the National Academy of Sciences. He was an inaugural recipient of the Breakthrough Prize in Fundamental Physics. Please welcome Nima Akarni-Hamed.
Nima Akarni-Hamed, hello.
Also joining us is an experimental high-energy particle physicist working on the ATLAS detector at the Large Hadron Collider at CERN. Please welcome Monica Dunford.
Monica Dunford. Hello.
All right, finally, please join me in welcoming
Those
the
seats are
Deputy
comfortable
Director
or
of
what?
Research at the Fermi National Accelerator Laboratory. He's a fellow of the American Physical Society and the
Whoa,
American
American
Association
Physical
for the
Society.
Advancement of Science. Please welcome Joe Licken.
Joe Licken. Joe Licken. Hello. Wow.
I've known all you guys for
Brian.
many years, probably known Joe the longest of all. I think we probably go back 30 years.
Yeah.
But whoever wrote
Whoa.
my little notes here
No way.
probably didn't know that fact because they have told me that your name is pronounced Licken, just like finger licking good. So I think I would have gotten it anyway, but I appreciate that as well. So let's begin
Cringe.
the discussion by just going way back for a moment.
Oh,
Way
Brian,
back
you're
to,
savage.
ancient Greece, when there were thinkers who began to ask the question, what
You're humble.
is matter made of? What is the stuff around the world
Joe
made of?
Licken.
So we have this fellow right here. So Nima,
Hello.
who is this and what role did he play in your mind?
This is Mr. Democritus. Apparently, I don't know how we know he looked like that, but anyway.
Democritus.
Now, Democritus is widely credited as being the person who suggested that the world is actually made up out of atoms, that matter is made out of some fundamentally smallest building blocks.
And just tell us your view of that.
I think he's the single most over-credited individual in human history, okay? Because there's absolutely no evidence one way or the other whether this idea was right. You're just sitting around in ancient Greece. Hey, you think matter, you keep cutting it up, it goes all the way down forever? I don't know. Yeah, I do. No, I don't. And, there's absolutely no reason to believe either one, either way. The guy who said that it stops somewhere, he's famous for 2,500 years. It's not fair. It's not fair.
Just along those lines, let me ask you one thing, though. So we certainly tell our students, and I think it's a real truism, that asking the question is oftentimes as important as finding the answer. So perhaps maybe it's worth crediting him with at least thinking about the possibility that this is a worthwhile question to investigate.
I would agree with that.
What was the question?
What you said is true, but I'm not a historian of science, so I don't know.
Good. So the idea that he had, of course, was presumably you take a piece of matter and you start to sort of pound on it or cut it up in some. We have an example here is a rock.
Yep.
And so what have we found in the past, 2,000 years? If
2,500?
we start the journey with Democritus.
Yeah. So I think
Democritus.
A little over 100 years ago, in the mid-1800s, I guess chemists, or back in the time when there was not such a distinction between the different physical sciences, but anyway, people started suspecting that there might be atoms, that ultimately different kinds of material were made out of different sort of building blocks. We had the system of the periodic table of elements and so on. And already back then, there were people who were skeptical that you were talking about these teeny tiny things that no one can actually see, but there started to be more and more indirect evidence that
right now you can
atoms
see
actually
me.
exist.
I'm philosopher Chris Payne.
See them
Oh
in
no, I
various
remember
ways,
I've listened to you
directly.
before too. No
But
way.
that's where the sort of journey began, that big hunks of matter are made out of molecules, or in turn collections of atoms. An atom is maybe a 100 millionth of a centimeter across. So it's very
100 million.
very, very small. But then the atoms themselves were built out of other constituents. We have the electrons that you probably all heard about in school that were around the nucleus of the atom. The nucleus of the atom, in turn, is around 1 million times
And you got
smaller than
black
the size
hole.
of the atom itself.
Philosopher Chris Payne.
So these kind of pictures are not really to scale, right? The nucleus is around 1 million times smaller than the atom itself. And then we go into the nucleus.
I consume
we see that
everything. You're
the
talking
nucleus is made out of
gibberish.
particles like protons and neutrons.
Whoa,
which are
protons
now
and
around
neutrons.
10
Interesting.
to the
Wow.
minus 14 centimeters big. And around 50, 60 years ago, we started peering inside gradually. These apparently elementary objects, protons and neutrons, that turned out not to be elementary at all,
Right.
and built out of still more point-like constituents. So that's where the journey has been taking us.
Quarks.
In this, at least in this building blocks of matter perspective on what it is that we do, and hopefully we'll come back and talk about some other perspectives on what it is that we actually do. But anyway, in this very fundamental aspect of what we do, that's the journey that we've been on. We're now at a distance around what we're probing at the largest experiments
Higgs
in the world,
boson.
like the largest accelerators in the world, like the Large Hadron Collider, are distances around 1,000 times smaller than that. Right. That's 1,000 times smaller than the nucleus of the atom. And there's a lot of drama that has unfolded there, and
So let's actually talk a little bit about that. So Monica, when we show a picture, as we began there, with whatever, a sledgehammer smashing into rock, it suggests the most brutish way of figuring out what's inside of matter. You just sort of smash it apart and see what the constituents. It's like a 5-year-old just smashing things together to see what's in there. Is that what we do at the Large Hadron Collider, or would a more refined way be to make use, say, of E equals mc squared, sort of the most famous of all formula? So, you know, are we using energy to create stuff, or are we just sort of smashing things to bits?
I think pretty much it's one and the same. I think it's just a question of whether or not you want to speak elegantly or not. So yes, I mean, in essence, what we do is we take two things and we smash them together. And what we want out of that, of course, is a lot of energy, right? Out of any collision, you want a lot of energy. And
I agree.
As Einstein says, energy is equal to matter, and so
you
therefore we can
me?
produce
I'm joking.
heavy things, and that's our goal.
No,
but
not even.
Part of that, and the point which I
no, I didn't even mean that, Brian.
Was if you only are smashing things, you're only going to find the stuff that was literally there. Whereas that's not quite what we do.
No, that's not exactly. That is absolutely not what we do. It's sort of like it would be more as if you took two, let's say, cheap cars and you smashed and you got yourself a Ferrari. Right, that would be more the equivalent of what we're doing.
Yeah,
exactly. You're really creating something new out of what you had, and what you had is now no longer.
Right.
And you've got this elegant, hard to find status symbol that you're really looking for.
Yeah.
So that is more along the lines of what we do.
So
Very
from
good.
that way of looking at things, energy is sort of the basic currency
Sounds
from which
cool.
you can buy the status symbols.
Exactly.
That
Energy
you're
is
looking
money.
for.
Absolutely.
Right.
Energy is money in our case.
Right. So the more energy you have, the more options you have for the things that you can buy. Or if we get off this metaphor, which perhaps is a good idea. Yeah, that's on. I know, exactly. Yeah. I didn't know that's where we were going. The greater the mass of the particles that you're able to create through these collisions.
So the idea behind any sort of what we would call frontier collider is that it needs to be as energetic as you can buy, really, literally. Again, we want it big, you want it powerful, you want tons of particles, you want tons of energy, you want it all.
So the most powerful collider of that sort that we have today, I gather, is where
the Large Hadron Collider.
Work. So
the Large Hadron Collider.
So give us some sense of what it
versus
can do and
Philosopher
the
Chris
energy
Payne.
that it has and so on.
So the Large Hadron Collider, it's in a tunnel that's about 27 kilometers.
Okay.
Located near Geneva,
Whoa.
Switzerland, in probably some of the most expensive real estate in the world. So
wow.
probably, in future colliders, well, you wouldn't have designed in Switzerland now, let's say. But it's where we have it. And the idea is you've got two protons that are running around in this ring in opposite direction. They're being accelerated by superconducting magnets. They are, getting to very, very high energies. Energy is currency here, so the higher the better. This one runs, 13 TeV, soon to be 14. And then you collide them together. You have a tremendous amount of energy in that collision, and you basically build this gigantic detector. We have 4 such detectors. You build these gigantic detectors around that collision point. The Atlas detector, which is the detector that I work on, is a 5-story building, so it's humongous. And that basically takes a snapshot of the collision. And the collision is messy. It's not like, a couple of particles here or there, right? I mean, it's
so how many protons are in these bunches that are slamming?
So in the protons, you have many, many protons in the bunch. So the beam is not a continuous beam, as you might think. It's not like a stream of protons that are coming in.
Wow.
The beam is designed such that you have like little packets of protons, 10 to the 11 around.
Wow.
And you have these little packets of protons, and they're kind of colliding every 25 nanoseconds, which means that it's like your detector's a camera, and it's taking pictures every 25 nanoseconds.
Right.
So 40 megahertz speed. And these collisions are so big and they're happening so often that we actually cannot record all of the data. And we have to make a very difficult decision quickly within a microsecond about whether or not this event is interesting or not. And this is a very challenging thing for us experimentally, because if Nima comes to me a year from now and he says, oh, you know what? I think I saw a new signature. It'd be something totally different, like this. And if my trigger system makes that decision, wasn't or couldn't,
4 sneezes.
the data's lost. I didn't record it, so I can't go back to the data and say, I can look for that.
So theory really guides the experimental approach. It's not as though you approach it as a blank slate and say, let's slam these things together and just see what happens.
Well, absolutely, and it's also a very difficult challenge experimentally because, on one hand, you need to be ready for everything. Mm-hmm. Your detector cannot record everything, so you can't take everything. So you want to be ready for everything. However, you need to have made a decision. So you need to sort of have some sort of idea about what you're looking for. And to get that idea of what we're looking for, then yes, of course, we rely heavily on theory to tell us that, because otherwise
you're at sea.
We're at sea. Yep. We're absolutely at sea.
So Joe, you, of course, also have spent your career working at a facility that undertakes these kinds of experiments as well, Fermilab. And over the course of decades, both through collider experiments, but also through other kinds of experiments that we won't go into in any detail, cosmic ray experiments and other things of that sort, we have built up what we think may be the fundamental ingredients making up at least the stuff that we interact with in an everyday sense.
Yes.
And that's the standard model of particle physics. So I just wanted to go through the particles that were predicted and ultimately found, giving us our most complete understanding to date of what things are made of. So in the early days of looking for particles, maybe you can just sort of take us through some of these particles here.
So that's a familiar one. Electrons, everybody knows electrons, everybody knows photons. The muon was an example of a particle that wasn't predicted but was discovered, and we still don't know why they exist, but they are also fundamental particles similar to electrons. Neutrinos even stranger. We know they exist, but they're very different from the particles that you're made out of. But that's one of the things we're still trying to figure out.
And they have no electric charge?
They don't have any electric charge. They're very difficult to detect, and they're very different from other particles. Quarks, Murray Gell-Mann, who just recently passed away, invented the idea of quarks. You are made out of actually only 3 of these particles, the electron and 2 of those quarks, the up and down U and D quarks.
Yep.
That's what I believe. That's
My
what
favorite color is yellow.
But there are more quarks. There's the strange quark you see there was discovered later, and charm quarks, bottom quarks, top quarks were discovered at my laboratory, Fermilab. We're very proud of that.
And what year was that?
That was in 1997 with what was then the world's biggest particle collider, the Tevatron, before the LHC. And we don't know why there are so many of these elementary particles. There's way more than you need to make us. So that's one of the things that's still a big mystery, and we don't know why they're so different from each other.
Gluon, I'm gonna glue them together.
We have some ideas for that, but it's part of the big mystery of this whole picture of the Standard Model is why is it so complicated in some sense, and also why is it so simple? There are simple principles that hold it together.
Whoa, tau
so we see here
what
2
drives me,
collections
because
of
I'm a
particles, if you will.
neutrino.
The ones
I'm
on
a black
the green,
hole.
On the far right hand
Philosopher
side,
Chris Payne.
are distinct in a fundamental way from those on the left hand side. Can you just
They
draw
are.
that distinction for us?
So the particles that you are made out of are called fermions, and so we talk about matter particles. Particles are fermions, and they're one of the ways of distinguishing them is that they carry a little unit of spin, which is not really spinning around like balls because they're point-like particles, but they carry a little bit of spin-like angular momentum. So you're made out of fermions. On the other hand, the forces that hold you together and hold the universe together are carried by these bosons, these green particles, of which the photon is the most obvious example for electromagnetism. But the gluon and the W and Z also carry fundamental forces of nature. And those are particles that have a different spin. They have a spin that's actually twice the unit of what fermions have, and they're called bosons. And they behave very differently. They behave like forces instead of behaving like matter.
Sorry, guys.
Now, Nima, so when we actually begin to look at the mathematics behind this, one of the curious features that people recognized, even before the theory was fully in place, was that it was challenging to give mass to these particles. And it's challenging to describe why it was difficult to give mass to these particles. I'm going to ask you to try to do it.
Oh, it's a piece of cake.
Yeah, good.
What is mass?
It's actually a piece of cake.
What properties are you
fact,
describing?
What we're about to talk about is a very large part of the conceptual drama of
Philosopher
the 20th
Chris
century.
Payne. I'm dramatic, yes.
Physics, and we're just going to have to count on our fingers a little bit.
Fingers.
Maybe before getting to it, I just want to make one just general comment about this picture. Is that
okay,
you
sorry.
might, and it's echoing something that has been said a couple times already. On the one hand, it looks a little bit complicated. It's not the most complicated thing you could imagine, but there's many particles, and it seems a little haphazard and random, perhaps.
Right.
But one of the aspects of our subject, I think the deepest aspect of our subject is that all of these things are somehow completely governed, and their properties, the broad properties, are almost entirely dictated by big general principles. These two revolutionary principles in the earlier that we learned in the early part of the 20th century of the laws of relativity and of quantum mechanics. It turns out that these laws are almost incompatible with each other. It's not at all remotely obvious that you could come up even with toy universes that were compatible with the principles of relativity and of quantum mechanics. But you just barely can, and if you hand sufficiently competent theoretical physicists these laws and lock them up in a room and refuse to let them look outside and just say, what could you come up with that's conceivably consistent with these principles, then this is the kind of thing that comes out, in a sense, out of pure thought. Once you put in, of course, these two big facts that we've observed experimentally, that relativity and quantum mechanics are both true.
Whoa.
And a very big aspect of this, and a very big reason why it's so constrained, is exactly this business about the difference between being massive and being massless. So let me try to,
yes, thank you, sir.
We just talked about the photon. And as Joe mentioned, one of the properties that the photon has is it has a little spin. If you're familiar from just thinking about light as a wave, sort of classically as an electromagnetic wave, sometimes we talk about it having polarization. Okay, it can spin around one way, it could spin around the other way. Well, what's really going on, the underlying photons that make up light have a little spin, so they can spin either in the directions they're moving or opposite to the direction they're moving. And this is a crucial fact, that they can spin in two directions. Now, the other particles, like the W and Z particles, they're sort of massive cousins of the photon. But the mass is not a tiny correction. You see, if you're very naive, you would think, especially when we go to these huge accelerators, we smash particles into each other at incredibly high energies. Surely, when the energies are enormous, you can kind of ignore their mass, so that the E is so much bigger than the M, so that you could really just basically ignore the mass, and you can, and at incredibly high energies, you can think of the mass as a little tiny perturbation and just talk about massless particles. But it's not true. It's not true, because massive particles that have spin 1, that have spin twice the spin of the electron, we say it's spin 1, like the W and the Z, they have 3 ways that they can spin, while the photon has 2. And what's this difference between this 3 and this 2 is no matter how quickly this W particle, let's say, is moving around, you can always catch up with it. You can always move and catch up with it. And let's say it was spinning up this way. Well, by tilting your head, you could see it spinning that way or the other way as well.
You can catch up with it because massive, it's not going to.
Exactly. That's right. That's the crucial point. Because it's massive, no matter how quickly it's not moving at the speed of light, and so you can catch up with it. Whereas the massless particle, like the photon, is moving, zipping around at the speed of light. You cannot catch up with it, and therefore you can't play this game where you tilt your head and see it spin in in all of the 3 possible directions. In fact, all you can do is conclude that it's either spinning in the direction that it's moving in or opposite to the direction that it's moving in. This 2 not equal to 3 business is really profound. Okay? It means that you can't think of mass as just a little correction to things that are massless already. And in fact, precisely because of this point, if you attempt to describe the possible composition, types, and interactions of massless particles, then it's essentially a mathematical theorem. It follows from following from the general physical facts about the presence of both relativity and quantum mechanics. But the types and interactions of massless particles that you're allowed to have to come in a minuscule variety. Okay? The menu of particles that you're allowed to have that can interact in a way compatible with the principles of relativity and quantum mechanics are the following. The particles can have spin 0, 1/2, that's the unit that the electron has, just a convention. So 1, 3/2, and 2. That's it. That's all you can have. Furthermore, there can only be one of those massless spin 2 particles. So we're not going to talk about it much today.
It's
we can only have one of them, and if you study its properties that are sort of forced on you by relativity and quantum mechanics, you would find that it makes massive particles go around in orbits and so on. It's gravity, okay, and all the properties are sort of dictated by these basic principles of Einstein's special theory of relativity and of quantum mechanics. Then The spin 0 particles, okay, you can have as many of them as you like. The spin 1/2, you can have as many as you like. The massless spin 1 particles have to have very special properties and interact with each other in very special ways. You can have massless spin 3/2 particles. They have to be even more special. We might come to that later. And as I said, the massless spin 2 are associated with gravity. So that's it. There's this sort of tiny menu of possibilities that you're allowed to have. And nature is making use of that menu as far as we can tell. So we've seen of this set of possibilities before July 4th, 2012, we had seen nature make use of some of these possibilities. It had used particles of spin 1/2, particles of spin 1, and of course the spin 2 associated with gravity. One of the most exciting and important things about the Higgs is it's the first example of an elementary particle that has no spin at all that we've ever seen. So that's been added to the mix.
Wow, you are welcome.
The reason why the Higgs had to be there is that something has to account for this 2 not equals to 3 business. Okay, something has got to explain where mass comes from, not merely to add this number, the actual mass of the particle, but to account for this extra stuff, this extra spin ways that the extra ways that things can spin when you give spinning particles a mass.
Listen.
And that's the entire story of the Higgs, is to account for that for the origin of these extra degrees of freedom.
Now that's quite a piece of cake.
Yeah,
right.
Right.
I mean,
right. Well, but it is all just about counting.
Yes.
It really is all
Yes.
just about this 2 not equals to a 3 business.
So with that as a preamble to the motivation that you had to have something fundamentally new added to the story, Monica, can you take us back to the 1960s when Peter Higgs and others who shared the Nobel Prize with him as well, and Glare and so on, what was the approach that Peter Higgs took to add this crucial, profound new ingredient that would fix up the 2 not equal to 3 puzzle that Neem articulated?
Well, so Peter Higgs postulated the Higgs particle. And, well, I wasn't there in the 60s, so I can't really tell you a whole lot about exactly what was going on when that was. But it was a pretty revolutionary idea. You know, we were stuck in the 60s at this point where we needed to, you know, you had suddenly in the 60s this huge explosion of particles, right? Suddenly, I mean, the 60s was this period where it was like every week, essentially, new particles were being
What do you mean?
Not maybe elementary particles like quarks and you know, muons, but more like we were seeing mesons, which are combinations of 2 quarks, or hadrons, which are combinations of 3.
Sheesh.
And, you know, every week. And so suddenly our kind of picture of what the world went from very small, you know, what made
You
us up,
telling
to
me?
a whole fleet of particles that didn't really seem to fit into anything. We didn't really need them. Why?
You telling me?
Why suddenly all of these extra particles? And certainly, you know, how do they all fit together? You know, what's the bigger picture? And then also, as you said, what gives them mass?
Yep.
And so Higgs was, you know, part of that, which was sort of to say, well, postulated that there was the actual, and what was unique about his paper was that he postulated that there was the actual Higgs particle.
Yeah.
And that it could be something that we could then discover and detect.
So Joe, tell us about, so the Higgs particle is a key part of the story. Tell us also about the Higgs field, which ultimately is a key part of getting a sense of how particles acquire mass in this new
So you
idea.
mentioned this phrase, cosmic molasses, which
Yeah.
I think is as good a way of picturing it as anything else. But it's really a daring idea,
Like
right?
in-
You're saying that all of space, the whole universe is filled with this cosmic molasses whose effect
like
is
'em.
to give the particles that we're made out of and other particles mass. So that's a really daring idea. And in fact, Higgs's original paper on this was rejected for publication. It was considered a little
So
bit
crazy.
little too
I mean, what
wild.
we're seeing right here, and in fact, we can probably play this again.
The
So
Constitution?
these are, the dots here are meant to be the
Yes,
molasses
that's
that,
what-
that
yes.
you're referring to. And then one of
The
these
Bible?
particles is meant to be massive,
Torah?
like the photon, I guess, and the bottom
Right.
one is meant to be massive. So what's happening to the guy on the bottom?
So if you're an electron and you're moving through the molasses, you'd like to move at the speed of light like a photon. And the only thing that stops you is the fact that there is a Higgs field everywhere.
Of mass?
And you can't avoid it. On the other hand, for the photon is not interacting, at least directly, with the Higgs field, and so it just zips through the speed of light. And that's the difference between those particles.
So for this
difference between
crazy
what
sounding
particles?
idea to be true, we'd have to accept that empty space is not empty, and it's not even a quantum mechanical notion of fluctuating fields that people may have heard of. This is just, there's actually a something there permeating all of space. Obviously, it's invisible, because we don't see it. It's tasteless, right? Like when I move my hand, am I touching it in some sense?
You are interacting with it all the time.
Yeah,
because
dude.
part
Look
of
at that
the
body
resistance
language.
I feel that if I move my hand would be the electrons and the quarks in some sense moving against
karate.
this molasses. So it's,
Wow, are you
it's a
fit?
far out idea.
Everybody
He
looks
puts forward
healthy.
this
I mean,
paper, and it gets, as you say, rejected.
I'm just appreciating
Now,
guys, molasses.
Many of us, if we have a paper rejected,
Philosopher Chris Payne, I'm a
we
black
kind
hole.
of back off. This is not what
sucking up
Higgs
to him
did,
in a way.
right? He
I
actually went
apologize.
around and lectured on this and
That's correct.
proselytized and discussed this.
Mhm.
And ultimately, I've said it before, but when I was a
And
graduate
made
student
money,
and
probably?
first learned about these
And
ideas,
did stuff?
the
Like
class that I
what?
took, the professor taught it with such certainty that I had no idea that the Higgs was a hypothetical idea. There was a time in our community, by probably the mid-'80s,
Yes.
early '90s, it was almost a foregone conclusion that this crazy mathematical idea from the 60s, which had now somehow permeated the consciousness of particle theorists around the world, that it was right. But still, you gotta try to confirm it. So we start to look for it through these kinds of collisions. So,
Whoa.
Monica, I guess you were
Pick
you were
me.
there when this was actually happening.
Whoa,
so
you met me. So you got sucked in
What was it like,
to the
and
black
what
hole?
exactly were you looking for in those collisions?
Wow.
Well, in the beginning, it was very intense. I mean, at first, when we first turned on the accelerator, we weren't really thinking about the Higgs right then. We were thinking about, my God, please let it work. You know, I mean, it was
Okay.
15 years to build this detector. You're working on collaborations that are 3,000 people. The days leading up to the start of the beam, no one was sleeping, and so forth. And so I think in the
Whoa.
beginning you were more concerned with the
3,000
technical
people?
challenge, and the Higgs was sort of a
That's
far
lies?
off dream. And we
Or did
certainly,
you false that?
at that time
Release
when we
that
first
maybe
turned
not.
on the
America?
accelerator
Huh.
and also just collecting up the data.
That's just
we-
shady.
You've got a brand new detector. It's 5 stories tall. It involves millions of electronics channels that all need to be understood and
Wow,
calibrated
right,
and
yeah.
so forth. And the Higgs.
No way.
I remember people always saying to me, "Oh, when are you going to
5
discover the Higgs?"
stories,
There's,
3,000
you know,
people?
like
That
me,
sounds
when
small.
are you going to discover it? And I was like, give me
How
5
big is it?
years.
When
I've
you
got
see
to
it?
discover. I've got to figure out this detector. We've got to collect enough data. And so I think for us, we were really amazed, maybe very happy with ourselves at how fast the discovery was made, actually. I mean, no one was predicting that we would have discovered the Higgs in 2012.
The Higgs ended up in a particularly nice spot.
It did. It was very nice.
Higgs in
spot for us.
2012,
It's
January,
very-
July
When you say
4th.
spot, you mean its mass, presumably.
It's mass, and therefore, because of its mass, it has the maximal possible ways in which it can decay. The Higgs.
So how do you find it? So you smash these protons together. What happens?
Smash these protons together, you get a lot of energy, and
Yep.
in that energy, you produce your Ferrari, which is your Higgs.
Yep.
The Higgs then decays.
Ooh.
It falls apart.
It falls apart.
Not exactly a Ferrari. Then.
Yeah, well,
Yeah.
so the Higgs falls apart, and Higgs will fall apart to. It prefers to couple to mass, which means that it prefers to fall apart to the heaviest things it can.
Yep.
So depending on the Higgs mass, if the Higgs is extremely massive, then it will prefer to fall apart to 2 top quarks. If it's at 125, which is where it's at,
125 times the mass of the proton.
exactly, 125 times the mass of the proton, then it falls apart. Then it can fall apart in a whole bunch of things, which is, in essence, an experimental dream, right? Because it means that it can fall apart to 2
If I
Z
malnourish
bosons,
myself
and
till
you can look for
125
the
pounds.
decay of the 2 Z's. It can fall apart to 2 photons. It can fall apart to 2 W bosons, and so you have
Whoa.
a variety of different ways that experimentally you
Wow.
can test, and that for us was really key because it
Whoa.
allowed us to be able to say, okay, I looked at the decay of the Higgs to 2 Z's. I see exactly where it should be. I looked at the decay of Higgs to 2 W's. I see exactly where it should be. Because from an experimental perspective, we never actually measure the Higgs.
Right.
We never measure the Higgs. So all we knew at that time was we had measured something new. Whether or not it was the actual Higgs boson, we then had to compare the rate of decay to 2 Z's, the rate of decay to 2 W's, of which the theory, once you know its mass, is predicted.
Makes a statement about
Yeah,
it.
exactly.
So if there's an
Philosopher
announcement
Chris
on like
Payne.
July 4th,
I'm a black hole.
when did you know that you had it, or when were you fairly certain that you had it? Is it months before? Is it 6 months before? Or the day before?
You
Had what?
I mean, statistics is such that we were collecting data, and if you see some sort of statistical signal, you should expect that as more and more data, the size of the size of your Higgs peak, let's say, starts growing and growing and growing.
Higgs peak.
But that's not actually usually how we
Foster Chris
data.
Payne, I'm a black hole.
We usually get it in chunks, even though the accelerator is kind of working continuously over the day. We have to calibrate our detector, and we tend to. Data just kind of comes to us in chunks. We'll do this calibration, try to understand it. Okay, that's chunk A. We'll do this calibration, that's kind of chunk B. So we're kind of looking at it kind of in chunks at a time.
Chunky.
And because a false discovery is worse than death, let's put it that way, death would be better.
People won't keep making fun of you forever.
Yeah, I know. So a false discovery is,
Right.
Yeah.
So you're going to do anything that you can.
Anything. What we oftentimes do is we blind the data from ourselves.
Right.
So we
At
will
CERN?
we will do the entire analysis chain where we have, and we can do blinding in a variety of different. There's several strategies, but what it means is either we withhold from looking at a particular data, or we screw with the data such that we can't actually get the right answer. And we make sure that everything is correct, our calibrations, our analysis selection, so forth and so on, and then we unblind, and it's extremely stressful. That moment where it's a collaboration of 3,000 people, and then they agree to unblind, and someone hits you got a computer program, someone starts it, you're watching the data being processed, it being processed, you get the plots.
Yeah.
Is it there? Is it not? Is it there? Is it not? I mean, so it's.
What plot?
In that sense, it was semi-instantaneous.
Yeah, but that's sort of an amazing moment. And now that you have the Higgs, and we're going to now turn to the question of going beyond this major discovery. You were actually at the World Science Festival about, I think it was
3,000 people
10 years ago, having a conversation prior to the discovery of the Higgs. And I thought I'd just show you a little clip from that, if you don't mind. So can you just run that little...
The worst scenario, as far as I'm concerned, would be that the LHC sort of completes the standard model and doesn't do anything more. So in the standard model as it stands, we need this cosmic molasses that was mentioned.
Whoa.
We don't know what it's made out of.
Wow.
The simplest idea is that it's made out of one new particle, this so-called Higgs particle.
Mm-hmm.
And that could be true. And
wow.
You've accounted for the missing ingredient of the standard model, and that would be it. And that would be
I remember this guy.
Horrifying. Monica?
Well, I think there's pretty much two scenarios where I would end up at McDonald's. And that is that if we discover the Higgs and the Higgs only, which is Frank's worst case scenario and also mine. So far, every collider experiment we have is really, has predicted this, and we measure it. Standard model predicts this, and we've measured it. Standard model, and so
success is our curse.
Yeah, success is our curse, exactly. And so I think from the experimental perspective, we're really sick of the standard model. So to just continue to measure the standard model, which would be a Higgs and Higgs only scenario, would be frustrating.
So you said.
Philosopher Chris Payne.
So at the
Sorry.
I'm going to have to start working at McDonald's.
That's right. So at the beginning of the clip, you said there's a scenario you'd wind up at McDonald's. You're not at McDonald's. So I'm assuming that in the second part of our discussion, yeah, exactly. So let's think about
I'm right here
how we go
with you
beyond
guys.
and how we've tried to go beyond these ideas. And to sort of start that discussion, Nima, you pointed out that the standard model has a sense of both simplicity and complexity, sort of depending on how you look at it. And we were looking at it just graphically with
I'm a
the
black hole,
particles
philosopher
arranged in
Chris
nice little
Payne.
rows and columns. If you actually look at the equations underlying the standard model of particle physics, you just write them all out. This is what the equation looks like.
You brought it up already.
Which certainly has a sense of complexity associated with it. It's sort of hard to imagine that,
What is all that?
After, a certain number of days and nights, the Lord simply said, let there be the standard model Lagrangian, So
Lagrangian.
now you can also say,
Let there be the standard model Lagrangian. The Lord said that?
This
No.
is the most naive way of writing out the
Who
equations.
channeled
And
that?
what we have found over the course of many decades is that symmetry is sort of an important way of being able to repackage our understanding in a way that really simplifies and allows us to shine a light going forward. So Joe, can you say a little bit about symmetry?
Sure.
And how, for instance, it helps us to understand this better and illuminates the path going forward?
Yeah, so symmetry, of course, is something we're familiar with in everyday life. Snowflakes have interesting symmetries. A diamond is a good example of symmetry in physics. You know, what's the difference between a diamond and the graphite and the pencil? They're both made out of carbon, but the difference is that diamond is in a beautiful crystal lattice symmetry, and that's what gives diamonds its special properties.
That's your opinion.
So symmetry in the physics world, it controls the physics properties of the things that you're talking about. So this happens in the subatomic world as well, and when we're talking about symmetry in the Standard Model, we're actually talking about principles that control how the Standard Model works and actually make it much simpler than it could otherwise have been. And that's why those complicated equations can actually be expressed almost in words in terms of a few symmetry principles.
In fact, you can even use that symmetry to put those equations on a coffee cup, as has been done.
I think it's worth really stressing that these it's a kind of an unusual sort of symmetry that we're talking. There are some important differences. We don't have time to really get into it, but but this very simplicity and the fact that there's a certain kind of symmetry that is useful for theorists to describe this physics has everything to do with this 2 not equal to 3 business. It has absolutely everything to do with the fact that we're only allowed this tiny menu of elementary particles when they're massless.
I apologize, sir.
That mass is a big perturbation. So trying to describe massless particles, which we think we should be doing in some approximation when we go to very high energies, that's what forces you to these incredibly simple, compact-looking formulas. And these formulas are really directly reflecting the underlying principles of space-time and quantum mechanics that govern everything. So it's there's no real veil between these remarkable simple formulas and these grand underlying principles of 20th century physics.
And to draw the connection to Higgs and others who were working along the same lines in the 60s, one way of describing what they found was a powerful way of including mass in a manner that didn't spoil the beautiful underlying symmetry.
In fact, I would say that, I mean, this
spoil
molasses analogy is it's probably the sort of best metaphorical analogy that one can use. It raises various questions that probably occur to you if you're a kid in the audience. You know, is this like the ether all over again? You know, physicists don't learn anything. They're so dumb. You know, didn't you not have the ether? You had the ether 100 years ago and it's gone now. Well, all we can say is that this is something, but it's not like the ether. It sounds like ether, but it's not like the ether. And,
what? What are you
I
even talking about?
The most fundamental way of saying what the Higgs is about, the way that people will still be talking about in 200 or 300 years after maybe robots have come up with better metaphors and analogies, is that
analogies.
Is sort of precisely what Brian
Walk
just
with
said.
me, I'm a black hole philosopher, Chris Payne, dude.
Particles is completely prescribed and sort of fixed by general principles
Keep moving your arms heavy.
Space-time and quantum mechanics. The world around us appears to have massive particles in it. And so you have to somehow take the stuff that you see that's slow and massive and low energies, and as you collide them at higher and higher energies, be able to continuously interpolate to a world with massless elementary particles smashing into each other at very high energies.
Interpolate?
And if you just finish this counting that we talked about, you went through it a little bit more detail, you would find that you just can't do it with the elementary particles that we knew of before the Higgs. You just had to have something else in order to take the massive low energy particles and interpolate them to massless high energy ones. The incredible thing, and this is part of the sort of cognitive dissonance and the real irony about the Higgs.
How's that a word?
You just described it, for example, as something people knew had to be there for 50 years. You know, so it's very amazing that people predicted it, but it's sort of boring that it's the thing that we expected all along. But it's in fact something. It's actually quite shocking.
Most of the world. What are you doing?
It's quite shocking that all it took was one stinking little elementary particle. Just one extra thing was needed to allow us to be able to interpolate smoothly and continuously between this world of massive particles at low energies and this very sharply prescribed world of massless particles at very high energies. And it's shocking that it was so simple. That's the irony about the Higgs that we'll come to, is that nowhere else in physics, when this rough type of phenomenon happened, did anything remotely as simple as the Higgs happen. And it's a feature of a mysterious feature of our world that the simplest possible answer ended up being right.
So along those lines, as we've tried to push our understanding of the world further using this idea of symmetry, particles that in some sense are the different tips of the snowflake, to use Joe's metaphor, that can kind of be rotated into each other in some sort of abstract sense, we have come upon other symmetries, mostly from mathematical studies, not really from observations of the world. And the most prominent among those is supersymmetry. Yes. So can you tell us a bit about supersymmetry and what it implies for what we should find out there in the real world if nature abides by this particular symmetry?
So supersymmetry is actually an idea that relates not the tips of the snowflake, but it actually relates the kinds of particles that we said we were made out of, these fermions of matter particles, to the bosons, like the particles that carry forces. So that's sounds like a very profound relationship, and it is a very profound relationship. Okay. It was first noticed by a bunch of physicists in the 1970s, and immediately got the whole community that we belong to excited because it sounds like it's a theoretical breakthrough. It also makes predictions. It predicts a bunch of new particles.
Now, the way you framed it, let me just say, the way you framed it was, it takes the particles that make us up and it relates us to the particles, say, that make up light, like the photon.
Yeah.
That sounds very economical.
Yes. It's not quite as economical as you might have thought because, for example, the electrons you have in your body are related to a boson in supersymmetry, but it's not the photon, and it's not any of the other bosons you showed on your chart. It would be a new particle. We call it the selectron.
In fact, I think you see it up...
that hasn't been discovered yet.
Yeah.
The selectron.
So in that sense, it doesn't sound economical because it's postulating a whole bunch of new particles that nobody had seen. On the other hand, there's a historical analogy for why this might be reasonable.
That's so
which
cool.
goes back to what Nima was talking about, was the early days of quantum mechanics, when we were trying to understand how quantum mechanics can be made compatible with relativity. And as Nima said, that is a very, very difficult mathematical understanding, which was, part of it was first put together by Paul Dirac, one of the great giants of our field. And he found in making that work, just in the mathematical basis, that predicted also a bunch of new particles, what we now call antimatter, antiparticles.
Selectron.
Which also seems pretty out there. And in fact, Dirac, it took him a long time to convince himself that this even was reasonable. But he was right. And in fact, he was super lucky because the first antiparticles discovered about a year after his prediction came out. We now know that antiparticles exist. We can make them, and they're part of our standard model. So in some sense, supersymmetry is, if you like, the next phase of that. It's saying, yes, there's antiparticles, and then there should also be these superpartner particles, and you just have to go out and find them.
So let me just make sure we have the full playing field. So the idea then is, we see a pattern playing itself out over the course of the last 100, if not more years, where you invoke some notion of symmetry embodied in mathematics. It makes some statement about the world. You resist it at first because it's something you haven't yet seen, but then you go out and you look for it and you happen to find it. In fact, there's a beautiful quote, I think it's Steven Weinberg, where he said, the problem with us theorists is that not that we don't take our equations seriously enough, it's not that we take them too seriously, that we don't take them seriously enough.
Steven Weinberg.
Yeah, good, we have it right here. And so if you sort of take this to heart, it does suggest that if there's this beautiful new symmetry, that, as you say, seems to, in some sense, be the final symmetry that you could ever invoke because it puts sort of everything together, there's a strong mathematical motivation to look for all those particles that this symmetry implies. But that, I mean, how do you then make the argument to governments and to funding agencies, right? Because this is not a small undertaking, right? I mean, this is part of the motivation for the Large Hadron Collider, as well as with the Higgs. How much did that machine cost?
Oh, what was the cost of the LHC in the end? I mean, it's hard to. Do you remember what's the final number of the LHC?
It's billions of dollars.
Yeah, it's under 10 billion or so.
But it's a hard number to quantify. I mean, because in that number you have, like my salary and Joe's salary, I mean,
sure,
so
it's a very small fraction.
Yeah, which
now
is
we're up to 12 billion,
yes,
right?
Exactly, yeah. So, but it was. But I think that the time that the LHC was built was a very unique time in particle physics, and it's exactly like it's a unique time like we're at right now. So there's a great symmetry between the start of the LHC and the start of what's going to happen next. Which was, we had a tremendous amount of well, evidence is the wrong word, but we had a tremendous amount of consensus that that we would discover something at this energy. This energy is very unique to the Standard Model. So the energy at which the LHC can probe, let's say the energy of particles that the LHC has enough to produce, is a very key energy to the theory itself. And so if you expected supersymmetry to appear, you would have expected it to appear at the LHC energies.
And did you expect it to? In fact, I'd like to ask all three of you, because there's a lot of rewriting, I find, of history post facto that happens. And we're just a small group of friends, intimate gathering here. I mean, how many of you really would have argued and thought that supersymmetry, those other particles that we saw briefly on the right-hand side of the screen, would be found by now at the Large Hadron Collider? Nima, I mean, did you?
Well, I think...
I mean, I'm looking for a yes or no here, just so I can, like...
Actually, I would have said already. No, it's actually, but it's actually a very interesting question, because there is a whole. It's not just about supersymmetry.
Yes.
There is an entire. It's presumably something we'll come to in a second. There's a sort of whole paradigm that goes around the existence of the Higgs particle and how strange it is, how bizarre it would be to have the Higgs as a lonely beast accompanied by anything else. That's something. Even when we've seen roughly this kind of phenomenon elsewhere in physics before, we've never seen something like that for very good theoretical reasons that perhaps we'll come to. So there's a whole sort of paradigm built around what it would take to see something like the Higgs particle.
Yeah.
And it's that whole supersymmetry being the sort of best developed version and most concrete and well put together version of that paradigm. And by the way, it's not broadly the idea of supersymmetry. I mean, as it's been said a couple of times, supersymmetry is just the very last thing nature can do, compatible with its grand principles, that we have not yet seen it do.
Yeah.
But this is at the level of massless particles, right? However, there is mass in nature, and so we have to go to high enough energies where we see all the relevant particles in order to be able to see the asymmetry. From that point of view, supersymmetry could show up anywhere and still be relevant for nature. But there's a specific problem associated with the Higgs particle, which we'll talk about more.
In fact, we can do it right now if you want.
Well, yeah. So I think all the drama about the Higgs has to do with this basic fact. For all the other elementary particles, there's a difference between them being massless and then being massive. So, for example, if you ask the question, why is the photon massless? In this kind of analogy, you imagine that space is filled with these violent quantum mechanical fluctuations that are going on everywhere. While the photon is zipping through this kind of medium, why isn't it banging into all this crap all the time and picking up some inertia, just like the kind of molasses picture that we
this is just quantum mechanical uncertainty.
This is just quantum mechanical uncertainty going on all over the place, right? And those quantum mechanical fluctuations get more and more violent as you go to shorter and shorter distances,
higher and higher
energies because of the Heisenberg's uncertainty principle. So why does the photon, sort of impervious to this, go zipping through space at the speed of light? And the reason is that 2 is not equal to 3, okay? Because if the photon did have a mass, if it somehow picked up a mass with all these interactions, that's not, you can't be a little bit massive. It's like being a little bit pregnant. It's not possible, right? The extra way that it can spin has got to come from somewhere. And that's the deep reason why particles that have spin, like the photon, or the graviton, or electron, everything else, there's a good understanding for why they could be massless in some approximation, and then you've got to do something to them to make them massive, okay? And that something has everything to do with the Higgs. Well, that's the huge irony, is that the thing that gives us the understanding for why all the other things can be consistently massive, and there's a good reason why the mass of all the elementary particles is pegged to the scale associated with the Higgs. We don't understand why the Higgs itself has a mass, or what could be massless in some approximation, because the Higgs has spin 0. That's the strange thing about it. It's the simplest elementary particle we've ever seen. It has no spin, no charge, no kind of properties of any sort other than having a mass. And the difficulty is that unlike photons, for which massless guy has 2 degrees of freedom, massive has 3, the Higgs is spin 0, and 1 is equal to 1. There's no difference between the number of ways, namely none, that a massless or a massive Higgs particle can have. And therefore, as the Higgs is zipping through this complicated quantum mechanical vacuum, there's absolutely no reason why its interactions with all this virtual crap couldn't give it a huge inertia. And in fact, if you do a simple back-of-the-envelope estimate for where the Higgs should end up, it would be orders and orders and orders of magnitude more massive than naively than we've actually seen it to be.
So you need some explanation for why the Higgs didn't pick up a lot of mass going through all this fluctuating
Exactly,
stuff.
and it's really important to stress this point. It's not inconsistent for it not to do so. We can perfectly do it. In fact, we've done it, right? Higgs did it before ever having thought about any of these things. But when you think about it more deeply, you would not expect the Higgs to be right. And in fact, nowhere else in physics where similar phenomenon have shown up has something like the Higgs ever been seen, or ever been something as simple as the Higgs been the correct explanation. So if there's a mechanism, if there's a reason that we can understand that shows up right around, as has happened for 400 years in the history of physics, where to find some explanation for a phenomenon that takes place at some scale, you don't have to look at what's going on, 500 million times smaller than that scale. It has to show up sort of right around the scale of the mystery itself. If that mystery, if the origin of the mass of the Higgs was explainable in that way, which has been the trajectory we've been on for centuries, essentially the reductionist paradigm, if the reductionist paradigm that we've been on for centuries holds the way it has before, then we would have expected to see something come along with the Higgs. It's like, I've used this analogy, many people use this analogy. The sort of difficulty is like walking into a room and seeing a pencil standing on its tip. And it's not inconsistent. It's perfectly allowed for a pencil to stand on its tip, and it's okay. It's not violating the laws of physics. But if you saw it, you would probably try to find an explanation, right? Maybe it's hanging from a string, right? There's a string hanging from the ceiling. Maybe you look, there's a little hand holding it up, right? You need to find some mechanism to explain it. And it's that mechanism. Supersymmetry and the other ideas that people have talked about for decades were trying to look for a hand holding it up.
So just to give a quick summary, just a lot. Yeah. So the idea is supersymmetry provides an approach that, at least on paper, allows the mass of the Higgs to stay relatively small, like 10 or 100 times the mass of the proton, but not billions and trillions of times the mass of the proton.
It's very much related to what to how we were just talking about what supersymmetry is about. You see, supersymmetry relates particles of different spin. And if the particles have a spin, we have no difficulty understanding their mass. That's just what we alluded to. So by relating something that has no spin to something that does, we get to inherit the clean understanding we have.
So all of this gives some confidence, even if you're not willing to say it directly, but it gives some confidence that we thought that supersymmetry was going to be found. I mean, Joe, did you?
I mean, just to show how frustrating this is, at least in the simplest version of using supersymmetry to do this job, you can actually do a calculation that says the Higgs boson can't be heavier than a certain amount. And that amount this calculation was actually done by my colleague Marcela Carino, who you saw in the clip there. The answer was 130 in these units that we've been using. So when we found the Higgs at 125 in those units, it's like, okay, the supersymmetry must be right. It's right around the corner, right? But it's been a really big corner so far.
And so as we've turned the corner, we have found, what have we found? Nothing.
We found
right?
nothing.
I mean, certainly from the experimental community, it was a pretty heavy romance with supersymmetry, let's be honest. Because, I mean, from the experimental perspective, it was the experimentalist dream. I mean, it was going to be one new particle for every particle that we already have, right? I mean, I remember when I showed up at the LHC, and I was just a very young postdoc at that time, and I was working on the trigger system, so the system that helps us keep events versus rejecting them. And I remember senior physicists coming up to me and saying, like, you got to be really careful. Supersymmetry is gonna overload the trigger. And I remember thinking to myself, like, I'm happy with that problem. I'm okay with that. But that was kind of the feeling, was that this age of discovery was going to be this age of discovery again. And I think that I agree with you that I think many people, there were many problems with supersymmetry, but we didn't want to hear it at the time.
But even it's not just experimentalists, of course. I mean, I haven't done a calculation of it, but a significant fraction of every single paper I have ever written has supersymmetry at its core. The assumption that these
it's
ideas
a super deep theoretical idea.
It's a very deep theoretical mathematical idea, which has driven even mathematical discovery, not even just discoveries or non-discoveries in physics. But the bottom line is, here we are sitting in 2019. We built this massive machine in Geneva. It found the one thing that we were really certain about, the Higgs particle, and it has not found the other particles that we thought would come along for the party, because they're so, as you've articulated, directly related to the Higgs as well as directly related to this deep idea of symmetry. So the question is, what do we do from here? And we can continue to follow our mathematics, as we will do, but in the end of the day, we're going to need data. And we have to convince people to build new machines. So can you give us a sense of where we are on the frontier of building new machines that will have higher energy, be able to probe yet other domains, and perhaps maybe these supersymmetric particles are there, they're just heavier. So what's going on in that space?
So there is, let's say, a roadmap right now, but I think there's no money yet, let's say, in part of this. And there's two projects that, let's say if money was not a question, what would we do in particle physics? Well, we would build two things. We'd build two new accelerators, one of which would be a linear collider. Japan has expressed a lot of interest in building such a collider and hosting such a collider, let's say. And this would be where you, instead of colliding electrons and protons, you would be colliding, instead of colliding protons, you'd be colliding electrons and positrons. It's a linear machine, so you've got it's extremely long, and you basically collide them into each other.
And why is it a good idea to do those particles as opposed to protons?
So the advantage to electrons is that they're point-like, and therefore they're just clean. The problem is when you take two protons and you smash them together, what you're doing actually is you're smashing two quarks from inside those protons. But the actual how much energy those quarks have inside the proton is very difficult to model. And then on top of that, you've got the rest of the proton that breaks up, and it just leaves a huge amount of mess. If you look at pictures, I think we have some pictures of what a collision looks like. For example, in one of the detectors, you'll see there's just huge amounts of particles coming out.
Like we see here.
Like what you see here. So here in this event, you actually only have two particles that you're actually interested in. This would be kind of what you kind of see with these big red-blue clusters of energy. Those would be the two particles that you're interested in. And
these are tracks of
particles. And these are all, the green is all tracks of particles and so forth and so on. And most of this is just crap from the rest.
That's the technical term?
That is the technical. We use that a lot in publications.
Whoa, green is the red
so,
is my
that's just
drive,
the crap
and
that comes in the electron-positron collision. Everything's clean. You don't have this breakup of and you know exactly what the electron energy is. So from a precision measurement perspective, it's superior, absolutely superior. However, if you want to really go high energies, then you've got to go protons. Protons are what gives you your power in terms of the energy aspect. And so in addition to a linear collider in the ideal world is what we would have. So we'd have an ideal linear collider to really measure top and Higgs extremely precisely. And then in the ideal world, we would have another hadron collider, which was, the next generation, the FCC, Future Circular Collider, or there's
also... And where might that be?
And that would be at CERN. This is a picture of what it looks like. It's actually it would be a 100-kilometer ring. And what
so the LHC just pointed out, it's clear up there, but just pointed out.
Yeah, the LHC is a smaller ring here. And what's actually interesting about the Circular Collider is that God apparently put mountain ranges exactly perfectly such that you could build such a tunnel. It would have to go underneath Lake Geneva, and it would just pass right before the Alps, pass right before the Selev, coming back. So it's just perfect. Going under the lake is actually not a problem. Everyone always asks about going underneath the lake, but the thing about a lake, because they're always worried that there's going to be a leak. The thing about a lake is that there's never a leak in the lake, because if there was, you wouldn't have a lake. So going underneath the lake is no problem, but it is a problem in the sense that you do have mountains, and mountains lead to a lot of water drain.
What would the energy scale of that machine be?
So this would be, it's 100 TeV. It's 100 TeV. I suddenly drew a blank there. I saw the 100 kilometers, and I thought, it's a 100 TeV machine.
So it's roughly, not quite, but maybe 8 times?
8 times what we have now. The LHC here was 14, and then you had the Tevatron, which was lower. And so this would be your real discovery machine, right? Which would be you go out to 100 TeV and you would, again, it would be proton-proton.
But Joe, let me ask you a question, just so we have those numbers up there. So Nima was describing how the energy scale that the Higgs was at and supersymmetry in its most conventional formulation, it all seemed to come together. It was all happening at the right energy scale. Yes. Now when we go, say, from 14,000 times, the mass of the, 14 TeV to 100 TeV, factor of 8 in there, is there theoretical motivation that that particular slice of energy space is going to really hold something new, or are we just simply saying, let's go bigger because we haven't found anything yet?
Well, of course, it's a combination of those things, because there's never a guarantee that any particular collider is going to discover anything. We didn't know that the LHC would discover anything. So you're always making a gamble. But there is motivation that if the ideas that we've been talking about have any validity at all, if they're not totally wrong, that maybe what we're missing is we didn't quite have a powerful enough tool to see them. And what's the probability of that? Nobody knows. This is why it's discovery science. You're always taking risks. And Nima can.
And you've been actually making an argument to build a new machine, not in China, if I'm mistaken.
Yeah, let me just say a few broad points. First of all, we go to the frontier because it's the frontier. So that's the zeroth order thing. And but I think if you think that particle physics is about discovering new particles, and so you're only going to build a machine if you know for a fact you're going to discover a new particle and you have some idea where it's going to be and so on, then this is a perfectly good time to take your ball and go home and do something else with your life, okay? Because we have absolutely no guarantee, I cannot stress this enough, absolutely zero guarantee that, that a new machine is going to produce a new particle. There are some indications for a new phenomenon that would happen at scales, having to do with gravity and things like that, orders and orders of magnitude removed from where we are. But we had lots of theoretical arguments that something should happen right around the scale of the LHC. We haven't seen them. And there were, in any case, there were circumstantial indirect arguments anyway. So there's no guarantee that there are new particles. However, this entire, and that's why I alluded to this earlier when we were talking about the building blocks of matter picture of the world, it's maybe a little funny. That's certainly not what drew me personally into fundamental physics. I don't care that much about the building blocks of matter. It's a lot like chemistry. I sucked very badly at chemistry in school. And I don't care that much about the building blocks of matter. I care about the structure of the fundamental laws of nature. And we've learned that that the elementary particles are the letters of the novel. Excellent. That we're interested in the novel. We're interested in the structure of the laws of nature, and what we really care about are new principles, new phenomenon. And from that point of view, the Higgs is damn new. It's very strange. We've never seen anything like it before. And so I think the main, to me, and I think to most people proposing these future machines, the main thing we'll learn for sure from doing these new experiments are fundamental facts about the Higgs. We've never seen an elementary particle like the Higgs before. We have to put it under a very powerful microscope, more powerful microscope than we have at the LHC. And the main drama about the Higgs is whether it really looks elementary or not, whether it really looks point-like or not. From the LHC, we're going to get a pretty fuzzy picture of how point-like the Higgs looks. You really have to put it under, and in fact, it's fuzzy enough that we've seen roughly analogous things to it elsewhere in particle physics. Most of you probably haven't heard of this particle. There's a very important particle known as the pion that also, at first blush, looks like it might be kind of an elementary particle of spin 0, but very quickly you see that when you just put it under a magnifying glass with magnification 5, you see that it's actually made up out of little quarks held together with gluons. So all the theoretical drama that could have been there with the Higgs was actually not there with the pion. Well, that's the resolution we're going to get on the Higgs from the LHC. More or less that same kind of factor of 5 resolution that we had with the pion. But we need another factor of 10 on top of that to know if it's something really, really new, if it's point-like as we expect actually in the standard model, or if it has some substructure. And so there are two kinds of experiments that we can do. One of them is to see whether it looks point-like to other things. Like if you literally want to see that it looks point-like, you want to see what happens when a photon bounces into the Higgs. Of course, the Higgs doesn't actually live very long, so equivalently, you look at what happens when a Higgs decays to 2 photons, or into other things.
You and
then,
me.
You see whether
You and them.
that interaction of the Higgs with other stuff
You
is
and outside.
compatible with the Higgs looking point-like. That's what these so-called Higgs factories, the linear machine that Monica was talking about, is a great machine to do this. It would produce millions of Higgs. You could first collide electrons and positrons, produce millions of Higgs particles, and see whether it looks point-like to external probes like photons and the other things that it could run into. And then ultimately, if you go to the 100 TeV colliders, if you collide protons in exactly the same machine, you can ask and settle the question whether the Higgs looks point-like ultimately to itself. And that's kind of it's a sort of a fascinating thing. The very simplest interaction elementary particles can enjoy is with 3 of them meet at a common point in space and time. And it turns out no other single elementary particle actually has this interaction. Every other thing that we know, there's something that changes. Some property changes. The Higgs is the only elementary particle that can have as its dominant interaction this interaction with itself. And therefore, by looking for this interaction, not only for the first time seeing the sort of simplest possible interaction in nature, but you're checking to see whether the Higgs actually looks point-like even to itself. The LHC is not even going to tell us with confidence whether this interaction even exists, but the 100 TeV collider will produce billions of Higgs particles, and by doing that will not only tell us it exists, but it'll measure it to a few % accuracy. So I've just told you what I think of, and I think most of the people pushing for this next generation of accelerator, they're not promising, oh, we just barely missed supersymmetry, it might be right around the corner. That might be true, okay? But that's not the logic of the argument at this point. Right. The logic of the argument has to do with the fundamental kind of paradigm-shifting or paradigm-challenging nature of the Higgs itself, and the fact that theorists are confused. 40 years of ideas for what might be associated with the LHC, or with the Higgs, have certainly not been amply confirmed at the LHC, not even close. When theorists are confused, you need more experiments, and you need to do experiments on the thing that's confusing. The Higgs is the thing that's confusing, so we have to put it under a very powerful magnifying glass.
Very well said. Now, when we look at the big principles, so one thing to do is to smash harder, to magnify greater, to try to see fundamental structure that we may have missed, and so on. But in terms of overarching theoretical paradigms that will guide us forward, so supersymmetry is not ruled out. It could still be part of the story. But maybe just go down the line a little bit. Joe, what would you say? I mean, obviously, there are things that people have, string theory, which has supersymmetry. There are other things like Technicolor that people have spoken about. Do you feel that we've got the guiding theoretical structure to really give us a clear path going forward as to what we should be looking for?
I think we're in one of those periods of physics history where we really need guidance from data. We have ideas. Some of them, I'm sure, are good ideas, but we need more. We need nature to tell us more about what's really going on. And this has actually been more the typical situation in the history of physics than having confidence. And Dirac was, as I said, was the lucky guy where he had the idea and then the experiment came right along. This is the typical situation where we have some ideas. Part of it's probably right, part of it's probably wrong. There's probably something missing, and we need data to sort that out. And that's what these more powerful instruments are really for.
Now, there's a nightmare scenario that you described for the LHC. Imagine some next machine is built. What would your nightmare scenario be there?
Well, actually, I think that, coming back, having looked back now 9 years later, and, lots of data later, we didn't have any data at that time, right? So we were sort of in the, I definitely have also sort of had, let's say, eye-opening experience out of the whole thing. And I think that, basically supersymmetry basically did us experimentally a disservice, let's say, because it sort of set this expectation that I think that, that the LHC was going to be the discovery machine in the sense of discovering particles. Mm-hmm. And the LHC has been a discovery machine. And I think that, because we have learned a tremendous amount, the LHC has given us many, many precision measurements of the Standard Model. The detectors that we have are beautiful. They're stunning. The amount of precision we can get out of these detectors is amazing. It's really been an absolute success in terms of what we've been able to measure. And as I said, we discovered the Higgs in 2012. No one expected that our detectors would be at that precision at that time. We've been making measurements that we never thought. I mean, Nima says we won't be able to measure the Higgs self-coupling, but already we're doing studies that show that we could maybe start to access it, so forth and so on. So I think that we have made tremendous progress in technology. We've made tremendous progress in precision measurements of the Standard Model. And I think this idea that physics, particle physics, was about new particles was really a disservice to us. And this comment that I made 10 years ago, saying it would be Higgs and Higgs only as the worst case scenario, is absolutely a reflection of that time. I think it was a reflection of how we were viewing progress at that time. And I think there has been a big emotional shift in physics, in the sense that, exactly as Joe says, that we need the data.
Yeah.
We need to know the Standard Model better before we can really say, let's go in direction A, B, or C. And that we're really, despite its successes, despite how much we know about the Standard Model, we've all discovered that it's not enough.
Yeah.
And these next generation machines are exactly that. So in that sense, my worst case scenario would be pretty much a fire in the cavern, I think.
So, a
those
real
kinds
disaster.
Of, yeah, a real disaster.
I mean, I think we're at a moment. The most important thing is that we've seen this phenomenon that we've never seen before. And so I think it's very funny that, in a sense, seeing the Higgs and nothing else so far is by far the most shocking thing that could have happened, that could have come out of the LHC experiment.
Yeah. Yeah.
It's the biggest challenge to theorists. It shakes the conceptual grounds under us more than had we seen these things that we've been expecting for decades. It's actually funny, when I was a grad student, there was such an expectation that something like supersymmetry was right. And that was an idea that people came up with in the 70s and 80s, and the job of my generation was sort of clean up the details and figure out how precisely it broke and worked out and so on. And that's definitely not how it's worked out. In fact, the challenge just got greater, much greater. The stakes became more structural, rather than about this or that detail or this or that additional particle. I can't stress that enough. I think that the last time a whole community of theoretical physicists have been so perplexed by something and have had experimental results not align with what they expected was when we expected the universe was filled with an ether. And the absence of the ether, a null experiment, was the harbinger of the revolutions to come. This idea that a whole generation of particle physicists grew up with, that what glory looks like was the 1960s with a particle every week. It's true, it was a wonderful period, but that was not, in 200 years, this will not be the great thing about the 20th century. The great thing about the 20th century was relativity and quantum mechanics, and there's lots and lots of very important details after that. But these very revolutionary kind of conceptually earth-shaking discoveries don't have that character.
Yeah.
They're surprising. They involve things that happen that you wouldn't expect. And so I think we're in another one of those periods today. And the Higgs is not the only thing. You've talked in these programs eloquently over many, many years. There's one other very important experimental shock to the system in the late 1990s, when we discovered the universe is accelerating. Okay? And these are two different...
Accelerating expansion.
The expansion of the universe is actually accelerating in rate. These are two very, theoretically, from a theoretical point of view, they're very closely related shocks. Our astronomer colleagues want to go measure the heck out of the expansion of the universe. And our particle physics experimentalists want to go measure the heck out of the Higgs. And these are actually very closely related conceptual mysteries. I believe, I'm certainly not the only one, but I definitely believe that we're at another one of these periods that comes around every 100 years or so, where the issues at stake go up one order of magnitude in sort of structural significance. And in many ways, the Higgs is the most important experimental actor in the story, because it can be put under scrutiny. Okay, it can be put under a powerful microscope, be put under scrutiny.
Yep.
So all this talk of disappointment and nightmares and so on is, I think, kind of crazy.
Yeah, and I should point out,
yeah.
just because in these conversations I need to sort of play devil's advocate, but in 2010 or 2011, I wrote an op-ed for the Times in which I wrote about finding nothing unexpected at the LHC as being one of the most potent possibilities that could emerge, as opposed to this standard frame of mind that you're articulating, which is particle find more particles and more particles. So I fully agree. But I want to finish on one point related to the note that you just made about accelerated expansion, cosmological ideas. I just want to finish on a cosmological question. So Joe, you have written about a curious feature of the Higgs phenomenon, which is that, in the very early universe, at least in many conventional formulations, the Higgs field wasn't actually permeating space then. It was only a little bit later on that the universe kind of went through a transition where the Higgs then permeated everything. So it went through a phase transition, a change of a very radical sort. The particular mass for the Higgs field that we found suggests at least the possibility that we could be facing another such cosmological change in our future. So since that's a very bright note to conclude on, maybe you can describe what it is that we're referring to.
We can end with the end of the universe.
Yes, exactly.
Yeah, so as you said, we believe the cosmic molasses wasn't always there. It actually the Higgs turned itself on, if you like, at some point in the early universe. That's the phase transition you're talking about. And so you can ask the question, well, is the cosmic molasses just going to stay the way it is forever? Or at some point, will something else happen that involves this? And there is a calculation that you can do, at least with those standard model equations that we have. Now that we know the Higgs boson and its mass, we have all the numbers that you need to do a calculation like that. And some of our colleagues have done these calculations very carefully. And interestingly enough, we seem to be right on the borderline of a universe that will eventually want to change into something else. It seems that our universe is slightly unstable to, at some point, a little bubble of something else where the Higgs is doing something else will appear somewhere. A different value. And once that bubble appears, it will expand at basically the speed of light, and eventually it'll get to us.
And when it gets to us, what happens?
And that'll be the end of us. So it'll be a different universe, but we won't be there anymore. Now, the chance, even if this calculation is right, you would expect this to happen incredibly far in the future. So it's not like something. It's on the order of 10 to the 100 years from now. So even in the billions and billions of years, it's a very long time. So you shouldn't actually worry about this. I have gotten email from people saying I can't sleep at night because I'm worried about this. And I always reply, you have many other things you should be worried about, but this is not one of them. But to particle physicists, this is an incredibly profound thing. It's the question of what is the Higgs really forever? It's not forever. What does that mean? And one possibility is, again, this leads back to ideas like supersymmetry. If you think that nature should make stable universes, then you need some ingredient that we need to add. And what is that ingredient?
Right. Now, one thing that you could also write back to people with that concern is, since this bubble of sort of a new phase is expanding at the speed of light, by the time you see it, it's upon you.
Yeah,
so you don't have to worry. You won't see it coming. You'll just be.
You know what it looks like inside? I can't resist saying this. I'm sorry. You know what it looks like inside this bubble? Because what's going on is that the Higgs gets a lot bigger inside the bubble. So that means that every particle in your body that has a mass gets way more massive inside. So anything massive goes splat, right? The stars, you, me, everything would go splat on this, except light. Light goes sailing right through. So if you
into the black hole,
or some progeny of yours managed to make it inside the bubble and run at the speed of light to sort of keep up with the wall of the bubble. It's literally like being on the inside of a car with flies on the windscreen, right? So the whole rest of the universe is just going splat on this bubble as it goes through you. So it's a very cheering thought indeed. Sorry.
No, not at all.
Philosopher Chris Payne. Yeah, Brian.
So we just have
this is a good talk so
couple
far.
minutes to go, and I just want to give you all a chance for sort of a final word.
I'm still a black hole.
Compared to where we were, say, 10, 15 years ago, do you think that we've gotten to a more exciting place? Do you think that we've kind of gone through the doldrums? I mean, what would you characterize the state of particle physics to be today? Maybe just write down.
I always remember when I was having a really frustrating time as a graduate student, a senior graduate student in my group, saying, if it was easy, it would have been done already. And I think that pretty much really describes where particle physics is right now. There's absolutely nothing about particle physics that's easy. Whoa. And I don't know a single particle physicist who went into this field because they wanted it to be easy. Sure. So in that sense, I'm personally excited about the challenge. It's going to be hard as hell to build experiments for these new colliders. Bring it on. I'm ready. And I'm ready to take on measure the Higgs as well as we can.
All right. Nima?
Well, I tell my grad students that if I could go back in time and control when I'd be born, I would wish that I was entering grad school today.
Really?
I really think this is, from my point of view, it's the most exciting time in fundamental physics certainly in 50 or 60 years, maybe going back to the time when relativity and quantum mechanics ended up coming into existence. And it might sound crazy. I mean, so that there are other people who are wandering around, they're sort of depressed, we've seen the Higgs and nothing else, so who's right? Am I just on drugs, or are they on drugs? What? And I think it really depends on why you got into this business. If what really drives you is trying to understand something deeply conceptually new about the world, that kind of opportunity does not come along every 10 or 20 years or so. Most people don't get to experience that. And I think we're now at the point,
after Chris Payne, I am a black hole.
All kinds of easier questions, where in science you're motivated by gigantic questions, but you have to work on the next question. You have no choice but to work on the next question. Well, we're finally at the point where the next questions are these gigantic ones, or these sort of existential ones. What's space and time? What's the origin and the fate of our enormous universe? Why can there be large macroscopic structures when there's enormous quantum mechanical fluctuations that seem to want to destroy them, and so on? These questions even seem to be interrelated to each other in some way, potentially. And our generation of people are the generation of people who get to work on these questions responsibly. It's meaningful for us to work on them because there isn't like 10 other questions in between us and them. And so I'd like to say it's like you want to climb Mount Everest. First you have to get in a plane, go to Kathmandu, find Sherpas, foothills, all kinds of stuff.